All right, I'm Sarah from Flashbots. Thank you all so much for joining us for our fourth Mev-Sbc, the MEV workshop at the Science of Blockchain conference. Our first speaker today will be Quintus Kilburn from Flashbots.
Hello? Is the mic working? No? How about now? Okay. All good? Okay. Hello, everyone. I'm Quintus. I'm from Flashbots Research. And today I'll be talking about a topic that sort of steps outside the scope of the things we usually talk about at these kinds of events. And I hope this is an expansion of scope that will be lasting, and we'll see more of this in events to come. And I'll be talking about the sort of the idea of trust and the idea of trust in hardware, hence the sort of confusing name. Now, before I start, just to set the ground, a TEE at a high level is a piece of hardware that gives you some security guarantees against an adversary and can convince a remote user that a program is protected in its privacy and its integrity, even when that user doesn't have access to the machine. Now, TEEs have seen a lot of uptake recently. You can see many examples. WhatsApp is an end-to-end encrypted messaging service, which now sends user data to a TE-secured LLM, optionally. Apple has launched a private cloud compute service to run AI workloads on user data that used to be kept only locally on their devices. Organizations like Flashbots are pushing for TEEs to be used in blockchain block building. On some days, close to 50% of Ethereum blocks are being built in TEEs. Signal uses TEEs for contact discovery. There are many more examples that I could go through, but the basic point is that there's a big trend. And the problem with this trend is that TEEs are full of holes, as they are today. The adversarial model doesn't consider the supply chain. It doesn't consider physical attacks. And so we're left in a position where actors like Intel and AWS are able to completely circumvent our security mechanisms. We're also left in a position where, because security is based on reputation, there are only a couple of big, reputable actors that we can interact with instead of having a very diverse ecosystem. And I think the first step to addressing this problem is breaking away from a kind of abstraction that we have. We tend to treat hardware sort of falling from the sky, and then we just accept it. We either use it or we don't. It's either secure or we don't. But in reality, it's this kind of almost beautiful object, which is very complex, but it's also engineered. There are many trade-offs, and it can be designed for different use cases if you can articulate those well and make the case. So I guess part of this message is that I think we should design towards an ideal, and this ideal is the trustless TEE. And what is that? Well, I think I just mentioned that physical security is a big problem, and really what we're interested in is verifiable physical security, meaning that not only should the hardware protect us against adversaries who have physical access, it should do so in a way that we can be convinced that it actually does it, meaning it's open source so we can verify that what security mechanisms are in place, what code is actually running. And in order to do this, we need verifiable remote attestation, meaning that a remote user can be convinced within an interesting security model, not just trusting a central party, that they are indeed interacting with a piece of hardware that satisfies a certain design. So to elaborate on this, okay. So do you guys want to hear a joke? I was speaking to my plastic surgeon the other day. His name is Philip.
Texas, because California doesn't have an accident. Okay, you guys are. They laughed at Tesla.
I think because it's live streamed, we're somehow limited. Yeah. That's another one. Is it? Okay, I will speed run that for the sake of the audiences in future who hopefully will attentively watch the recording. Sorry? Oh, yes. Okay. Hello, everyone. I am Quintus from Flashbots Research. uh, I can, but I think all the ones that I can think of, I probably shouldn't. I'm not educated enough. Yeah. Is that good now? Yeah, yeah. Good. Hello, everyone. I am Quintus from Flashbots Research, and today I will be expanding the scope of the things we usually talk about at events like today, and I hope that this expansion will be lasting. As you can see, I'll be tackling the idea of trust in hardware. And before I start, I should explain like a basic definition for those who don't know. A TEE, a trusted execution environment, is a piece of hardware that gives us some assurances that code is being run in a confidential way with integrity against some adversarial model, and can convince even a remote user that this is the case, so the remote user can open a secure channel with the TEE. In recent months, we have seen an incredible uptake of TEEs, partly due to the advent of AI, partly for other reasons. WhatsApp, an end-to-end encrypted messenger, is now sending user data optionally to an AI-based or a TEE-based AI inference tool. Apple has launched a TEE-based private cloud to move data and computations that used to be local to the cloud. Organizations like Flashbots are trying to, or advocating for and developing TEE solutions for blockchain block building. On some days, up to 50% of Ethereum blocks these days are being built in TEEs. Signal uses TEE for contact discovery, the list goes on and on. And the basic point is that TEEs seem to be growing and growing in importance, and part of the reason for this is that they're just much easier to use and much more performant than anything else we have to offer. Now, the problem with this is that there are many holes in the security models. For one, the sort of supply chain and manufacturer is a trusted actor in the TEE security model, and TEEs also don't protect against physical actors. This means, one, that we are vulnerable to actors like Intel and AWS should they decide not to have our interests at heart, but also we have to interact with actors who have a strong reputation because security is based more so on trust than on actual technical enforcement. I think the first step to changing this, to plugging these holes, is to break away from a kind of simplifying assumption and mental model that we always have, I think, in this community. And that's that the sort of hardware falls from the sky, that it is something we take and it's either secure or it's not secure, where in reality, it's a very complex object. And I think sort of in this, at least in this case, you can see it's quite a beautiful object, which is designed with trade-offs in mind and can serve different kinds of use cases and has an active body of research going into it for security and performance. And really, I think we should try to influence this to our needs. So what I'm going to advocate for today is that we should try to strive for a kind of ideal from the hardware space. And I'm calling this a trustless TE, which obviously is an impossible thing. There's no such thing as trustlessness. But it's an ideal that I think we should strive for. And what I mean by this is that, like I just said, we're missing physical security in these devices. And I think we should strive for verifiable physical security. So not only should the hardware protect against physical attackers, the design should be open and auditable. The code should be open and audible so that we can tell whether these countermeasures meet our bar. Secondly, we should have verifiable remote attestation so that users who do not have access to the physical device can be, without simply trusting a central authority, convinced that they are actually interacting with a piece of hardware that satisfies the advertised design. So what do I mean by remote attestation? I can sort of give a slightly more detailed abstraction to talk through it. So imagine we have an adversary that presents us a piece of hardware, and they have an interaction with an inspection body, a certificate authority that has a look at the hardware. This certificate authority can then issue a attestation, a certificate to a user telling them, hey, we think this piece of hardware does satisfy the blueprint. And with that, the user should be, with some confidence, able to interact with the hardware knowing what its design is. Obviously, this doesn't make any sense if the hardware doesn't actually have interesting security properties, which brings us to another kind of abstraction I want to give. So when we think about physical adversaries, we have to think about various attacks we don't always have to think about in software security. One is physical side channels like power channels and electromagnetic radiation. Another is fault injection. The adversary can influence the execution of programs on the chip, and finally, there's adversaries can literally drill into the hardware, shave away at it, and we have to think about these things. And we have two kinds of goals that we could strive for with physical security. The first and easier of the two is integrity, meaning that a program only returns a value if it's correct or doesn't return anything at all. The more challenging property, but also the more interesting, is confidentiality, which broadly means that the program doesn't leak. But I think we can be a bit more specific. And one thing we can target is the adversary only learns a sequence of instructions that are being executed and maybe the memory locations that are being accessed, but doesn't learn any of the data that is being operated over. What this implies is that if any software program satisfies memory trace obliviousness, then it should be secure. And Elaine will talk about that after this, so I won't elaborate, but that's a useful pointer, I think. You'll notice that I haven't spoken about the TE attacks that people usually talk about, like Spectre, Meltdown, all these kinds of attacks that rely on there being adversarial software running on the same hardware as the program we're trying to protect. And the reason I haven't spoken about this is partly because if we can secure against a physical attacker, we've secured against these as well, but also because these kinds of attacks are partly or largely often a threat because of the design decisions made in the hardware, not because of the inherent requirements of the use cases. We often don't have to run adversarial or unknown code next to the open, trusted code or audited code that we're running on hardware. So at this point, you might be saying, so what? I'm a cryptographer. I'm a long-term thinker. In 10 years' time, our cryptography will be way more performant. Why would I care about this new field of hardware that hasn't really given us any great results yet? Well, I think there's a couple of reasons that you should care, even if we think in the 10-year time horizon, and we think, okay, snarks have gotten way more efficient, MPC, FHE, whatever, have become way more efficient. One is that I think performance is still going to be important. And one way to see this is an important differentiator between the technologies. And one way to see this is that MPC requires that a physical adversary doesn't have access to all of the parties, meaning they have to be separated in space. And this requires communication overhead, which will still be present even if we minimize computational overhead. And I think because a lot of the digital interactions on the internet are becoming more automated, not involving humans, the latency differences that we can tolerate or that will be important are becoming smaller and smaller. Second is that TEEs have unique trust assumptions. Maybe not even better trust assumptions, maybe worse trust assumptions, but they're different. And you can see this today where deployed MPC protocols like threshold signing products already require that the parties in the MPC run in TEEs to minimize collusion risk, an undetectable threat that is very real and makes setting up MPCs very, very complicated. Finally, we have governance over physical objects. Already today, we have cameras that journalists use to sign photos to attest that this is actually a photo taken in somewhere in the Middle East. It's not generated with an AI model somewhere in the US, for example. We may also want to attest that surveillance cameras are not sending data off somewhere. It's all being processed locally. And you can make all sorts of very interesting examples with autonomous vehicles, with robotics. The point being that I think secure hardware is a required component in giving us assurances in these systems. The bottom line is that TEEs are here to stay. And for some of you, this might be horrifying. The hardware world hasn't provided us the kind of primitives that we're looking for before, and really hasn't even embodied the ideals that we want before. It's a space where everything is closed, and there's a lot of trusted relationships and large organizations that dominate. However, I think that there are important changes that have happened. There have been important changes happening in the hardware world that should give us cause for hope. The one is that there have been research breakthroughs that have allowed us to, or the hardware community, to apply rigorous security models, those that should be familiar to people in this audience, to hardware security reasoning. And at the same time, we've had a lot of advances in the open hardware ecosystem. And the combination of these two advances gives us hope, because the same feedback cycle that have allowed us to significantly improve security and reach the point we're at today in other domains of security can be applied to the hardware world, where researchers, based off minimal assumptions, do a security proof which we implement in practice. This is then tested through open verifiable means, and again, we can go through the cycle iterating towards secure assumptions and implementations of these abstract schemes. To give you an idea, I thought I'd just put a chart that looks way more convincing. This is a couple years outdated, but there's just been many more chips being produced for which the actual physical design, the picture, the layout is publicly available. At the same time, there are a number of projects I listed two here doing open silicon where the design is at least partly open, targeting specifically secure use cases. These aren't there yet, but these aren't satisfying our use cases yet, but they are paving the way and providing a lot of reusable blocks that will be useful down the road. So on the research front, we have several problems that we have to tackle, and I'm going to flip through some solutions to these problems, not because I'm giving an exhaustive list, but just to give you almost like an existence proof that, hey, there's at least one idea that we can use to tackle these problems, but there are many more that I won't be mentioning. So first, we can divide our problem space into sort of physical attacks and supply chain attacks. Those that can be carried out on the hardware once it has been complete, and those that can be carried out by actors who tell us that they've designed the hardware in a certain way or manufactured the hardware in a certain way. On the physical side of things, we can divide into non-invasive and invasive attacks. Non-invasive attacks are those in which the structure of the chip hasn't changed. And this allows us to make some assumptions about what the adversary can see or do. Then invasive attacks are those in which the adversary does change the structure of the die or the chip. They drill into it, they shave away at it. And then on the supply chain side of things, we have two problems. One is, given access to a physical piece of hardware, can I tell that it does match an advertised design? And then the second is, how do we convince a remote user who doesn't have access to the physical design that some public key is associated, or some key pair is associated with a piece of hardware, and they can interact with this key and then only interact with the rules set out by the design of the hardware. So how do we bootstrap a protocol to leverage this inspection to give remote confidence? So one technology that's interesting, and actually one of the most interesting technologies to look at here, is PUFs, physical unclonable functions. And the high-level description here, I think the analogy is a physical hash function, is that there is natural variation in the ways in which we produce physical objects. No matter how hard we try, we can't exactly replicate the same object, and this is a problem that the hardware world has been trying to solve for a long time. And through the use of clever structures, we can amplify these variations to create a secret assigned to every physical object. Make it so sensitive that every chip, even though they satisfy the same design, has a different secret in it, and make it so sensitive that if someone does penetrate the die, shave away at it, the secret is destroyed. The hash function produces a different hash. And this is interesting because it helps us to avoid the manufacturing process requiring the manufacturer to generate keys and then inject them into the hardware, which is obviously a big security concern. It also helps us to protect against physical attackers because changing the physical structure of the die should change the secret, the key. And here's just an illustration of the kind of idea we want. We want a high probability of bits flipping in puffs when an adversary alters the structure of a die, of a chip. Die equals chip for this talk. And so that satisfies the invasive and inspection problems that I was talking about. Another interesting technology is Iris, which is an inspection methodology, like a visual or optical inspection technology. There are already technologies that allow us to, with very high confidence, tell exactly what a chip's design is, but these are destructive and expensive. This technology is interesting because they are trying to reach a point at which we do not need to destroy chips, and we can quickly and cheaply audit them to know what their design is. Complementary to this kind of technology, there's lots of research going into how we can design chips so that if there is a Trojan, if there is a backdoor inserted, it is obvious through a kind of technology like Iris. That's another technology satisfying inspection. Now, talking about the protocol that I mentioned we needed, you can imagine some world in which we have a magical 100% accurate inspection protocol where, given physical access, we know for sure what design has been implemented. In this world, a trivial protocol would be one in which we have n inspectors, each of them inspects the device and publicly attests to the device being correct and being associated with a certain key. In that world, a remote user only needs to trust one of these verifiers to have confidence that they're interacting with the chip they expect. Now, this isn't realistic. Inspection isn't perfect. And we can come up with some more like cryptoeconomic arguments around this as well. But this should give you a flavor. And I put a QR code there if you want to understand the problem a bit better. So that covers the protocol. Right. So the last thing I haven't mentioned is non-invasive attacks. And this is actually probably the most interesting class of attacks for this audience, partly because it's quite complicated to deal with these. Dealing with non-invasive attacks involves changing the way in which we do computation. And this necessitates taking performance trade-offs and navigating these well. And the style of reasoning that has been applied to dealing with these attacks is very similar to those that the cryptographers in the audience should be familiar with. So at a high level, just like in other forms of cryptography, we find some asymmetric advantage for the defender. In this case, the defender pays a polynomial or even a quadratic overhead in latency or surface area in the chip, which means that the attacker has to pay an exponential cost in the bandwidth of the side channel, the amount of information they can extract per second. And this is about, here I'm talking about side channels, but you have a similar argument for fault injection in which the precision required is amplified. So masking is a technology that you can think of at a high level as like MPC on a chip. It splits a computation into multiple shares. And this is used to mitigate side channels, to require the adversary to take longer and longer time observing the chip before they can extract any information. If we can make the amount of time sufficiently long, then we've reached a high level of security. Now, masking has a very interesting history, which I won't go through today. The point I'm just trying to make is that after more than 20 years of working on this kind of problem, a very interesting, a very important contribution was made, and that is of arbitrary composability. Before this point, protecting a circuit against side channel attacks using techniques like masking was very cumbersome. It required many hours of labor from highly skilled cryptographers and security researchers. And even then, they would still make mistakes. Now, with arbitrary composability, we need only do this laborious effort for a set of small gadgets, which can then be arbitrarily composed. This means that security can be very easily scaled to much more complex circuits and the processes that we ultimately are after. And unsurprisingly, immediately afterwards, or the year afterwards, the first automated tools for generating secure circuits, secure in this physical sense, was published. And many more have followed since. The problem now is no longer finding some notion of security that makes sense. It's optimizing these and making them performant and useful. One thing I want to say to this audience also is that this is a field of research that should be very appealing because it has a very strong connection, a mathematical connection, with the cryptographic foundations we rely on as well. Leakage resilient cryptography, this field of research falls within leakage resilient cryptography, and there's a strong chain of reductions that traces from the abstractions that we know as well down to security models that are very close to practical security, and a lot of work has gone to map between what is actually physically secure and what a threat model tells us. A mathematically abstract threat model. That slide was wrong. So, to recap, I've said that TEs are increasingly important and that we can't get away from that no matter how, not no matter how, maybe we have quantum cryptography or something like that, but probably it's going to be a very important technology for the next 10 years, if not many more. I've also said that there's a lot of problems with the technology right now and said that we actually can do something about it. One challenge, though, is that us in the software community don't always feel empowered to make changes in this hardware world. It's a foreign world. It requires a different skill set. But actually, we can do something. There is a long history, if you look at how hardware was developed of there being a conversation between the hardware and software worlds. Hardware designers ultimately want to target applications just the same way that designing cryptographic protocols try to target applications. And for them to do that, they need to understand what the use cases are and where the demand is. At the same time, we need to use the hardware and develop software that optimizes for the hardware constraints. So what we can do at the moment, apart from actively investing in the hardware world and trying to make changes there, is give our part of the conversation. I'll give some examples of how I think we've done this well in the research world. One example is this trusted incrementer paper, which uses non-equivocation properties of secure hardware to implement a fast consensus mechanism. And what this paper does well is that they rely on minimal functionality. They don't assume that we have some abstract processor that is secure for all computations. They narrow down the specific functionality that we need, which makes it much easier for a hardware designer to say, oh, okay, this is the thing that I'm trying to secure. Let's optimize for this. Let's try to meet the performance requirements within the level of security we need. Another example is a ZipNet paper, which will be discussed later today. This is an anonymous broadcast design. And what's interesting about it is that it uses TEs for efficiency, but it does it in a clever way. It's not simply relying on the TE as being a trusted third party. Instead, it has this layered approach where the physical security only gives us liveness, and if there's a break in a TEE, that is immediately detectable because the protocol goes down, but we still preserve confidentiality as long as the cryptography works. A final example, and this is maybe the hardest one, is Raccoon, which is a signature scheme that is designed to be efficiently maskable, efficiently protected in a physical sense. And I think this is something we should look to because designing our protocols and our workloads to be physically secure makes it much more likely that we can navigate this sort of efficiency security trade-offs that the hardware design must if we are to meet this sort of trustless TE ideal, or at least move closer to it. To end, I think I'd like to go back to the definition of a cypherpunk. And I've highlighted here that a cypherpunk is someone who not only leverages security and privacy technology, but it is someone who tries to do this to effect change in the world. And sometimes when I speak to people about secure hardware, they are reticent because they prefer the abstraction and the mathematics that we see underlying software cryptography, which is much more familiar. And I firstly reject that because I think we can apply the same level of rigor to hardware. But also, even if that wasn't the case, really, if we look at what's happening in the world, hardware security is what's providing the kind of guarantees we would like to provide to more people than a lot of the other cryptography we're working on. That doesn't mean we shouldn't work on it, but it also means that we can't ignore hardware security. And really, I think it's a mistake of this community not doing so. So I've been working on an initiative for the last year, the Trustless TE initiative, along with some other people, that is targeting actually realizing a more secure, in the senses that I mentioned here, TEE in the next 3 years, and advancing the required research. If you want to learn more, you can scan this QR code. And I added a picture I won't explain here, just to remind you that hardware is also beautiful. Thank you.
All right, thank you very much, Quintus. Do we have any questions? I think I can start us off. From your experience now interacting with hardware manufacturer, in addition to cryptographers and researchers, has anything surprised you? Like, how does hardware manufacture work in ways that may diverge from what we expect?
I think that probably the most surprising has been that security through obscurity is a relatively common, or like the de facto perspective in the hardware world. I think to this crowd, it's obvious that like having something open and auditable is the only way to really give high confidence that it is secure. And in that world, people just haven't come to see it that way. I don't think that's because that's actually how you achieve security, but it's because the sort of business and commercial needs have led everything to being closed source, and people have been using it as a crutch. And so I think just getting away from that already moves us quite far in the right direction.
Thank you. Other questions? Yeah.
In May, I had breakfast with the new CEO of Intel, and there's a lot of cool stuff. And what are you doing with Intel? You've mentioned them a couple times.
We haven't spoken to Intel about the hardware specifically. I think.
So what's your background? Because you can talk to me afterwards, because I have this group that's working on this encryption stuff, and you might fit in because Intel's making it possible to integrate this kind of work into their chips. Yeah, and so I was just wondering what you were trying to do with Intel.
Yeah, I should have introduced myself as a junior software engineer. Like I'm not a hardware guy. I'm sort of a coordinator between the hardware people and us with the use cases. I think having not really spoken to Intel about this in depth, about more like software level things, I think one challenge for these large companies is they invest tremendous amounts into their chips. and so have to target a very large user base. And right now, the people who need GDPR tick boxes is a much larger group than the people who actually care about security. And I think that can change over time, but first we need to demonstrate that to them. And so right now, their like closed source security model, or closed source business model is probably more likely to be appealing to them, and the security trade-offs is likely to be unappealing. In the long run, I think that'll change, but that seems like an uphill battle in the short run.
Well, we should talk. There's two other groups that I'm working with, and I think you might be able to fit into the puzzle. And there's also a big announcement potentially at DevCon, a zero knowledge proof that if it actually stands up to scrutiny, will revolutionize encryption. So I want to include you in that circle.
That sounds amazing. Okay. That's not a question, but I love it.
Did any other of you working on this? I used to teach it. So I used to teach at Berkeley. I taught the entrepreneurship for engineers, even though I'm a mathematician. And we used to show up startups like inside Soda Hall, like Databricks and things like that. And what the idea is to basically integrate all the technologies that are evolving. And Intel started out of here. Andy Grove and Gordon Moore both were graduated from Berkeley. And the idea is to put this future technology and put these groups together. And if you have anything like this, my email is really easy to remember. It's just berkeley@gmail.com. Okay.
Strong. Oh, behind you, Sarah.
All right. Any other questions? Yes.
Thanks for the talk. I have a question about, so you've been interfacing with hardware people, trying to figure out, I don't know, which direction they're heading. What incentives do they have to sort of like take the knowledge that they've built they've accumulated a lot of knowledge building secure enclaves and so on and so forth, and probably all of those knowledge is inside NDAs at the moment. What incentives do these people have to sort of like, push this forward with us without NDAs, or like, I don't know, or we start from scratch, but like that's a long road.
So I will say that we aren't starting from scratch, and that there have been efforts already to move the open hardware ecosystem forward. I think the incentives, you can think of different incentive models. Probably the one that seems the most likely to be appealing to me now is that you can look at a project like Calyptra, which is a root of trust that the cloud manufacturers are all investing in. And the reason they're investing in this is because it's like too much effort for them all to do duplicate work, and then rather just have it be secure and be a standard that they all rely on. It's basically economically more efficient to invest in like a shared open source repo that they can all rely on than doing duplicate things with different standards that might be less secure. Also, more broadly, there is an increasing persuasion that openness is important for security, hence the project that I was mentioning. So obfuscation gives you security, gives the big guy security against the little guy. Like, it takes 9 months to reverse engineer it. That's actually decreasing, but like, in the extreme, it takes 9 months to reverse engineer what a chip is, and then they might sue you for publishing the results. But it doesn't prevent the other government from reverse engineering the chip, and so the small guy still has no protection against the big guy. And as more IP moves into these chips, and like Tesla's model weights are moved into their cars, I think they have more reason to invest in this kind of security. And we should not rely on obscurity, because we're the little guy trying to be protected against the big guy. It shouldn't be big guys protected against the little guys. Yeah. I don't know if we have time, but there's another question.
Ask about the standards. Are standards
These standards are more at the interface level. It's not about the level of security. It's more about just the. No, it's like attestation standards. Yeah.
All right, let's thank Quintus. All right, thanks everyone. We are back. So our next speaker will be Elaine Shi, who's a faculty member at Carnegie Mellon University and the founder of Oblivious Labs.
Test, test, test. Okay, sounds good. Turned off.
And sorry, with the camera visual field, you have to be standing like here.
Okay, sounds good. Okay, so I'm very excited to be here. Actually, Quintus emailed me and said, oh, we want you to come to the MEV workshop to give a talk. Talk about ORAM. And I said, oh, of course, I'd be happy to talk about ORAM anytime. And then he said, oh, no, but we don't want you to talk about ORAM because we have heard about ORAM. so I'm going to talk about compiler for oblivious computation today. Or in other words, I will tell you, do you actually need an ORAM? Okay, and before I explain whether you need an ORAM or not, let me first explain what is ORAM and what are the applications of ORAM, just very quickly. So I'll just take Flashbot's use case as an example, right? So in order to mitigate MEV, a great approach is to encrypt the transactions so that when you build the block, the miners don't see the transactions in the clear. And Flashbots has built a BuilderNet, and it has SGX TE support. And then we are going to do the block building inside the trusted enclave called TE. And I want you to think about the transactions as small programs. They are smart contract programs. So as we build the block, we have to speculatively execute these programs. And as the programs execute, they will access data that live on the blockchain. And even if everything is encrypted, like your transactions are encrypted and the blockchain data can be encrypted, the accesses to the blockchain can still leak sensitive information. And in this case, the information that gets leaked includes things like which crypto asset is being traded and who are the sender and recipients. And these are precisely the information we care about hiding. So it is very important for us to try to hide the access patterns to this big data set. Okay, and here's a concrete example to just show exactly what gets leaked. And this is like a Uniswap contract. And if you are going to execute this contract, it's going to access sensitive information like the crypto asset you are going to trade, as well as the account information. So this is the information that will get leaked. And in order to hide access patterns, we can use this powerful tool called ORAM, which stands for Oblivious RAM. And in this talk, I want you to think about ORAM as a generic compiler. And why do I say it's a generic compiler? Because given any insecure program that runs in time t, you can take the ORAM compiler and it will emit an equivalent program that runs in just a little longer in t log n or t log n square time. And this resulting program is oblivious in the sense that the memory access patterns don't leak any information. And the security is provably guaranteed. Okay. So because ORAM is a powerful building block, actually there has been exciting developments in real life. These are some of the use cases of ORAM. Signal has actually deployed ORAM at a large scale, and they use it for private contact discovery, right? So if you actually use Signal and they ask you for your contacts, don't worry, because they're using my algorithm, it's perfectly secure. Ethereum wants to use it to enable private blockchain reads. And actually, yesterday I was on a call with Ethereum Foundation, and we are very excited to collaborate with Ethereum to help them make this happen. And Meta has also implemented ORAM, and I think likely they're using it for private AI, like maybe to analyze data collected from WhatsApp. But I don't know about this detail. The detail, it's an educated guess. I think they're being a little bit secretive about exactly what it's being used for. Okay, so in fact, what's important to observe is that in all of these scenarios, traditional encrypted databases fail. They don't solve the problem, because if you think about it, in all of these, let's say in Ethereum's case, right, the data itself is public. So it's not the data content that we care about protecting. It's actually the accesses to the data. So traditional encrypted databases, they only encrypt the data contents, and they basically don't do anything to address the privacy concern. And so is the case with Signal's use case, because in Signal's case, the data actually Signal can already see the database, and it is the queries that they want to hide. So really what you need is ORAM rather than traditional encrypted databases. So if you want to use ORAM, as I said, ORAM is a very powerful tool. It gives you a generic compiler that can convert any program to an oblivious form. And if you want this generality, it's known in theory that you have to suffer from a log-n performance lower bound. And this was proven by Goldrick and Ostrovsky. And we also know that if you make some computational assumptions, like if you assume existence of pseudorandom functions, we can indeed match this lower bound. In practice, we don't use these computationally secure schemes. We use a different class of schemes called, so typically we use either path ORAM or circuit ORAM, and they're based on a new paradigm called binary tree ORAM paradigm. And these schemes, in theory, they get log square performance, but because one of the log has a large base, in practice, they actually just behave like log-n algorithms. Okay, so that is ORAM landscape. And having talked about ORAM, I will now try to answer the question, do I need an ORAM? In my earlier talk, I guess maybe in MEV workshop last year, I showed this decision chart. Do you need an ORAM? So pretty much, if you want to use TEE or MPC, you really want to think about this question. Like if your computation task is somewhat interesting in the sense it will make dynamic accesses to memory, then really you want to think about using an ORAM. Otherwise, it may not be secure. But today, I want to give a more nuanced answer to this question. Do I need an ORAM? And the thing is, like, indeed, we want to protect access patterns, but ORAM is not the only way to protect access patterns. And this log-n lower bound for ORAM, if you have a concrete computation task, this log-n lower bound may not apply. Like you can oftentimes do better. Like for instance, if you want, what you want is just sorting, or you want to run some Dijkstra shortest path algorithm, or you want to run compaction, which is a special case of sorting, or you want to have a priority queue. Like in all of these cases, and there are many, many other examples. In all of these cases, like we often know oblivious algorithms whose performance actually even match the insecure counterpart. Like we don't have to suffer from the log-n overhead. So for this reason, like we shouldn't just generically just apply ORAM and, I mean, of course you can do that, but it's just like you have to suffer from more performance overhead. Okay, so I will kind of take a algorithms compiler code design perspective to tell you how we can take advantage of this insight. And on the algorithm side, right, so on both sides, we are asking the question, do I actually need ORAM? But more specifically, on the algorithm side, we are asking, given a specific computation task, how can I design an efficient oblivious algorithm, possibly, circumventing the need for using ORAM? And on the compiler side, it's a slightly different variant of the question. I'm given a specific program, and I want to look at this program and compile it to an efficient oblivious implementation. So that's the compiler's goal. Okay, and then when I go over, I will go over some examples, and I will tell you the algorithm's perspective, and I will tell you how the compiler can, be inspired by these algorithmic ideas and automatically emit efficient oblivious implementation. Okay. So idea number one, so this is a very simple idea. It's essentially partitioning, right? So from an algorithm's perspective, we want to look at a program and partition the accesses into ORAM accesses and non-ORAM accesses, because some accesses are actually safe to reveal. They don't disclose sensitive information. And then we can actually automate this analysis using a compiler. The compiler can take a look at your program using a standard technique called information flow analysis. It can figure out whether each access has to be protected or not. Okay, so let's look at a simple example. This is a really simple program. It just linearly scans through an array to find the maximum element. So you don't actually have to read the code in detail, but you can see like the access patterns into the array is just determined regardless of the array contents. And in this case, actually, you don't need to put the array in ORAM. And you can, if the array is actually secret, you can just encrypt it. You don't have to put it in ORAM. But the compiler is still going to, so this is like a side note, like the compiler actually will still inspect the program and rewrite this control branch by padding the else branch. And the reason for doing this is that it wants to guarantee that both branches have the identical traces. So like it should not be the case that an observer can look at the instruction or memory trace and determine which branch is taken. Because if you look at the guard for the branch, this is a secret guard, right? Because suppose let's say the array contents are secret. HI is a private array with secret contents. Then this array, this conditional is a secret conditional. So you want to make sure both branches have the same behavior. Okay. So, but nonetheless, we don't need ORAM in this case. And here's a more, of course, the find max is very simple. Here's a more realistic example. Like this is actually a main loop in a Dijkstra implementation. And the details of the algorithm is not important. But if you look at the code, you'll realize that there are three arrays: the distance array, the visited array, and the edge array. And if you look at the code a little more carefully, you'll realize the distance array is always accessed sequentially. And actually, we don't need to place the distance array in ORAM, and we only need to place the visited array and the edge array in ORAM. So with this kind of analysis, and basically, our compiler can automate this analysis. And with this kind of analysis, we can basically avoid the usage of ORAM whenever possible to improve the efficiency of the execution. Okay, so this is the first idea, partitioning. The second idea I want to talk about is we can actually design programming abstractions for obliviousness. So again, from the algorithm's perspective, like one approach is like for every computation task we care about, let's say today I want to implement a heap, tomorrow I want to implement binary search tree, we are going to design a customized algorithm for every task I care about. But this is a slow and maybe somewhat tedious process, right? A better approach is we are going to look at classes of algorithms. So I want to have an understanding for certain classes of computation, I can do better than ORAM. And this is what we are going to try to achieve from the algorithm's perspective. And from the compiler's perspective, we want to be able to design programming abstractions. And if the programmer writes the program in these abstractions, then the compiler can get some insights, get some hints during the compilation process, and avoid the usage of ORAM. Okay, now this may be very abstract, but I can give you an example and you can see like a concrete example. So this is just trying to compute a histogram. It's a very simple program. So this is how you normally write the program, right? You just scan through the array, and then for every element you encounter, you increase its count. And if you do a normal compilation, if you write the program like this, the compiler will see that if your array is a secret array, the array contents are secret, then the access patterns will leak the array contents. So it will decide to put the count array in an ORAM. And this will create some performance overhead. However, imagine the program wrote the program using a map-reduced abstraction. So histogram is something that's very easy to implement with a map-reduced abstraction. Like essentially, for every key you encounter, you map it to R, 1, where 1 means I have seen it once. And then the reducer gives an aggregation function that just adds up the count. So if you write it with a map-reduced abstraction, actually the compiler can realize, we don't need an ORAM in this case. We can just compile it to oblivious sort. And for oblivious sort, we have like, this is a paper that's going to appear in Usenix this year. And we have these fast implementations, and the performance will be much better than ORAM. Okay, and here's how the sorting-based solution works. So we have these keys. We want to do histogram. We first obliviously sort it. So the same key will appear adjacent to each other. And then we do a linear scan. And with this linear scan, essentially every element will look at its neighbors. And the last element of the same kind will write down the count during this linear scan. So like, for instance, the count is like apple appears twice, banana twice, and I guess it's wrong. It's like 3. And then finally, you can sort it again. So the actual counts appear in the front and the dummy entries appear at the end. So now you gather the counts for every element. Okay. So actually, this is not a coincidence. We actually have a lot of insights about how to compile parallel algorithms to oblivious counterparts without going through the ORAM transformation. So in general, the high-level intuition is that if your computation task is parallelism friendly, it can be efficiently expressed as a MapReduce program, or efficiently expressed in the GraphLab abstraction, or in the binary fork join abstraction, then actually we can compile it to an oblivious implementation without going through ORAM. And oftentimes oblivious sort is enough. Okay, so from a programming language perspective, we are going to allow our programming language to have these programming abstractions. And when the developer uses these programming abstractions, it can help improve the performance of the compiled implementation. Okay, so finally, I want to give you another example of a programming abstraction. And for this, I want to illustrate the algorithmic idea first, and then I will tell you how it generalizes to programming abstraction. So it's oblivious data structures. So data structures are used everywhere, right? You know, there are lots of data structures. So let's imagine we have a simple binary search tree, and we want to make an oblivious binary search tree. The most naive idea is that we are just going to use ORAM to compile a plain insecure binary search tree. So let's say we are going to take AVL tree and use ORAM to compile it. With the AVL tree, every access takes log n time. But when you use, let's say, path ORAM to compile it, every memory access incurs log squared overhead, right? So it's multiplicative. Log squared times log n. So essentially, you get log cubed cost per request. And I will tell you a better way to accomplish this so we can save a log factor. And in order to understand the idea, so I will not go into ORAM in detail, but I will quickly talk about how to think about ORAM, because to do this trick, we need to use like a building block that's part of designing the ORAM algorithm itself. So essentially, ORAM is a tree. It's a binary tree. And in ORAM, every element resides on a random path from the root to some random leaf. So let's say, you know, some element you care about resides on this blue path. So I will just abstractly draw the tree as a triangle, and I will draw the path as a line. And then if I want to access some element, I just have to access the path that the element resides on. But besides doing that, I also have to do some maintenance work, which I call relocate on this slide. Like I'm going to get the element I want, but I will also move things around on the path to make sure the buckets don't overflow. So this is like a maintenance operation to make sure that the database, the data structure is well formed. Okay, and then I will, once I access something, I will choose a random new path and assign the element to a new path, but I will not disclose the path at that time. I just write it back to the root. Okay, so essentially every request touches a single path. And then in order to know which path it is, we are going to use a recursion data structure. So how does the recursion work? So imagine I want to read some logical address 01100. And you know, I have to first find out which path this element resides on. And in order to do that, I will put, like, imagine I have an array that records where every element is. And I put this index array in a smaller ORAM. And if you take this recursion idea, essentially, you'll have a sequence of trees. And your lookup will start from the smallest tree, which is constant in size, right? Because if it's constant in size, you can just read the whole tree. And then every time I will ask the question, you know, you can imagine every time I'm filling in one more bit in the address, and I will look up the path in the next tree. And then I know where to access in the next tree. And eventually, I will get to the final data tree, and then I will be able to get my element. So this is the recursion data structure when expanded. And a very simple idea for implementing the binary search tree is that we are going to overlap the recursion structure with the logical tree of the binary search tree. So on the left-hand side is the logical binary search tree, and on the right-hand side is the ORAM tree. Right. Here, I've coalesced all of the trees into a single tree. We can take all the recursion trees, coalesce them into a single tree. And essentially, these pointers there denote the recursion data structure. So like, for instance, once I look up the element 8, I immediately know which paths the two children rely on, reside on. I immediately know where the two children 3 and 10 are. And then because let's say I want to look up 1, I just have to look up 3 next. So what this does is like, essentially you get log squared cost per request, because essentially you are saving the recursion cost. And the naive approach I talked about has like log cubed cost, right? So this is like, by using this clever trick, we can save a log factor. And this idea generalizes to like a lot of other data structures, not just binary search tree. And actually it generalizes even further, because there's this recent paper by Pan, Heath, and Ren very recently, and they further generalize it into something called oblivious single access machine. So this paper, although they didn't make a compiler, actually it gives a very promising approach to defining a programming abstraction called smart pointers. And if you write the program using the smart pointer abstraction, we can compile it directly, to this non-recursive ORAM tree without going through the full ORAM transformation, and this can save you a log factor. Okay. So just to quickly summarize what I talked about, do I need an ORAM? I talked about this idea of using a compiler, right? So at the bottom, we have a suite of rich oblivious algorithm building blocks, not just ORAM, but also oblivious algorithms for many other primitives. And these primitives will be fed into, the compiler is aware of these rich primitives, and then the developer will supply some source code, and the compiler will do optimization and figure out the most efficient oblivious implementation. And this can both be a TE-based secure computer or an MPC-based secure computer. Both, when you compile to TE or MPC, you have to worry about obliviousness. Okay, and then so there are actually 2 aspects of the compiler. I only talked about the efficiency perspective today, but there's also another benefit of having such a compiler, because it can formally verify the obliviousness of the program at compile time. And this is something that we call memory trace obliviousness. Essentially, you can develop an information flow type system, and like normal information flow type system, make sure that data sent to low outputs do not contain secret data. Like, let's say if you are going to send some data to a public network channel, it better be public data and not secret data. And then memory trace oblivious type system extends the standard information flow type system. It also captures memory traces in the type system. So it makes sure that the memory traces do not depend on secret inputs. So even though I don't have time to go into details of this, I want you to keep in mind this is another great benefit of having such a compiler. It can defend against accidental programmer mistakes. Okay, so our just before I conclude, I want to quickly talk about our roadmap. Today we have already shipped a very fast oblivious key value store implementation. The open source is out there. You can try it out if you want. Our implementation is like an order of magnitude faster than Signals and about 100x faster than Matter's implementation. And we are also working on something called oblivious STL. This is ongoing. And this is the rich suite of oblivious building blocks that I've been talking about. And it's kind of like a prerequisite for eventually making a compiler like this. And we already have some primitives available, like sorting some oblivious data structures, maybe a few graph algorithms. But it still needs a lot more work. And eventually, at some point, when the oblivious STL is more ready, we can start working on building an optimizing compiler like the one I talked about. And then Quintus talked about the future roadmap, right? So besides trusted hardware, it would be very nice if some of the cryptographic primitives can also become practical. And then in our research at CMU, we are also looking at the performance of these cryptographic replacements of TE. Like, for instance, if we replace TE with two-party computation, you are looking at about 1,000 to 10,000x slowdown, but actually it's still reasonably fast. Like with plain TE, for a very large database like Ethereum or Signal scale database, every request takes 20 to 50 microseconds, which is very, very fast. And then with these crypto techniques like 2PC or private information retrieval, we are looking at about, on the order of tens or hundreds of milliseconds. But this is all measured on a single computer. So I think another promising direction besides developing a new secure computer is like we can develop hardware acceleration techniques for these cryptographic primitives, right? Because even this is just like on a single computer and there's limited parallelism. And a lot of these primitives are very amenable to parallelism, and we can further speed it up to get practical performance. Okay, thank you very much. The talk is based on several of my earlier papers, and I didn't have time to, refer to them. But if you are interested, you can go to my webpage and look at these papers in more detail, like for instance, about some of the type system details. Thank you.
Questions?
Thank you very much for the talk, Elaine. Oh, I have a question. So one thing you didn't touch on too much in the presentation is instructions. But instructions can also reveal information about the data that's being processed. I know that's part of the memory trace obliviousness definition. Could you elaborate a bit more on that? Yeah.
Yeah, so I had like one slide that quickly mentioned it. So this is one example. It's like, if you have a control branch dependent on secret data, you want to make sure that all branches exhibit the same memory trace and instruction trace. And this also secures against timing channel as well, because if both branches have the same instruction trace, and assuming the execution time of the instruction itself is not data dependent, then you make sure both branches take the same time to execute as well. Yes, Phil.
I had a similar original question and also about timing channels. So how do you actually handle that in the ORAM side of things? Does like the compiler like kind of pad things, or does it just assume that you're kind of invariant in like the number of memory accesses and the timing on?
Generally, there are usually three ways to defend against timing. One is that you can always develop, like, imagine you are building a secure processor, you can always access memory at fixed intervals. And even if there is no memory access, you will pretend you are making a memory access. So this is like naive approach number one. Approach number two is to use our compiler, which will take a look at your program, and it will essentially pad the program such that you always incur the worst case timing. It will always execute to the worst case for all possible inputs.
So that's even if you're not doing the like full oblivious, even if you're just doing the ORAM compiler, it does that?
The ORAM compiler does give you full oblivious.
Okay, cool.
But in some cases, this overhead is reasonable, because like, let's say the worst case and the common case are close. In some cases, if the worst case and the common case are far apart, like let's say you are doing database join, like the worst case can be quadratic and the common case is linear or quasi-linear. And in this case, we also have a line of work called differential obliviousness, and we can obfuscate the timing using differential privacy techniques. So you don't have to always incur the worst case overhead.
Okay, cool. I'll check that out. Thank you.
I think when maybe Afonso also interned at Flashbot, like Afonso is a co-founder of our company. He actually built, but this is still an preliminary thing. Like he built oblivious EVM instructions, which is kind of taking all the EVM instructions and trying to do this for every instruction, to make sure every instruction will execute in a data independent way, like the timing and the traces of the instruction itself will be data independent. So I'm happy to share the open source with you if you are interested.
So just to clarify, you're saying that the ORAM in your version of a compiler kind of protect this timing attack for the existing like ORAMs like have.
Yeah. I mean, ORAM itself is like it's just going to take every memory access and translate it to some random axes. So
yeah.
ORAM itself doesn't necessarily give you the timing channel protection, but the compiler does.
I see. And does it have a overhead in terms of like obfuscating the timings and for the tracings, or like is it insignificant?
It depends. I think in many cases, like for this EVM instruction at that level, it's like, sometimes you may incur twice the overhead, because you have to pad, like in this example, you have to pad the other branch, right? So maybe the runtime for that particular instruction will slow down by a factor of 2.
I
But I
see.
mean, of course, you have like your whole program. Not every instruction is like a secret branch. So like overall, how much overhead you incur, it depends on the application itself. And in some cases, as I said, if like this padding is incurring a large overhead, because essentially what this padding will do is like it will pad the execution of your program to always to the worst case. And in cases where this overhead is too large, we can use something called differential obliviousness, which relaxes the privacy notion to like differential privacy. And we actually have some papers on that too. Like for instance, we applied it to database join, which is a good example where the worst case can be quadratic. Let's say two-way join. The worst case can be quadratic, but the common case is usually linear or quasi-linear. And in these cases, we don't want to suffer from the worst case. So we use differential obliviousness.
And does the efficiency come from for even though you like preventing the timing attack?
Yeah. So the differential obliviousness basically adds noise to the running time. So it obfuscates the running time in a mathematically.
If you do the Gaussian distribution, like a worst case is like a more larger range, but like based on the average case.
Yeah, you can add noise by sampling from a Gaussian distribution. Yeah.
All right, let's thank our speaker. So that concludes our secure processors session. Because we're running a bit behind, we'll just take a quick 5-minute break, and then we'll be back here for the next session.
Cool. And how are things?
I think we're talking to the stream, by the way.
What?
Because your mic's on. Is it? Did you turn it on? Yeah. And I hear they're kind of sad. Well, the clear tax passed right now. It's a regulated market as well. So a lot of companies. Yes. Hey, everyone. If you could take your seats, we're going to get started with the next session. All right. Hey, everyone, we're going to get started with the next session. Hey, I'm sorry. Yeah, I'm sorry. Can we?
So just tell them during lunch to go to the faculty club. That's the best place to eat. It's the most reasonable and it's really nice setting.
Okay.
Okay.
Thank you.
Oh, sure. You know, I just, because there are a lot of them not around here, but that's, I'm sorry. Are you okay? All right. Take care. You're doing a good job, by the way.
Thank you. All right, thanks everyone. So we're going to get started with the next session. And our first speaker is Davide Krapis from the Ethereum Foundation.
Hello. Hi, everyone. I'll talk about this end game, EIP 5059, which is actually two EIPs. So I start with like the current state of resource pricing on Ethereum L1. Then I'll introduce something we call multidimensional metering. And then finally, I'll discuss this full multidimensional pricing with a few options we have in EIPs being drafted. Yeah. So the TLDR is that the current resource pricing on L1 is quite inefficient. So we have a naive price controller that does like some simple demand estimation block to block, like very naive. And then the individual resources that the EVM consumes, like compute, state access, state growth, memory, they're not even being metered. So there is no simple way of pricing multiple resources. And over the years, many solutions have been proposed, but then like the range is like from too academic and hard to implement. There was like a stream of papers on multidimensional fees, including like some of my own work with co-authors. Then like some were like too simple and inefficient. And also Vitalik had a couple of posts on things that are implementable in the EVM, but kind of like a UX nightmare. So yeah, we have some recent breakthrough here. So that's why I'm excited to like talk to this audience because definitely relevant to MEV. And yeah, so basically the two steps are like, first we improve metering, and then we can unify pricing. Yeah, so in Ethereum, there is like multiple resources, but we have one single price. And this is because like in effect, like the virtual machine tracks only one resource. Like all the resources are mapped to this common currency called gas that like most people that work on it know. And then basically the protocol only specifies conversion rates from like opcodes and different resources to this single one. And then the protocol today is metering this gas consumed by transaction, which is effectively used for two purposes. One is like controlling like that the block resource usage is within some admissible limit. And then the second one is like charging transactions for what they consume, and then manage congestion. Yeah, so the problem of resource management, basically like, why is this inefficient? So the properties we want is that we want to be within a safety limit for each block, but also we want to be efficient in the sense that we would like to utilize like most of the block capacity. So like in the picture, there is actually like the block limit depicted today in a space of like two resources, like data and compute. In reality, there is more. But just like to like convey the idea. So the constraint we have today is kind of similar to the green line, where like the block gas limit is like, first you aggregate all the resources and then you impose a limit. The blue line is the safety limit for data, and the purple line is the safety limit for compute. So ideally, we would like to pack blocks so that we can utilize like basically all the space in the square. So in reality, like we cannot do this today. So basically, the yellow area is like safe blocks that essentially we cannot build because the limits are like in a way too tight. Like the structure of limit does not allow us to go there. Yeah, so how can we improve from here? So first, we need to track the gas that is consumed by each resources. So if you assume that there is n resources that each opcode consumes, the reality is that most opcodes actually only consume compute. And there is maybe like 10 to 20% of opcodes that also consume other resources, but these are quite important. Yeah, so we meter all of these during execution, and then we define this new variable that we call gas meter in the block, that basically we take the max of gas consumed across resources. And then we can use this block's gas metering to like control the block capacity and also to update pricing. So essentially what we are doing at every block, we are updating the price just on the bottleneck resource. Yeah, one simple example is, yeah, like if you have data and compute, essentially like if one of them is at capacity, then you will increase the price. Otherwise, not. So essentially what this does is that, and both of them can be at capacity at the same time, right? So what this does essentially, it allows us to move from like this block limit model to this. Essentially we can be efficient, but while still respecting the safety limit for each resource. Yeah, this is only a first step. So essentially, in the simplest version of the proposal, we don't change price at all. So there is still like one single price for gas, and there is a minor change to the 1559 update rule. And this update is simple, like it's safe, and I would argue is valuable. Like there were like some simulation work being done where you can actually increase throughput by like 2x, or like in some extreme cases even 4x, without compromising too much, without compromising on safety. But it's still suboptimal. So like we are not pricing the resources right. Like if there is only one resource that is overutilized and all the others are slack, you are effectively like increase the gas price, so you increase the price for all resources. So we need a second step, basically. And what this second step should do, basically, like we would like to approximate the market clearing price for each resource separately, right? So that essentially, like each resource is priced optimally. And this is what the unified multidimensional pricing proposal is trying to do. I'll give a sketch here. So essentially, like what we want to do, like for multidimensional pricing, is like now the protocol is going to maintain k prices if there are k resources. Yeah, the cool thing is that actually, like we call unified because this can also include the blob market and the data market that today is something separate. So it's basically a unique framework that we can really like have this general framework where we price all resources in the same manner. Yeah, and then like the price for a resource is just update based on like supply-demand imbalance of that resource only. And in order to do this, we also need to change, we need to introduce a new transaction type. Yeah, so I guess it's like a little bit more involved on that side, but I think that's important because we still want to keep like decent UX. That's another constraint that we have in mind when designing this. Yeah, so essentially, like there is going to be this new transaction type where like there is two main changes. One is we go from fee per gas to aggregate fee. So what does this mean? Like if you look at the fields that are related to the fee market in the EIP 1559 transaction type, basically there is the max priority fee per gas and the max fee per gas. So today, as a user, you don't specify your willingness to pay for the entire transaction. You specify the willingness to pay for each unit of gas. And then the wallets already like kind of help with this, abstract this, but this is kind of a bit constraining when you try to do like multidimensional pricing. So the change here is just that in this new transaction type, then the user like just specifies like the max fee, the max total fee they want to pay, and then like the max priority fee they want to pay, which is also more intuitive, is how like potentially like many users already think about transactions today. And then the second change that you need to do is like how do you implement the gas limit for a transaction, not for a block. Here we're still like at the transaction level. So there is two options. One is like essentially you still meter like resources in different buckets, but like you map them to gas. So you keep one single gas limit over all resources. The second option is that actually the gas limit, if you have k resources, you specify k gas limit. Still, like the fee parameters is going to be unidimensional, but if you have 5 resources, you need to specify 5 gas limits. The wallets can also help with like kind of estimating this. And basically, like there is just a trade-off between UX and efficiency, or like let's say capital efficiency in this case. So if you do option 1, arguably you have a better UX on paper, I say, because like you only have 1 parameter instead of 5, like let's say in the case of 5 markets, 5 resources. But essentially, like when you compute whether like an account has enough balance to like pay for the transaction, you need to like do it in the worst case. So you need to take the resource with the highest price and use the gas limit, even if your transaction may not really use that resource. So it's kind of very inefficient because you need to have like more, in many cases, more balance than you need. So option 2, like if you have k resources, you need to add k-1 parameters, but it is more efficient because now like you can set the gas limit for each resource separately. If you're not planning to use any resource in that transaction, if there are some expensive resource you're not planning to use, you just put the gas limit to 0. Yeah, so I guess it's under debate which one of these model will go in, but both are feasible, and I argue that both provide like decent UX. Yeah, so maybe to summarize, like if we combine multidimensional metering and new transaction type, they give us like this endgame EIP 1559. we get to fully utilize the resource capacity of a block. We have efficient price updates for each resource, and we have no degradation in user experience. The cool thing is that, as I said before, we can unify like the fee markets across different resources, which today it's kind of a problem, like we've seen with the blob fee markets, and there is also some work from people in the room that like highlight the challenges. And so when we ship an improvement, it's an improvement to like all fee markets. And actually, like I just gave the sketch of the main ideas of the two proposals, but like there is much more detail, and like there is already a few improvements. Like in the unified one, there is like also reserve prices. And then it's easy to add new resources. As long as we can meter them, then we can add them to the framework. Yeah, for the next steps, both of these are like kind of in the stage of EIPs being drafted. So one is the multi-dimensional gas metering. You can look up this practical proposal on ETH Research. And then the other one, unified pricing, yeah, also in draft stage. Yeah, and that's all I have. Thank you.
All right, any questions?
The recording. Just curious, if you've got multidimensional fees and you're holding the pace of block production constant, you've always got a knapsack packing problem, which is where the efficiencies are coming in. Is there anyone at Ethereum looking at variable time? Using time to adjust the comparative efficiency with which the various silos contribute to the pace of block production, so you can get rid of the knapsack packing problem completely.
So like I don't agree that you always have this knapsack packing problem, because like most of the blocks are not full. So like for the blocks that are not full, you can just greedily pack them. Like you don't need to optimize anything. When you do have, yeah, it's a little bit more complicated. I would say like we are not looking at like changing like slot times in that context specifically. Other people are looking at like changing slot times for other reasons, but yeah, not in this context.
Any other questions?
So what do you think are like the worst case scenarios from like a super adversarial point of view that could be enabled by this change? Like, are there any like weird resource lockouts or like things like that? How do you reason about the space of new behaviors that we're introducing?
Yeah. So it's actually, that's a very good question. And I think like once we put forth these two proposals, that's most of the discussion that is going to happen. Like actually for each of them, there is like some edge case scenarios. Yeah, we looked into some of these. Also, we looked into how this plays out with like fossil and like the censorship resistant EIPs. Yeah, there is a bunch of cases considered in the EIPs. Maybe like.
Okay, yeah, I'll stay tuned for that discussion. Thanks.
Oh, I just got a simple question. So obviously, it's quite obvious why this is quite useful, but have you quantified how much better it is than the current system and whether it's actually worth doing? Because obviously it takes like a lot of time to implement and everyone else around it, especially if you modify how the transaction looks.
Yeah. So we just have like some simulation and some backtests that Maria, like one of the authors of the multidimensional metering did. So like on average, I think she was finding that you can increase by 200%, like capacity, like basically the number of transactions you can include while keeping the same limits. But then we were also talking to Marek at Nethermind. He thinks that like in the cases where like the blocks are full, like or I don't remember exactly like which kind of extreme load cases he was considering. He says that this can go up to like 300-400%, but of course that's like a small fraction of blocks. But yeah.
All right, let's thank Davide. Our next speaker is Sarish Wadwa, who is a researcher at Duke University.
Good morning, everyone. I am Sarish. Thanks for the invite to present our talk. Today, I'll be talking about OCIL, which is an inclusion list design tailored for rational parties. So let's get started with an example in which there is a transaction star. Alice wants to add some collateral to a position that she has on the blockchain. Otherwise, she would get censored. Otherwise, she can get liquidated. And the adversary does not want this transaction to go through because if this collateral is not added to the position, then Alice can get liquidated and while it will make a lot of profit. And therefore, the adversary wants to censor the transaction. Alice's transaction, along with many other transactions, go into the mempool of the for the block builder. The block builder now has choices from this transactions, whichever transactions it wants to include in the block, and it can definitely remove transactions intentionally, whichever transactions it wants to. So the block producer has the means to censor the transaction. And what makes it worse is that the block builder space is heavily centralized right now. 3 builders contribute to roughly 90% of the entire builder space. And that makes it easy for the adversary to bribe the block builders to exclude transactions. That is not the only reason for censorship. There can be more compliance reasons as well. But aside from that, this talk we'll be focusing more on the incentives side. So inclusion list has been touted as the solution for censorship resistance. The way it works is that inclusion list is a set of transactions that the block builder must include in the transaction in its slot. If the block does not contain a transaction, then it can make the block invalid and basically be forked out. This makes it really bad for the adversary because it cannot now easily bribe this builder. How bad does it get? That is actually dependent on the enforcement model of an inclusion list, which can be a conditional inclusion list, which is the regular inclusion lists that currently fossil, which, hey, today they went into a confirmed update for the next Ethereum update. So congrats to that. So in general, the transactions in inclusion list must appear if there is space in the block. If there is no space in the block, then the transactions can be excluded. Unconditional inclusion lists, however, do not allow that. Regardless of how many transactions there are in the block, the transactions that are included in the inclusion list must appear in the block. Otherwise, the block would be considered invalid. And OCIL design is based on an unconditional inclusion list enforcement scheme, and that's what we'll be focusing on. Okay, so we saw that if an inclusion list exists and the transaction makes it into the inclusion list, the builder cannot censor it easily. The adversary cannot bribe to censor it easily. But what stops the adversary from also bribing whoever is creating this inclusion list into excluding the transaction from the inclusion list in the first place? This inclusion list mechanism itself needs to be a censorship-resistant mechanism. And there have been talks about that, and that is exactly what OCIL is going to be working towards. The first point is who is going to be building this inclusion list? Should it be a single party, which can be, again, bribed? It is easy to reach. or should it be multiple parties, making it worse for the adversary? Should it be builders who are a centralized entity, or should it be validators who are relatively known to be a decentralized set of parties? And these are all rhetorical questions. Obviously, we want multiple validators. We want a multi-validator inclusion list protocol. And that is exactly what COMIS introduced, and it laid the groundwork for multi-validator inclusion list protocols. In a multi-validator inclusion list protocol, basically multiple validators try to collaboratively form the inclusion list. They select transactions from the mempool, and then they send it to an aggregation phase. The aggregation phase basically computes a union of all the transactions or all the inputs that the validators have given, and that forms the inclusion list. So how does this aggregation and input selection work? But before I talk more about OCL and how it answers these questions about how these inputs are selected and how the transactions are aggregated, we'll first formalize what the design goals for our protocols are. The first and foremost, the goal is that if all parties are rational, they should be incentivized to follow the protocol. In other words, there is some sort of an equilibrium that is established when parties are choosing their transactions, broadcasting, and whatever the aggregation does. Secondly, if some party is unable to participate because it crashes, let's say, then we should still be able to proceed forward and not and the inclusion list protocol should not stop. And lastly, it should make it as hard as possible for the adversary to bribe the parties, and which would make it robust against censorship. Before going to OCL, we will talk about Fossil, which again is the current design that is going to be incorporated. So Fossil produces a very simplistic design in which all validators select their inputs and select the entire mempool, so an entire selection of mempool they have. Any valid transaction, they just contribute that to their input. They term this input as a local inclusion list, but we call it an input list because there are some differences in both of those terminologies. But for the context of the talk, I'll call it the input list. And then they send it to directly the builder or the proposer, who will aggregate them, all of these inputs by themselves, and produce this inclusion list to constrain themselves. They are, however, required to do so honestly because the attesters are verifying that this inclusion list is actually correctly formed. They confirm that the union of all inputs have been taken and the transactions in inclusion list are given the right space. However, what we see is that there is no current fee structure for Fossil. What this implies is that rational parties have no incentives. There is no fees that they are receiving to behave honestly. And they also rely on the trust of a majority of attesters, as well as relying on these attesters to actively scour through the mempool to basically compute the union on their own and participate in all the timings and computations that Fossil introduces. To their credit, if a single party is honest amongst the validators that they have, and the attesters are doing this work, then Fossil has really strong censorship resistance guarantees. Okay, so now moving on to our protocol, which is OCL. OCL is a design, a multi-validator inclusion list design, in which parties are selecting inputs, and I'll explain how these selections take place in the first place. And then these inputs are broadcast to the next phase, which is the aggregation phase. In the aggregation phase, each party computes a bid, which is basically the list of all the inputs that have previously been seen. Based on whoever has this highest bid, the builder has to basically compute a reverse auction, and whichever is the highest bid would constrain the builder. I'll go into it phase by phase, but before that, this design of ours allows OCL to, in fact, achieve censorship resistance, which is quadratically increasing in the fees that a transaction pays until the transaction, and it caps at around the validator time, number of validator times the fee paid. So until a scaling factor of number of validators is achieved, we have a quadratic increase in the bribe tolerated. Okay, so going into more details, into phase-by-phase selection, how do we first know which validators are selecting which transactions? Do we even need such a suggestion or some allocation problem in the first place? Well, if we do not give them what transactions they should choose, they'll naturally just select transactions based on a mixed Nash equilibrium, which is probabilistically choosing each transaction in order to maximize their utility in the expectation. However, this does leave utility that is uncollected. Basically, the adversary can come and tell the parties which transactions to include. Even if it is not trying to censor, it can increase the utility of each of these validators. More details on this can be found in a paper. Yeah. So what we suggest in OCL is to use a greedy selection round-robin based allocation for input selection. This achieves a correlated equilibrium where no party has actually any incentives to deviate from the transactions that have been suggested to it. The way it works is a greedy selection. We see that star is giving the highest utility to each party, so star is chosen. Then we update the utility that star is providing because now already one party or one instance of star has been chosen. And we repeat the greedy selection over and over again until we have the desired number of transactions or instances of transactions selected. Then, based on the final effective utility of each of these transactions, we sort and allocate them in a round-robin way to all the validators. What this ensures is that the utility received by each validator is as high as possible, and this achieves correlated equilibrium in which no party has incentives to deviate from the suggestion of algorithm. We can see that the red party over here is not suggested to include star, which is the highest paying effective transaction. But if it does select star and deviates from the protocol, it would only receive 10 utility, which is less than or equal to what it has already been allocated. So how does censorship resistance work in this space? Well, if the adversary wants to stop star from getting into the inclusion list, it must bribe both the blue and the green parties to exclude this transaction. And it must bribe the full fee, which is 30 to both of these. And this is basically based on the multiplicity gadget assumptions, where if the fee paid is, let's say, the bribe paid is, let's say, 20, which is higher than the effective utility, then still probabilistically some party may deviate and choose to select the transaction. moving on to the next phase, we have the aggregation phase, in which after the parties have selected their inputs, they'll broadcast that for the aggregation phase. And each party will compute a bid, which is, as I explained earlier, the list of inputs that it has received. The bid value, in fact, would be the number of lists that it receives and has computed in its bid. And whatever the highest bid is, will, and let's say it receives a utility of 30 in this case. So two things to note here. A party can choose or crash and not broadcast their selection in the first phase. This would mean that other parties now do not have this input to select, but the protocol still moves on. If the party crashes, we don't have any troubles. If this party again returns in the aggregation phase, we can still accept its bid in that phase and move on. However, if it does broadcast, there is no incentive for either of the parties, the blue or green, to drop this input from their bid, because it just reduces their bid and reduces the probability of winning the auction. So what exactly is preventing this red party from not broadcasting its input in the first place? Well, there is nothing in the current form of this aggregation. It can just choose not to broadcast, which is bad. To prevent this, what we add is the first thing we observe is that if they don't win, they will lose the fee as well, if for whatever reason they don't win. So we bias some parties won't win by adding another random number to the bid. So each party would compute a random number, a random bias that would add to their bid, and whichever party has the highest bid after computing this sum will be selected as the winner. Let's say the red party generates a bias of only 0.1, where the bias was in the range of 0 to 2, then the party is now not going to win, even though it withheld its input list from everyone else. So basically, all in all, the VRF value should be small enough that it does not impact the selection of inputs in the first place, because if we can just do a VRF which is infinitely large, then it doesn't matter if you're including inputs or not. So we don't want that to happen. We don't want it to be small enough that all parties now are incentivized to withhold their inputs. And so we come up with a number, a parameterization, which is square root times the number of parties in the system, is what we would want the bias to be, maximum bias to be. So based on this, if red party is still losing, then it might as well broadcast in order to save the 21 that it was receiving as fees from the inclusion list. And based on this bias, what we observe is that as long as a party generates a bias of less than 1, maximum bias minus 1, then it is always incentivized to broadcast. In this case, if the bias was only in the range of 0 to 2, every party who generates a bias value of less than 1 will be incentivized to broadcast. Whereas the parties within the range of 1 to 2 will follow some sort of a mixed Nash equilibrium, which is again shown in the paper. So basically, this means that every party would broadcast. The green party can choose not to, but if it does not, it doesn't impact the system. And as long as most parties broadcast, we achieve the censorship resistance properties that we were looking for in this phase. In fact, if the adversary now wants to bribe in this phase, it would have to bribe, and if it wants to remove star, it would have to remove 2 inputs from each of these parties. So it will have to bribe all 3 of these parties to remove the 2 instances of star that were being included. that is pretty bad in of itself. But let's say we use a world which is easier, and the adversary wants to only delete this triangle from the inclusion list and not star, which had 2 instances. In this case, again, the adversary would have to bribe those parties with a high enough VRF value that if it removes those, even if those parties reduce the bid, they're still higher than others. But that VRF value that I'm saying is known is actually not known to the adversary, and basically the adversary now has to bribe every party still in the system, and the censorship resistance properties remain the same, even as long as if there is one instance of a transaction in any of the inputs. And the value of this bribe must be greater than the utility that we are providing for winning this auction phase, which is 30 to each parties. In fact, the censorship resistance value in this phase is much higher than what we achieve in phase 1, which is where the quadratic increase and then the linear capping comes from. All in all, OCIL, our protocol, has 3 properties that it achieves. The first is that it achieves an input selection equilibrium in which no party is incentivized to deviate from the selection of transactions. It achieves crash fault tolerance in which the protocol remains live with even up to theta crashes, and which can be controlled by the adversary or not. And lastly, it increases the cost to censor the transactions to really high in all phases, not the theoretically maximum yet. The theoretical maximum would be a linear scaling with respect to with a scaling factor of number of validators, but a high enough. So here's a link to our paper, and you can contact me at sarish@wadvad.edu. If you scan this, you will get the text as well. So yeah, contact me for any questions on any further. Yeah, thank you, and yeah.
All right, any questions?
Great talk. Great talk. I guess I got one question to do with the utility. So how do you envision, like, what do you envision the utility to be? Will that be, for example, like in an Ethereum transaction, you have a tip that's paid to the validator? Or will it be like a special field where if I really do want this to be censored, I'm willing to put like $20 in there, $50, and that would be the utility these guys would get like a separate censorship resistant fee. How are you envisioning this?
Yes, so OCIL has 2 utilities. The first phase has the fee that I was talking about, and that is a censorship resistant fee. This can be derived from the tip that the party is giving, or it can be chosen like by the user in a very separate manner, and this can be an entirely separate fee structure. The second utility comes from the auction winning mechanism, where that is a protocol generated reward. And both of these are some things that in future work we should look to minimize if that is possible.
Thank you for the talk. So first of all, I learned that it's not called OCIL, but OCIL, so that's good to know. The second thing is in the input selection part, is it going to be run on like a single server? So then like one, and then it will like start at some certain point in the slot phase, which then some could have an incentive to like co-locate with it, or would there be any kind of manipulation for an input list maker to like make sure he gets the high value transactions?
So yeah, so one thing I forgot to mention over here was that the input selection algorithm, while I described that as an interactive phase where each party is getting allocated transactions, it's not an online algorithm. Every party has their own mempool. We assume that is common across all parties, and they're all simulating these by themselves. So there is no actual on-chain input selection mechanism that will go on. This is just a suggestion to how validators should behave while picking their inputs for OCL. So yeah, to your question, there is no way to manipulate the input selection phase in an adversarial way because yeah, those will be locally computed by the inclusion list, the validators, and not. There is no other. Yeah.
Okay, thank you.
So two questions. First is I'm a bit puzzled about how the aggregation works. Like just like who is running it, or like just like what machine is actually doing it. So I wonder whether there's some point of failure in this aggregation part. And second, just another just about the selection. You said it's a correlated equilibrium. Is this equilibrium of this selection game separately, or it's kind of like you consider a overall dynamic game thinking about the later steps? Yeah, two questions.
Yeah. So to answer the second question, because it's simple, yes, we do consider it as a dynamic game in which the second phase has already influenced the first phase. For the first question, so there is no single aggregator that is present. All validators that were involved in making the inclusion list or input selection in the first place are all parties that will be participating to aggregate. The every party is computing this bid in OCL and then sending it to the block producer. The block producer must choose a bid which is greater than at least n minus theta other values, n minus theta minus 1 bids, and it must show proof that it is greater than n minus theta minus 1. Because theta is the crashes that our protocol follows, this proof is always existent in our scheme. Yeah. So there is no way of introducing another fault in the scheme.
All right, let's thank Sarisht. So that concludes our morning session. We'll be back here at 1. There are sandwiches set up in the lobby here, and then there's a courtyard outside where we plan to eat. All right, thanks everyone. If you could take your seats, we'll get started. Okay, welcome to the third session of the day. Our first speaker will be Leo Bahenbach from ETH Zurich.
Yes, so thank you for the introduction and thank you for inviting us to give the talk here. So I will be talking about optimistic MEV in Ethereum layer 2s and as to why this just might be the answer, why their block space is always in demand. So my name is Lioba, and this is joint work with Ozan, Jan, and Roger. And Jan is actually also in the audience today, so if you have any questions after the talk, you can also ask him. We're all from ETH Zurich. In this space, this sometimes leads to confusion. This is ETH, the university, not ETH, the cryptocurrency. But now Jan is also joining the Ethereum Foundation, which just might really add to the confusion even more. So with that, let's look at what I'm going to be talking about today. So now we're talking about Ethereum, the blockchain, and Ethereum in the past, it had problems with scalability. So high demand on the Ethereum layer 1 just led to there being an increase in transaction fees and congestion on the network. So instead of just making the layer 1 bigger, what Ethereum decided to do is to also adopt a roll-up-centric roadmap. What this means is that we move transaction execution, at least for a good proportion of transactions, off-chain to layer 2s. And these layer 2s, they then post their data to the layer 1. So the layer 1 is essentially a settlement layer for the layer 2. And then it is thereby securing these layer 2 chains. Now, transactions on the layer 2s were already a lot cheaper than on the layer 1. But last year, then the Denkun upgrade, as part of that in EIP 4844, blobs were introduced, which made layer 2 transaction fees even lower. These layer 2s, they're really gaining traction. They're no longer experimental. In the first quarter of this year, actually, around 50% of the DEX volume in the Ethereum ecosystem has been on these layer 2s. And also, they are securing more than $40 billion in value. But despite this, we really do not understand much about how this MEV landscape differs on the Ethereum layer 2s as opposed to the Ethereum layer 1. So I want to start by pointing at some differences between the two that might then also lead to their differences in the MEV landscape. So the first one is fees. On the layer 1, we have, at least in comparison, high fees, while layer 2 fees are quite low, and they've gotten even lower with blobs being introduced. Then block times. In comparison, the layer 1 block times are currently quite long. There's a block only every 12 seconds, while it's 2 seconds on the OP stack, so Optimism and Base, and around a quarter of the second on Arbitrum. Now, the last difference I want to point out that might be relevant for how MEV might behave differently in these two ecosystems is that on the layer 1, the way transactions are ordered, it is done by builders essentially. So most blocks on the layer 1, they're built through a builder auction where builders are optimizing blocks. So they're reordering transactions to build high value blocks, so high MEV blocks. And on the L2s, this is not quite what is happening. There we have sequences. On Arbitrum, this is first come, first serve. So transactions are ordered just in the order that they came in. This was at least until the introduction of Time Boost, which gives some transactions priority, but our data largely predates the introduction of Time Boost. Now on the two OP stack rollups, we have gas auctions. So the transactions in a block are just ordered by how much they're willing to pay, essentially. So these are some of the differences between the layer 2s and the layer 1. And what we found is that these differences really fundamentally change the MEV landscape on them. And let's very quickly say what MEV is, even though I'm sure this audience doesn't need it. But it is essentially the value that you can extract through including, excluding, and reordering transactions in a block. Now, common examples that we've in the past studied on the layer 1 are sandwich attacks, cyclic arbitrage, sex-dex arbitrage, or liquidations. But now the thing that I want to get at here is that on the layer 1, these MEV opportunities, they're generally computed off-chain. So you compute some profitable sandwich attack, cyclic arbitrage, then you put your bundle and you include it generally, at least through the PBS auction these days, and then it will only make it on-chain if it is profitable, essentially. So there is a lot of precision and pre-planning involved in MEV on the layer 1, at least in general. So to show it more as an analogy, let's assume that we have a really big fish here. All fishers, also the ones in the boat, they found this opportunity. But then one of them essentially buys the right to go into the ocean with the harpoon, and it's a special harpoon that just is able to kill every fish it sees, and thereby sort of get this big profit it has. So this is traditional MEV as we know it from the layer 1. And then when we move to the layer 2, this is maybe more what it looks like. So we have all these fishers that are just putting in their fishing rods without really knowing whether there are any fish. There are some tiny fish around. Most of them will really not catch any fish, but they don't care because it's so cheap to just sit there and keep fishing, even though the chance of them actually getting a fish is quite low. So this analogy was supposed to hint at the difference between traditional MEV on the layer 1, which is very precise and of high value, and optimistic MEV on the layer 2, which almost has this spam-like feature. So to put it a bit more formally, by optimistic MEV, what we mean in this work are essentially strategies where the profitability of a transaction is searched for and decided on during the on-chain execution. And this then leads to many speculative transactions that often end up executing without actually executing any trade or executing upon any MEV. Now, in this work, where we study optimistic MEV, we in particular focus only on cyclic arbitrage. The reason why we do this is that with cyclic arbitrage, you can search for the entire opportunity in a single transaction on-chain and then also execute it in a single transaction on-chain. So essentially what this means is that you can discover the profitability during execution time, which isn't the case generally for the other types of MEV. So now let's look again at how traditional MEV looks. Now, in particular, we're looking at cyclic arbitrage here. So this is just one cyclic arbitrage that was executed on the Ethereum layer 1. And what you essentially see here is that we have this bot here that makes a profit in wrapped ETH by also going through another token. But the crucial thing here is if we look at the call data, which I'm showing up top, the pools are specified, the amounts of the trades are specified. It's all in the transaction call data already. This was pre-executed. This transaction didn't land the chain and was first wondering what it should do. It had exact directions on what to do. Now, let's look at how a cyclic arbitrage transaction looks on the layer 2s, which is one that is in this optimistic MEV world. So first, it looks quite similar, right? We also have a cyclic arbitrage bot here that has the starts with wrapped ETH and then makes a profit in wrapped ETH, just goes through one additional pool essentially. But the difference really is that if we look at the call data now, it is completely non-informative. And this suggests that this wasn't pre-computed. The transaction was actually searching for these opportunities on-chain. So that logic was in the smart contract and the computation was happening on-chain with this optimistic MEV as opposed to off-chain, which we saw with the traditional MEV. Now, the question we were wondering once we saw that there were these transactions which seemed to be just determining the profitability on-chain, so optimistic MEV, what does it really look like on the layer 2s? How big of a thing is it? And for that, we first needed to collect data. So we collected raw blockchain transaction data from the Ethereum layer 1 to have something to compare against. And then from 3 layer 2s, which are Arbitrum, Base, and Optimism. And these are just the biggest 3 layer 2s in terms of volume and total value locked. Then what we did next is on all of these 4 chains, we detected cyclic arbitrage contracts. So we went out and searched for contracts that perform cyclic arbitrages, so bots essentially that do cyclic arbitrages. And then most importantly, we then, with this, were able to classify transactions. So for each transaction, we classify it along 3 dimensions. The first is the purpose. So is the transaction a cyclic arb transaction? That means it was submitted by one of these cyclic arbitrage transactions or not, then it's other. Now, the second dimension is the DEX involvement. And there we differentiate between 3 different things. The first is if the transaction actually executed a swap on a DEX, then we call it trade. The second category, interaction, that is transactions that we see, they're reading the DEX state, but we do not see them actually ever executing a trade. So they are interacting with a DEX, but not doing a trade. That is the interaction category. And then we also have residual. These are just the transactions that do not even interact with a trade. And now the third dimension that we label is execution outcome. That just means whether the transaction successfully executed or whether the transaction reverted. Okay. So as I was saying previously, one of the defining features of this optimistic MEV is really that it is quite speculative. When the transactions are being submitted to the chain, you do not even know what the opportunity is, neither do you know whether you will actually be the one capturing the opportunity if it were to exist. So what I'm showing on the slide now is that as a result of that, the outcome of transactions from these cyclic arbitrage bots, they are radically different across the chains. So for each of the 4 chains we looked at, what I'm showing on the slide is essentially for those transactions that are being submitted by these cyclic arbitrage bots, how many of them actually perform a trade? Presumably, this is a successful cyclic arbitrage. Those are shown in red. Then in orange, I'm showing those that actually interact with a DEX. So they read the state, presumably that computing whether anything profitable exists. But then in orange, essentially, it's those that do not actually revert. They just eventually stop executing. And in yellow, it's the same, but these are the transactions that then stop executing. And what we can see here is that on the 2 OP stack rollups, so base and optimum, less than 12% of the transactions from these cyclic arbitrage bots, they actually succeed in executing a trade. So more than 98% of them, they just do not do anything. They do some on-chain computation, but nothing really comes out of it. And this is extremely different to Ethereum, where more than 95% of transactions from these cyclic arbitrage bots actually perform a trade. Now on Arbitrum, it sits somewhere in the middle between these OP stack rollups and Ethereum. There we have a pretty equal 50-50 split. With 50% of them, they actually execute a trade, and then the remaining, they decide to not execute a trade because, well, they couldn't find an opportunity, for example. So this really shows the difference that this behavior in optimistic MEV versus traditional MEV does to the outcome of transactions. What we then wanted to do next is we wanted to understand what is the scale of this. And for that, what I will be showing you is the daily gas usage on these 4 chains. So for now, what you can see in here is essentially all the gas usage by transactions that are not from cyclic arbitrage bots. So this is essentially the part that we didn't really look at too much. And now the first thing that I will add in is the cyclic arbitrage trade proportion. So now this is the gas usage by cyclic arbitrage bots that actually do perform a trade. And really, when we're looking at this, we don't see radical differences between these chains yet. The proportion of cyclic arbitrage trade category is actually relatively similar across them all. Note that Arbitrum just looks a bit different because of the scale, but overall, it is all quite similar. Where we do see the radical difference now is when we include the cyclic arbitrage interaction category. So that is what is shown in orange now. And essentially, these are the transactions from cyclic arbitrage bots. They presumably want to perform a cyclic arbitrage, but they just read state and eventually they stop without ever executing upon any opportunity. And here you really see the radical difference between especially the OP stack rollups and the Ethereum layer 1. Now, in total, in the first quarter of this year, the optimistic MEV, so the cyclic arbitrage bots, in total, they accounted for 55% of gas on optimism and 51% on base. On Arbitrum, it was 7%. But I think the more important part here is that on base and optimism, actually around 50% of the total gas usage is then the cyclic arbitrage interaction category. So this is just pure on-chain searching or on-chain computation where no trade actually executes. This is something that to some extent wouldn't even need to be on the chain. But still, on these two OP stack rollups, it is currently accounting for around 50% of the total gas usage. And what you can also see is that in this plot we're showing with the dashed black line, the block, the gas target as it's evolving. And you really see that this optimistic MEV from these cyclic arbitrage bots, it is filling up the blocks. There seems to be almost an unlimited demand for block space from these low-cost speculative types of transaction, especially on base, and on optimism this has recently also been the case where it's just filling up the blocks essentially. Now we know that these bots on the two OP stack rollups, they are consuming around 50% of the gas. What we then also wanted to see, are they paying around 50% of the fees? For that, what we did is we compared the average gas price on base and optimism for the cyclic arbitrage bots that's shown in orange, and then for the others, we're showing it in blue. And what you can see here is that they are underpaying. So they're paying 3.5 to 6 times less than others. So all the other transactions on average on the two OP stack rollups. Additionally, this is what I was pointing at previously already. What we find is that once we were adding additional block capacity to especially the two OP stack rollups after the Dencun hard fork, this was mostly consumed by these cyclic arbitrage optimistic MEV transactions, and it wasn't being used by ordinary users. So they weren't the ones that were profiting from this new block capacity. So knowing that this is quite a significant phenomenon on the layer 2s, we also wanted to understand a bit more as to what drives this. And for that, we did a regression analysis, and essentially we were able to identify 3 clear drivers of both optimistic MEV activity, as well as those transactions that are actually successful. So the first one is the Ethereum price volatility. This intuitively makes sense because when prices are volatile, they are moving more rapidly. That means that price differences are just more likely to also occur with a higher frequency. And that would then mean that for one, these optimistic MEV transactions might be more likely to be successful, but also that they would probably spam the chain even more, submit more transactions to take advantage of these fleeting opportunities. Then the other thing that we find to be driving optimistic MEV activity is retail trading volume. The reason for this is that retail trading volume, it is not as optimized. So it tends to potentially be more likely to leave some price differences after it executed if like a non-optimized trade is being executed. And what that then means is, again, we have more price differences where the optimistic MEV comes in. And the final factor we found, it is quite related to the previous one. This is a lower DEX aggregator usage. So amongst the retail volume, sort of what proportion of them is using DEX aggregators, which would mean that they're still relatively optimized, and what proportion is just submitting, well, as they are without an aggregator, which then would again mean that they are more likely to leave these price differences, which is good for optimistic, which then drives this optimistic MEV activity. Okay, so what I want to conclude with is to talk a bit about what the impact of optimistic MEV is on the ecosystem. I think the first thing to note is that it has a significant impact. I think this is quite clear, given that it really is dominating gas usage. It's more than half of the gas usage on base and optimism, and it is really filling up the block space with these low-value probes. which are doing on-chain computation, but end up not even executing anything. But then now what this means is that we are storing all these transactions on-chain, which to some extent, they never needed to be on-chain. But the result of that is that it increases node storage demands, it increases the bandwidth load on the network, and this is then potentially also a centralizing driver in this ecosystem because there will be less players around that have the required hardware to follow these chains. And then finally, this is a very different type of MEV than what we're used to. It is of low value, it's very speculative, and this also means that it might pose some challenges to mitigate, that we cannot just plug in sort of those mitigations that we're used to from the layer 1. For example, for auctions, I would presume if they were implemented, these optimistic MEV bots might just really spam the auction with bids, which will make it harder sort of to actually build blocks. And the auctions also need to be run in shorter periods of time, given the shorter block intervals on the layer 2s. So with that, I just want to conclude by saying that optimistic MEV, it is here. It is taking up 50% of gas usage on the 2 OP stack rollups. And yeah, let's see what you think about it.
Great. Questions?
So this is a question/comment. I think that another really big reason for the difference in like unsuccessful optimistic MEV between optimism base and Arbitrum would be that Arbitrum actually gossips pending pending transactions via on their sequencer via WebSocket, whereas base and optimism don't do that. So it's much less profitable to spam or like necessary to spam the Arbitrum sequencer with optimistic MEV swaps because you know that they won't hit if there hasn't been anything previously in that block, and you can just like wait, or you know how many swaps are already in the block and like what they're likely to be, which I think it's kind of interesting because it's kind of contrary to like what a lot of people say about how we should be minimizing the effects of spam on like L2s. And a lot of times people like bring up that we should be getting rid of FIFO and stuff like that, but Arbitrum is very FIFO focused. So maybe like FIFO plus like public pending trades is actually a really good way to lower spam rather than having like a stronger privacy guarantee, but also having FIFO. So yeah, just kind of I wonder what you think of just that like line of reasoning.
No, that makes sense. I think we also talk about it a bit in the paper where I have the QR code here, that essentially Arbitrum being FIFO also means that you do not know potentially sort of exactly, or it is a bit more difficult for you to then go exactly where you want in the block versus then with the priority gas auctions on the OP stack rollups, what you would do, or what we see them doing, is they just bid quite lowly. They're at the end of the block. They know there's something in front of them. They don't know what exactly it is, but they want to be the first ones to take advantage sort of after it happened. And essentially this behavior isn't quite the same on Arbitrum. Like we do not know exactly what is the difference between the very different behavior on Arbitrum and the OP stack rollups. I think there's many differences, and they all end up adding up with each other to create this quite different picture where Arbitrum almost looks more like the layer 1.
Thanks, Lila. Can I ask something for the orange and the yellow transactions, which are some of those, like both of them interact, but they don't trade? One type of them reverts and the other doesn't. Do you know why one type reverts and the other doesn't, or no?
I think the reason for this, I cannot tell you exactly why. I can just tell you those on Arbitrum, we have quite a significant proportion that reverts, while on the other base and optimism, almost none of them revert. On Arbitrum, these are actually, I would call them a bit less optimistic MEV type transactions. For these bots that are doing them, still around 50% fail, which is still quite a bit. but they sort of fail quickly. Like they don't spend all this money on on-chain computation, which on Arbitrum tends to be also more expensive than on the two other rollups. And then they decide to just quickly fail and revert. So maybe they have like one or two possible things they want to check. They check those, and then they are like, okay. Versus on the two OP stack rollups, they just seem to be searching, and eventually they stop. Exactly what is the reason for this? We don't know though.
I just found interesting that some stop without reverting. I guess that was like.
Yeah, to us, this was also surprising. I think this is how we first realized that this was going on, because we were seeing all these transactions, I believe back then on Optimism, that were using so much gas and doing nothing and not even reverting. But then, yeah, I guess there's no need for them to revert. I presume that is the reason.
And then also a second question for the average price paid that you showed later. Is this priority fees or
No,
the sum?
This is the total fee they're paying.
Mm-hmm.
So this is everything that they're being.
Okay, thanks.
And we'll take one more and then I'll ask the rest for coffee break.
Yeah, I mean, maybe one thing I'll comment on the Arbitrum one is just everyone pays the same fee. So you can't have like differing fees between transactions. But I have two questions. The first is, did you work out the total number of addresses doing this? For example, is it like a few bots or is there like 1,000 bots? Like, is it like I assume they're using like an address per bot probably. Then the second question is, did you compute the total profit they were making and then compare it to the fees they were paying? Because I'd assume if you're spamming half the blocks, and you're paying fees for this, I assume, then their profit must be through the roof if you can just afford to like waste all this block space.
Yes. So to your first question, yes, that we looked at, and it's very few that are sort of dominating the gas usage. I cannot tell you exactly what it was, but I believe on two of them, much more than 50% was by 10, versus on one of them, it wasn't quite as centralized. We also actually found that the same contracts were being reused on multiple chains. So on the OP stack chains, it was sort of the same contracts that were being reused, even on Unichain, which in theory has revert protection. But even then, they were just stopping execution without reverting because they were reusing the same contracts they were running otherwise. In regards to profit, no, this we didn't look at. I believe their profit is not through the roof, as you put it, but I believe they are profiting, otherwise they wouldn't be doing it. But the transactions they're paying also aren't adding up too much. So, I believe they are for sure profiting. They wouldn't be doing it otherwise, but we didn't look into it because there's so many weird tokens involved in it. Sorry? Oh. I can tell you in the coffee break. I think now it's.
All right, let's thank Lioba. What's your last name?
Sorry?
How do I pronounce your last name?
Mama Geishu. Mama Geishu, same way. But I can do it.
Okay. Standing right behind the podium and confused, but if you move them, you still get a recording.
So it's on.
Yeah.
Do you convert?
To a website.
Sorry about that.
Yeah.
No, but yeah, just not first month.
Our next speaker, Akaki, is a researcher at Off-Chain Labs.
Hello, everyone. Welcome to the presentation, and thank you for organizing this nice event. Can you hear? So is it better now? Now better? So can you hear me? I can be louder. Okay. So Off-Chain Labs is a company that originally built Arbitrum. And I will free ride on Lioba's presentation that introduced what are rollups. So Arbitrum, up to 3 months ago, had the first come, first served transaction ordering policy. And that was changed to time boost, because in first come, first serve, searchers, so arbitrary searchers are spending resources on improving the latency. Oh, okay, so it's, see the slides are, yeah, slides are modified, but yeah, so bullet points are broken. Yeah, it's really broken.
Okay, we're going to take a coffee break early while we fix an unfortunate slide conversion that we did, not him, and we will come back in 10 minutes.
Yes, almost all bullet points. Yeah.
Can we do video?
No problem.
We thought this would make it simpler. It did not.
I was myself confused, so it wouldn't work.
Yeah, I guess the question is like, does it deter other volume? And to answer that, it's probably not. Oh, yeah.
Yes.
They all look okay now?
Yes, yes. Yeah, I'll check all pages, but yes. Yeah, I was thinking that PDF never screws up, but apparently it does.
I think so. The issue here was that we thought we could let everyone present from their own computers.
Yes.
And so I hadn't collected them in a unified format. And then the AV person came this morning early, and we were working together with him, and he couldn't figure out how to get the camera view right if we use individual laptops. So then we have to use OBS on here. And so then I think it was the like.
I checked all pages I wrote.
Yeah. So it was last minute scramble issue, not a PDF issue. Yeah. I think we needed like a authentication. We should just try to do that before.
And the centralized sequencers usually have one service.
All right.
I thought you might be dialing in remotely.
Oh. Oh. Yes. Yeah. Okay. Who is it?
Literally just shooting.
I'll be, yes. Hey, you? Set me up, yes. We talk, and we agreed to talk again after this.
So I.
Yes, how are you? Do they know?
Yeah.
That's why they're sad.
Season sad already.
Maybe it's for another reason, but why? Pantera is where this Matt Stevenson is.
He left him, so I took his job.
So you'll be overlooking us. Pantera has invested in.
Delegator.
Uh-huh.
In and out, but yeah.
Oh.
Yeah.
It's also invested in Blockchain Labs.
I'm excited to work.
I was actually Our slide is stuck on the first. Uh-huh.
Yeah, Vanessa is trying to just do the slides. Can you go back to the first? Oh,
Are people watching actually?
it's like it's going up and down. Like some people seem like they took a break because we took a break in content, but yeah, it seems like there are like 10 or so people at any given time. And the stream also will be coming up.
So videos you will make separately then.
Yes, the videos are we will cut down into individual talks.
So now I pretend it's from the beginning. Now I'll pretend it's from the beginning, but I didn't do much, so it's easy.
Okay.
Like
I won't get emotional.
And if you advance the slide, sorry, do you want to just check it is? What? There's a line. Yes, it works. Okay. All right, thanks everyone. We're going to get started again if you'll take your seats. All right, thank you. And sorry, that was Akaki gave us unbreakable PDF slides and we converted them to online format and somehow broke them. So apologies to everyone. But I'd like to introduce our speaker again. So this is Akaki. He's a researcher at Off-Chain Labs.
Hello, everyone. Welcome to the presentation. Today I will talk about Time Boost, which is auctioning time advantage in first come, first serve. So motivation is that in first come, first serve transaction ordering policy, the arbitrage searchers spend a lot of resources on improving the latency, which leads to latency wars. And this expenditure is completely lost from the protocol perspective or the application's perspective. Also, there are too many reverted transactions because the transactions are in the private mempool, they are not observable. So searchers are trying probabilistically to background them, and most of them are reverted or failed. And also, last, it's a source of revenue to the Arbitrum DAO. So now let me describe what is time boost exactly. So it's still first come, first serve transaction ordering policy, except there is one player who has 200 millisecond advantage over others. And this advantage for that player lasts for 1 minute. And the advantage on the implementation level is achieved by delaying all transactions of other users by 200 milliseconds. So you can imagine there are these two first come, first serve queues, one from regular users and one from time boosted user, and they are getting merged. Except the first one is delayed by 200 milliseconds. What is important that I have seen many times is that people think time boost gives sequencing rights or block proposing rights. Time boost doesn't give such rights. It only gives 200 millisecond advantage in the first come, first serve ordering policy. And time boost is auctioned. So auction takes place every minute. It ends 15 seconds before the next minute starts, and the round winner is determined by this sealed bid second price auction. So sealed bid second price auction has this nice property of incentive compatibility. There is one reserve price, which is 1,000th of Ether. So if nobody wants to bid more than that, then time boost is not given to anyone. And then we are reverting back to first come, first serve. So there is no delay. Just to give you some idea what numbers look like so far, the revenue stands at $2.8 million Ethers, and $4.1 million worth Ether is deposited in the auction contract. So there are 3 regular bidders, and 2 of them bid almost all the rounds, so all minutes, and one of them bids once in few minutes, let's say every 6 or 7 minutes. We wanted to measure how much value is for the time boost owner. So we wrote this paper. So if you're interested in details, I recommend you to check this paper here, the title, so together with colleagues. So we looked into automated market makers that were deployed on Arbitrum, and how much arbitrage profits can be extracted with this 200 millisecond time advantage. And we looked into this sex-tex arbitrage in which there is external venue, so outside market, and there is IMM on the Arbitrum. And if there is a price difference, you can make money. So we made the standard assumptions from the literature that, let's say, the price impact for trading on the external venue is negligible, which doesn't necessarily hold, but let's say for simplicity. And the price discovery for the risky asset is happening on the outside market. So hopefully that changes at some point. Also, we ignore the noise traders on AMM. So let's say they don't exist. So AMM is only how much TVL is available there. The price doesn't move. Or in reality, of course, it moves, but we can assume that if they are noise traders, it moves in both directions with equal probability. And the risky asset, the price, external price, follows this memoryless process. So price changes don't depend on previous minutes or previous price changes. So we simulated the expected gains with these assumptions. So we took the historical real data from Binance last year, July, and we looked at all large pairs of assets of Ether and USDT and Ether and ARB, etc. So Bitcoin was also there. And we observed when we solved the optimal strategy that waiting till the end of the time advantage, so this 200 millisecond, once there is an arbitrage opportunity, is the optimal strategy. So that was the empirical observation. And the optimal strategy we calculated using this dynamic programming, where the state is how much time advanced in the 200 millisecond interval. So that's the advantage window. And we assume that if the arbitrager who has time boost doesn't take the trade, then it will be taken by other users. So this is conservative assumption. So it gives a lower bound on the value. And we only looked at spot trading. So we also looked, so this minute performance in that month, July 2024. And we looked into 3 strategies. So always arbitrage is basically first come, first serve. As soon as you see arbitrage opportunity, you take it. And that was giving a mean profit of $5. So that was a pool of Ether and USDC. And max profit was $21,000. So there was 1 minute where arbitrager could make this amount if the pool size was $300 million, which was quite close to the real number. So arbitrage in equal intervals corresponds to basically priority Gauss auction model where you can trade at the end of the block time. So we took the same 200 millisecond interval, and we see that mean profit is increasing, but max profit goes down. But if we now take time boost and optimal arbitraging strategy, which says that you need to wait 200 milliseconds, but once you see the arbitrage opportunity is there, so not trading in equal intervals, but waiting 200 milliseconds once the event is triggered, and you can take arbitrage or make money. But of course, this includes LP fees in the calculation. That's how the arbitrage profits are actually defined. So you need to cross the threshold of paying fees and still have positive value. So max profit was $29,000. So there was 1 minute where you could make $29,000. So it's very high variance. We also looked at all other large pools. So the last number tells you LP fees. So 500 is 0.05% fee and 3,000 is 0.3%. So as you can see, you are making with time boost much more money if you pay less fees. And these are all the large pairs. We also looked into the option of letting the applications or smart contracts know about time boosted transactions at the execution. So now you can access this data and find out all transactions which were time boosted or not, but you cannot do it at the time of execution. So that is doable by introducing some precompile. But once we do that, it's interesting how AMMs react to this opportunity. So what they could do, of course, they can ignore and not execute time boosted transactions. That's an option. But I think they can do something smarter, and that example of that thing they can do is to have different fee structure for time boosted transactions. So not to make them pay flat fee, fixed fee, but try to capture more value from time boosted transactions. So modify basically AMM slightly. And that is, for example, doable by these Uniswap v4 hooks. Okay, so they can do that, but then also time boosted parties can also react to that. And also one thing here is that they need to limit number of time advantaged, so time boosted transactions, 1 per time window, but that's only 200 milliseconds, so that's not a big restriction. Otherwise, arbitrager can just send many transactions and get all the value or most of the value. So we solved the optimization problem, how much they should extract from the arbitrager time boosted party, where time boosted party is smart not to move the price to the true price, because otherwise it's not getting any value. So it's moving the price somewhere in the middle between the AMM price and the real price. And that allows it to capture half of the value. So half of the value goes to time advantaged arbitrageur. And if we assume that auction of time boost captures all the value arbitrageurs capture, then revenue will decrease by a factor of 2. Then quarter value goes to liquidity providers. And I think that's better than nothing, or better than fees plus nothing, because that's what they are getting now. And 1/4 of maximal extractable value stays unrealized, and it's not clear, at least in our model, who would get it. So another problem we looked into is similar to what Lioba was talking about. So there is this backrunning opportunities where noise traders move the price on decentralized exchange, and there is an opportunity to make arbitrage. And we try to compare time boost to first come, first serve. And right now we also try to understand what happens with priority gas auction. Okay, so we assume here that price, so it's the opposite of Sextex arbitrage, in which we were assuming that price doesn't change on AMM. Here we assume that price doesn't change on the outside market, and all players have the same value for each opportunity. So the main assumption is that there is some latency to reach the sequencer. So once you submit transaction to sequencer, there is some latency. And that latency can also be interpreted as sum of 3 components, latency components. One is to, once the sequencer discloses the state of the chain, and it reaches to nodes who are listening to it, then nodes interpret that state and find that there is arbitrage value, and then they send transaction, and it needs to reach to sequencer. And this total value we assume is the same for all players who are playing this game. We also assume that backrunning opportunities come with some process. So example is Poisson process, but you can plug in different process. And we know that there is some distribution of the value. Okay, so now what are the players doing? Players can decide how frequently to send their transactions to sequencer, and we assume it to follow Poisson process. So the only thing that players decide is how frequently they submit transactions. So the only parameter of a Poisson process. And one justification of having Poisson process is that you're not giving any information to other players when will be your next transaction. Also, we need to have in this model the gas fees, so how much you pay for one transaction. Okay, so now we have one player, Alice, that has 200 millisecond advantage over all other players, and we call we have this other players, aggregate other player, Bob, which doesn't have time advantage, but it employs this probabilistic strategy of trying to steal backrunning opportunities. And then we can calculate what is Bob's expected utility. It will depend on how many transactions it's submitting and what are the gas fees. So now Alice is faced with this following decision problem. Once it sees the opportunity, it can now react to it, which Bob cannot do. So Alice needs to decide to extract it or not to extract it. And it can calculate the probability of winning because we assume it knows what is Bob doing. So it can calculate also expected utility. And it turns out that if value is large enough, Alice will try to extract it. And if value is low enough, then Alice doesn't extract it. Okay, so now Bob just needs to decide on his own frequency, or all the other players decide on the aggregate frequency. And if we assume some mild conditions on the distribution function, we have one optimal strategy for Bob on the frequency. So we can also complicate this a bit and allow Alice also have this probabilistic strategy. So Alice also tries her own Poisson process of sending transactions. And we can solve that game too, but it becomes a bit more complicated. But what is important is that if gas fees are large enough, then in the equilibrium, so there is equilibrium in which Alice doesn't even try that strategy. But if gas fees are small enough, we cannot exclude that Alice will also try it. So there will be some, let's say, spamming coming from Alice too, even though she's the time-boosted party. We also looked into first come, first serve setting where there is no such party. And if there are sufficiently many players, all the value will go into these gas fees. So in the reverted transactions that we can interpret as spam. So we took one particular distribution and estimated it from the data and saw that first come, first serve has 6 times more spam than time boost. And the intuition of that is that time boosted party takes high value arbitrages and only leaves a little bit on the table for other players. We are now, actually with researchers in Flashbots, try to model priority gas auctions. So here we have the same situation, except there are block times, and we only learn which backrunning opportunities survived the process at the end of the block time. So those that survive, they will be taken in the priority gas auction of the next block, but all the rest can be taken by these probabilistic backrunning strategies. And we have some initial insights that if the block times are long enough and gas fees are low enough, then in priority gas auctions, we will have very similar level of reverted transactions as in first come, first serve setting. And the intuition is that nothing will be left to be exploited at the end of the block in the equilibrium. And then we basically get this dynamics of first come, first serve. That's all from my side. Thank you. Questions?
All right, we have time for maybe 2 quick questions. Any questions?
So you have the 2 different players. I know the 2 different models, I guess the SexDex and more the backrunning one. What I'm wondering is, do you think it's the same person that's going to be doing though and then paying for the time boost advantage, or is it just going to be that either or sort of wins?
Yeah, I think it will be the same person because in principle it's the same arbitrage opportunity. It doesn't matter where it came from, there is price difference that needs to be exploited.
Have you thought about measuring or estimating like a different metric? So this is kind of like the possible profit they could make in these models, right? Is there some proxy from what's actually happening on the chain that you could compare to maybe? I know a lot of it is kind of data we don't have because it's not on the blockchain, but is there something that might be close that you've run into?
But now there is data, right? So we can track the time boosted transactions and see how much maybe they are making. Or what is not available on chain?
Well, you can tell, well, you can't tell how much they're, for example, like what price they're getting on a sex.
Yes.
Exactly, right.
Yeah. So in the first part, we are just taking the Binance best price and assuming there is no slippage there. But yeah, that's not. But on the other hand, that is conservative because they can have some other like better price or different utility function or different goal. So at least there is that. So there is this price difference that gives you value, but can be some other sources for the value too. So I would say this giving also lower and upper bounds on the value. But now with the time boosted transactions, maybe we can even infer what they are doing, like understand or compare it to this like Binance best price or centralized exchange best price and see that even so they are not making money in this sex arbitrage, but they still trade. So they must have some other utility function to get some idea about what they are doing.
Cool. That makes sense. Thank you.
Let's thank Akaki. And we're going to go right into the next session because we had the break just before this talk. So we'll get set up. All right, so kicking off our next session, our first speaker will be Mahim Nikelkar, presenting work that he did during his PhD at Cornell.
Awesome, thank you. So I just graduated with my PhD from Cornell. I'll be starting as a, thank you. Did not expect applause for that, but thank you. And I'll be starting as a faculty at Purdue next year. And this is kind of my, awesome. Well, you know, I expect this round of applause for every slide now, so. All right, anyways, today I'm very excited to talk about some recent work on the incentives of accountable cryptography. And this is joint work with Aditi Jobano, and Matt Weinberg. So as we all know, multi-party cryptographic protocols. All good? You know where it's all wait. 8 seconds, okay. No worries. Okay, cool. So I'm excited to talk to you about accountable cryptography and its incentives. So the starting point is, as we all know, multi-party cryptographic protocols, multi-party protocols in general, make a lot of these honest majority or honesty of a quorum kind of assumptions. So for example, there's a lot of protocols that work when you have, say, 2 out of the 5 nodes are corrupt, but don't work, completely fail when 3 out of the 5 nodes are corrupt. And a kind of common goal that we have in mind is, hey, can we detect these protocol failures when they happen, and what can we do to fix them? So broadly, from an accountability perspective, we have these few intuitive goals in mind. So the first one is, let's say we want to identify when things go wrong. So that means whenever there's a failure of an assumption or a protocol property, we want to be able to detect this. And then if possible, we also want to be able to identify one of the culprits so that we can maybe penalize them in some fashion. So in this talk, my focus will be on scenarios that are sort of not publicly detectable, not publicly visible. So don't think about things like double signing, which you can just observe on chain and figure out that there's been a block height that's been signed twice. But instead, the setting we want to focus on today is where some party, if there's a collusion or if there's a failure in the protocol, some party will get a proof that they can then show to some external judge that will enforce like some penalization procedure. And we'll call these sort of protocols whistleblowing protocols. So essentially what the whistleblowing framework is let's say you have this multi-party protocol that's running. In its ideal form, it's emulating some functionality F, and the security is provided if at most some T-1 protocol nodes collude. So if T or more protocol nodes collude, then the protocol may completely fail. And the kind of idea with whistleblowing is that if there is a T-size collusion that happens, then you can essentially guarantee that one of these parties within the collusion will obtain a proof that's publicly verifiable so that they can show an external judge that, hey, something went wrong with the protocol and please enforce penalties. And for our purpose, you can think about this judge as an external smart contract as well. So you don't have to have any trusted state and you can sort of self-enforce this without any trusted party being involved. So when this collusion forms, there will be some party that has access to a proof that they can show this smart contract judge. So in general, we want to look at whistleblowing from two perspectives. The first is this cryptographic one, in the sense that when is it possible to generate these whistleblowing proofs of collusion? So for what cryptographic primitives can we guarantee that when there's a failure of the assumption, this threshold assumption, one of the parties will obtain this proof? And the second thing, which I'll focus on today, is the mechanism design or game theory side, is that even when we have such a cryptographic proof of collusion, are these colluding players actually incentivized to submit this proof to the judge, or are they just incentivized to stay silent? And in this context, we'll model a new form of collusion through essentially using smart contracts. We'll call this smart collusion. So today, because this is MEV Day, I'll only focus on the mechanism design side of things and show sort of a general framework that can capture many existing works from the cryptographic whistleblowing proof of collusion as well. Okay. But just so that we're on the same page, these are some sort of natural properties that you want so that you build some intuition in your head. So sort of the cryptographic properties that we want are, let's say, some sort of completeness and soundness. So completeness says if this collusion has T parties, then someone will obtain a proof that they can show to a judge. Soundness means that if there's no collusion, then nobody can convince the judge that there is a collusion. And then unframability means that even if everyone except for one of these parties colludes, they still can't frame another honest party of being involved in a collusion. And this is especially important for proofs that can identify particular colluders. But from the game theoretic side, what we want is for these proofs to be incentive compatible. That means that whenever a proof is generated, you want to be incentivized to submit this proof. Or in other words, honesty must be sort of this sub-game perfect Nash equilibrium of the entire game. Of first whether deciding to collude or not, and then the second stage of deciding whether or not to submit this collusion proof. So I'll mention that this is sort of a broad framework that captures a lot of natural applications. So there's a bunch of new applications that we provide where you can think about a set of servers guaranteeing some service to the client and colluding with the client to provide some extra service that is sort of outside the protocol. So in the paper, we'll discuss things like distributed randomness beacons, where you want to ensure that this randomness is not leaked earlier, or things like rate-limited credentials or tokens, etc. And it also naturally applies to a lot of very recent existing work that looks at accountability in cryptographic primitives. So one really cool work is this secret sharing with snitching work, which essentially embeds this like MPC hard function in the reconstruction phase of secret sharing. So in typical secret sharing, if T parties collude, then this is sort of a silent failure and the protocol just breaks. But with secret sharing with snitching, if T parties collude, the only way that they can recover the secret is just sending all of the shares to just one party. So what this means is that that party will get a proof of collusion that they can show to an external judge. Another thing this sort of applies to is this new recent work on accountable threshold decryption, which applies to a lot of privacy-based MEV techniques. So in particular, in such a case, if these committee members come together to decrypt a ciphertext early, say in an encrypted mempool, then there will be a proof that they can show to a judge that they colluded to decrypt the ciphertext early. It also applies to other protocols like BFT forensics. And sort of our general idea is to establish this broad framework so that our game theoretic results in particular can apply to a large number of these accountable cryptography primitives. Okay, but as I said, I'll focus primarily on the game theory today. And we start with the idea that let's say you have this proof of collusion, right? You're a colluder who is equipped with this proof of collusion. The thing we want to look at from a game theory perspective is, should you submit this proof or is it better to stay silent? What are the incentives involved in that? So here's sort of the roadmap for the game theory. So I'll describe the first game, base game B, which is sort of the standard game of this cryptographic primitive. This is without any whistleblowing. So this is like, say, just standard secret sharing with silent failures. Then I'll describe this whistleblowing game, where now you design a cryptographic primitive with accountability so that someone gets a proof that they can show to a judge. And finally, I'll arrive at this new model of retaliation, which models our new smart collusion based approach that colluders can use, essentially where a collusion can be formed in a way that the colluders are penalized if they try to snitch on each other. Okay, so here's sort of the base game B without any sort of whistleblowing or accountability. Let's say each player I can play one of two things, either they're honest or they collude. And for simplicity, I'll only talk about n out of n collusion. So you need all n parties to collude in order to break the protocol, but the results for t out of n collusion are pretty similar as well. And let's say if all n people collude here in this example, each party gets some utility v. So the total utility of the collusion is n times v, and each party gets v. So now it's easy here to see that if there's no accountability procedure, obviously everyone's going to collude. That's a pure Nash equilibrium strategy that everyone just colludes. So now let's say a cryptographer comes along and designs a way for when this collusion happens, somebody obtains a proof of collusion. So this proof will be publicly verifiable so that you can be verified by a smart contract. We also allow it to be anonymous. So it doesn't need to reveal who submitted the proof. And that way we can just model this as a smart contract intuitively. So as I said, the game theory questions are, how do we design this reward mechanism to actually incentivize people to submit this proof? So here's sort of the basic design for a protocol that works. So each player you can think about as depositing some deposit, D, into this whistleblowing mechanism. And then the player decides whether they want to play honest or collude. So this is sort of the steps in the game inside the model. So first, the whistleblowing mechanism will ask for some deposit, and then each player can decide whether they want to play honest or collude. And if all of the players play collude, then this forms a collusion, and that results in this whistleblowing proof given to someone. And further, now when there's a collusion, the colluders can play either whistleblow or stay honest, so they can choose to either submit this proof or just stay silent and faithful to the collusion. And now, depending upon how many of these proofs were submitted to the mechanism can reward or penalize these colluding players. So basically, because we have anonymous whistleblowing, we need to allow for multiple parties to submit proofs as well. So you can think about these reward functions R and penalty functions S as sort of functions on the number of whistles that are submitted. And you can think about the deposit as sort of the maximum of all penalties that can be enforced to a player. So any maximum penalty that they can incur, that's how much deposit we'll take from them. And these are some natural properties that we'd want from a whistleblowing mechanism, is that when there's 0 whistles that have been blown, obviously you don't want to reward anyone, you don't want to slash anyone, because this is sort of the normal case. And we don't want to create any money, so any money that's awarded as rewards must come from penalizing some other player. And we also want to incentivize whistleblowing, so that means incentivize submission of this proof. So we want it so that the reward for submitting this whistle is larger than the penalty you'd get from losing out. Okay, so here's one mechanism that works. There's a bunch more that can, but here's just one example. So here's the high-level idea: is you just take deposit D is V plus epsilon from all of the players. So V again is the utility each player gets from the collusion. So you just take a deposit that's slightly larger than the individual utility that players get, and if there's no whistleblowing, so this is sort of the honest case, then take no action. If there's one whistle that was submitted, then you sort of reward the player V plus n minus 1 times epsilon, and then penalize everyone their whole deposit. And if there's more whistles, you actually just give 0 reward and just penalize everyone involved. And why does this work? Well, the intuition is you're sort of creating this prisoner's dilemma-esque situation for whistleblowing. So if I'm the only person that is whistleblowing, then I'm always better off, and I'd want to do that. But if more people whistleblow, then everyone's better off. Everyone's worse off. And so you're kind of creating this prisoner's dilemma and incentivizing people to whistleblow, but doing so will land them in a bad equilibrium. Okay, but now what can colluders do if they know about this whistleblowing mechanism? And the intuition here with smart collusion is using smart contracts to strengthen collusion in a way that penalizes defectors of the collusion. So basically what we're going to do is allow the attackers, allow these colluders to use smart contracts as commitment devices. So what the contract will do is it will hold like a really, really large deposit from all of the colluders, and then say something like, if anyone tries to rat us out, anyone tries to whistleblow, then we'll just burn everything to the ground, right? So this sort of intuitively will incentivize these colluders to stay faithful to the collusion. And the idea here is that the colluders can decide on this retaliation smart contract mechanism after the protocol designer's whistleblowing mechanism is announced. So they have this sort of first mover advantage. And we showed that smart collusion can actually circumvent a lot of prior results in accountable cryptography. And basically, it's impossible to protect against smart collusion. So I'll kind of just detail the game a little bit, and sort of to state this impossibility result a little bit more formally, what we say is that smart colluders with enough money can always win. And the intuitive idea is that you just have a retaliation contract with a really large deposit. And what this means is that achieving unconditional security is feasible without smart collusion, but it's infeasible with smart collusion. And in fact, this impossibility result ends up holding true even when your whistleblowing protocol is anonymous, so that it doesn't leak who is doing the whistleblowing, and even when it can identify all colluders. So for example, in a T out of N collusion, even if it can identify all of the colluding players and then you only slash the colluding players, the impossibility result still holds. But we do have this bounded positive result, so all things are not lost. And the idea is we can protect against smart collusion, which takes in a much larger amount of money. So basically, we show that a small whistleblowing deposit, so let's say you take a deposit of D from each player in our original whistleblowing mechanism, this can protect against smart collusion with a much larger retaliation deposit of roughly n-1 times d. And sort of here's the intuitive sketch of a protocol for showing that this works, is basically what you do is you take deposit d from all of the players and then give the whistleblowing reward as n times d minus epsilon. So just the minus epsilon is so that all the colluders are not disincentivized to collude and then whistleblow. And basically, for smart collusion, to prevent this whistleblowing, each of them would need to put in a retaliation deposit that's larger than the reward that they would get from whistleblowing. So if I put in a deposit that's larger than n-1 times d minus epsilon, then I will prefer to stay silent because I'd lose a larger amount of money than I'd get from whistleblowing and claiming the reward from the mechanism. And we actually show a roughly matching lower bound. So this basically shows sort of a intuitive tight result for how much whistleblowing deposit we need to protect how much retaliation smart collusion deposit. Okay, another sort of positive result we have is in a sort of a long-standing server setting where clients are transient. So what this means is if there's a service that's offering some computational service, let's say to clients, and clients are coming and going, we show that smart collusion can only work to break our protocol if the service requires each client to lock up their deposit for indefinitely long. But as a client of the service, I'm not incentivized to collude with the servers if I have to lock up my money for indefinitely long, because that essentially is like a cost of service for me, which isn't accounted for. So basically, only in this specific setting, we can actually get unconditional security. As I mentioned before, the results roughly transfer to the T out of n collusion setting as well, basically by replacing all instances of n with just T. There's one subtlety of how we model this T out of n collusion. So in our model, we just assume that these T colluding parties somehow get together, and we start analyzing the model from this starting point. But the game does get complicated if we start to analyze this collusion formation phase, or if there's multiple collusions that players can sort of switch between. I'll just kind of talk about two example deployments before concluding, just to kind of give some intuition of where the results could be applied. So the first one you can think about is these custodial wallets. So think about something like Coinbase or Binance, which holds your funds for you in a way such that your key is not in the hands of the user. And this makes sense for some users who don't want to worry about storing a key themselves, so they can custody their key to an external service. And that external service can use something like secret sharing to distribute the key amongst multiple servers. But maybe the user still wants to be protected against collusion of these servers. So the user doesn't want to custody her funds herself, but still wants to be protected such that the committee that she's custodying her wallet to doesn't collude to just steal out her funds. So this is one kind of example where this whistleblowing framework can come into play. And we show that each committee member can deposit some 2W over n, where W is sort of the money in this user's wallet, in order to be protected against collusion. And the idea is, like, if there's a collusion proof that's submitted by the committee, the user will be reimbursed the amount of money in her wallet. So even if there's a collusion, she won't end up losing any money. And this is, of course, without smart collusion. Again, smart collusion, given enough money, can still break this. The other sort of interesting example deployment scenario is with distributed randomness beacons. So imagine sort of a committee that's running a VRF service for generating randomness that applications can use. So let's say we have this casino application that subscribes to this randomness feed and uses the randomness to run its casino games. Now the application still wants to be sure that nobody is colluding to learn this randomness early and then sort of stealing from the house. So basically what the casino can do is it can buy insurance from the committee. It can pay some premium to make the committee members lock up their deposits so that the casino is protected against any collusion that happens. And I'll mention that insurance pricing is sort of like an orthogonal point. You can think about it as based on some risk-free return of these extra funds that the committee members have to lock up. So you can think about some pricing algorithm for that. I'll just conclude with a brief summary. Basically, I talked about new smart contract-based collusion that circumvents a bunch of results in accountable cryptography. And I provided this sort of broad focused whistleblowing model for understanding the incentives in these accountable cryptography protocols. So with smart collusion, I showed that it's impossible to provide unconditional security, but on the positive side, you can protect against a much larger adversary with a lot more money by taking smaller deposits from everyone. And kind of the TLDR point of all this talk is even when we think about accountable cryptography, even cryptography more broadly, we should also think about the incentives. And I'll end there.
Thanks for the talk, Mahimna. And I really like the message of combining the incentives and the security side of things. One question, though, which on the part that you didn't mention so much today, but still maybe you can give some insight. So I'm curious, in generating this proof of collusion, this whistleblower proof, is it not possible to circumvent the generation of these kinds of proofs with like a dark DAO-like collusion where the committee colludes via TEE, where if you're decrypting some ciphertext, you're not revealing the plain text, but some function over the plain text? Can you protect against that somehow? Does the question make sense?
Yeah, so that's a good question. It's sort of unclear and dependent upon the scenarios. So for example, this secret sharing with snitching work protects against MPC-based collusion, but it still finds it challenging to protect against TE-based collusion. So if, for example, everyone puts in their keys inside of a single TE and colludes that way, that's sort of already a centralizing component of the protocol. So it acts sort of as one entity with private state. And it seems more or less impossible to prevent against that kind of collusion as well. But you can prevent against MPC-based collusion. So the way this secret sharing with snitching work, for example, works is they embed this MPC hard function into the reconstruction part of the secret sharing. So the only way that you can reconstruct the secret is actually by just sending the shares to one specific party.
Okay, so the snitching works when you assume the adversary doesn't have access to a TEE.
So it's not that the adversary doesn't have access to the TEE, it's the case that all of the colluding nodes don't like dump their keys inside of the same TEE.
Okay, thank you.
Yeah.
And we can take one more. And if the next speaker could go start setting up, please.
Yeah, my question was kind of related. Could you say one or two words about are you using additional tricks compared to what secret sharing with snitching does in terms of like how you do it cryptographically, preventing collusions?
So our work, I'll say, was more focused on the game theory side of understanding the incentives of all these protocols. So we provide some number of new settings, specifically in this sort of client-server model, where the servers are providing some computational service to the clients, and you want to prevent like off-band collusion. So think about this like randomness beacon setting, where you want to ensure that there's no collusion to recover the randomness early. And then we also show that our game theoretic framework also applies to existing accountable cryptography protocols, including this like secret sharing with snitching work, accountable threshold decryption work, among others. So there's no new cryptography work on that side, in our paper at least.
All right, let's thank Mahimna. Great. Our next speaker will be Jan Bormet from TU Darmstadt.
Okay, can you hear me? Nice. So hi everyone. My name is Jan, and I'm presenting today our recent work on Beat MEV, and this is joint work with Sebastian Faust, Hussein Ottman, and Zian Ku. And in our work, we deal with the MEV problem through the means of encrypted mempools. We eliminate a single source of failure through threshold encryption, and we make use of a recent batching technique for extra efficiency and security guarantees. And also we are one of the first works to eliminate expensive per epoch setup on behalf of the committee members. But before going into details, let's quickly start with an overview of how encrypted mempools work. So in blockchains, users commonly submit their transactions to a mempool. Suppose that some user submits transaction 1 here, where he buys a large amount of some asset, let's say asset A. And there's also some other transactions in the mempool. And when it's time to make a block, a miner comes in, takes a look at the mempool, and collects transactions from the mempool, assembles them into a block, and the transactions get executed. And one problem here is, as we all know, the problem of MEV. So user 1 can observe what is the content of the transactions and see, for example, that the first transaction buys this asset A and run a front-running or sandwich attack. So in this case, so in this case, he sees that the transaction buys a large amount of asset A and kind of puts the transaction before that also buys asset A and the transaction afterwards selling asset A, running a sandwich attack, and this has some kind of downsides. So first of all, the user who sent originally transaction 1 gets worse execution prices. The miner profits from this. And also it has the side effect that transactions 4 and 5 don't get included in the block anymore. So also this creates some inefficiencies. So encrypted mempool tries to prevent this issue by, instead of having users submitting their transactions in clear, users actually encrypt their transactions to some public key PK. And when the miner needs to assemble a block, he doesn't know what is the context of the content of the transactions. So he needs to assemble the transactions kind of in an arbitrary order. And the idea is that he now cannot do any malicious MEV. He cannot do any front running in particular. Then once the block is assembled, we wait for finalization. And when the block is finalized, whoever obtains or whoever holds the secret key decrypts all the transactions and the block gets executed. So clearly there's a problem because if only one party has custody of the secret key, this party could be malicious and is basically a single point of failure because this party could just do MEV on its own. And yeah, it could be easily bribed. We just want to avoid these kind of trusted parties. So instead, the common practice is to use or make use of a tool called threshold encryption. So instead of having a single party having custody of SK, we're going to assemble a committee of, in this case, 5 parties and secret share the secret key among the committee members. So now each committee member has a secret key share. Also, we're going to set a threshold T. In this example, we set T equal to 3, such that any subset of at least 3 parties is able to decrypt transactions or ciphertext, and any malicious committee that doesn't meet the threshold. So, for example, parties 1 and 2 here, it's not 3 parties, so they cannot decrypt or learn any information about the transactions. And the naive approach now is having all users just send encrypted transactions, and when the block is finalized, all the transactions are decrypted individually. And the big downside with this is that now each committee member has to release a partial decryption for every single transaction in the block. So if we have B transaction in a block, every committee member has to send messages on the order of B. And this we really want to avoid because this causes large propagation delays and would kind of cause the system to have some trouble in keeping up with the blockchain. So we avoid this issue by trying to decrypt all the transactions at once, so not individually. And kind of common approach here is to make use of identity-based encryption, where instead of encrypting to just a public key, you can encrypt to an arbitrary tag. So suppose we're trying to encrypt to block 5. So let's say the tag is 5, and all the users have encrypted their transactions to this tag. And again, some transactions are put into the block. The block is finalized, and now the committee members just publish a decryption key for this specific tag, in this case, K5. And K5 can then be used to just decrypt all the transactions in the block. And the cool thing now is that for publishing this 5, this doesn't scale, or the communication for publishing this K5 doesn't scale with the size of the number of transactions in the block. So we kind of have better properties regarding communication efficiency on behalf of the committee members here. So far, so good. However, there's a problem, because now we've published K5, observed that transactions 6 and 7 are still in the mempool, and because they have been encrypted to the same tag, they can now also be decrypted. And now we have basically 2 transactions in the mempool, which can be observed by whoever builds the next block. So basically, the next miner can just run MEV on them. And this kind of property we want to avoid. We call this property pending transaction privacy. And what we want instead is that we want to be able to decrypt exactly the transactions in the block, but transactions that are kind of stuck in the mempool stay encrypted, so are not vulnerable to MEV. And to this end, there is some recent work by Shuduri et al. That achieves the best of both worlds. So they define a notion called batch threshold encryption that on the one hand achieves this pending transaction privacy, and also it has constant partial decryption size. So still only the transactions in the batch get decrypted, but committee members only have to kind of communicate one element. However, with their construction, there's some practical downsides. On the one hand, their construction requires recurring per epoch MPC setup among the committee members. So before users can even encrypt to a block or to some epoch, the committee members have to run some DKG-like, very expensive MPC setup. And this becomes prohibitively expensive and causes the system to kind of not being able to catch up with blocks or epoch lengths on the order of maybe 10 seconds. And at the same time, in their construction, ciphertexts are tied to a specific epoch. So at the time of encryption, a user already needs to know what block their transaction will appear in. If then a different batch has been encrypted to that block, decrypted in that block, so their transaction didn't make it, then they have to re-encrypt. So they have to kind of stay online and repeatedly send transactions every time their transaction doesn't make it. So this would just introduce some further congestion, and yeah, it's just not so nice for the users to have to do this. And in our work, we try to mitigate both of these problems. So on the one hand, we don't need any recurring setup among committee members. So we only have a single one-time setup that happens in the very beginning. And from that point, you can kind of encrypt without any setup happening before that. And also our ciphertexts are independent of an epoch. So encryptors can just encrypt. They don't need to know a tag in advance. They don't need to know which block they will appear in. And at the time of decryption, you can dynamically assemble transactions in a block and kind of decide later on which transactions make it into the same batch. So to see how we achieve this, let's look at a high-level overview of our constructions. Suppose that users 1, 2, and 3 here each want to encrypt a transaction. And we're going to start with a very simple one-tempad style encryption. So user 1 here encrypts message 1 by just sampling a PRF key, K1, and evaluating the PRF at index 1 in order to kind of put a mask on his message, M1. And to make this decryptable, the user also attaches to a ciphertext an encryption of K1 under the public key of the committee. And the same is repeated by users 2 and 3 for their respective indices and their secret PRF keys. And to see how we decrypt, let's start with the easy example of having the batch that only contains one transaction, only C1. If the committee wants to decrypt this batch, they just use kind of in a distributed manner, decrypt this K1. And once this K1 is known, anyone can just recompute the PRF, evaluate it at index 1, and undo the mask and recover M1. Okay, so far so good. What happens if the batch is larger? Suppose we also add C3 to the batch, and now we could just repeat this process. The committee also sends K3, and we do the same thing or like we evaluate now this PRF under K3 at index 3 to also recover the third message. However, this clearly is not what we want, because now we exactly have what we wanted to avoid in the beginning. So now the committee members have to kind of communicate on the order of the batch size. So in this case, the batch size is 2, and they have to clearly send one key for every single ciphertext in the batch. So what else can we do? Let's say instead of sending K1 and K3, we use some kind of homomorphic encryption to aggregate the ciphertext and instead send a decryption of K1 plus K3. And now what happens to our decryption process? So we can now no longer evaluate the PRF under K1 because we don't know what is K1. But instead, we can evaluate the PRF under K1 plus K3. And due to some nice homomorphic property of the PRF, this is exactly equal to evaluation, or the sum of the evaluations under the two distinct keys. So the evaluation under K1 and under K3. And now we can see that this cancels out, basically this cancels out the evaluation under K1, and we are left with the message masked with the PRF evaluation under K3 at index 1. So we didn't really send K3 now, and we wanted to avoid this. So how can we get rid of this mask now? And for this, we will make use of another nice property of a PRF that we can kind of get, which is called puncturability. Suppose that user 3, who knows this K3, now also punctures his key to compute K3 star. And he punctures his key at index 3. And with a punctured key, basically, you can evaluate the PRF, for example, at index 1, at index 2, but not at the punctured index. So K3 star can be used to evaluate at any index despite the punctured index 3. And this is clearly important because if we want user 3 to attach this punctured key to a ciphertext, but if it would be possible to evaluate the PRF at index 3 with the punctured key, then you could just trivially undo the mask and recover M3. So the good thing is now that we know K3 star as part of the ciphertext. During aggregation, we can just use K3 star to undo this mask and thus recover M1. And if the same is done by also user 1 and user 2, so every party also publishes a punctured key for their key and their respective index, we can actually decrypt all ciphertext in the batch with only sending a single, or like sending kind of the sum of the keys, so it's order 1 communication. And also, we want the spanning transaction privacy, so let's observe what happens to message 2. So clearly, whatever the committee sent isn't at all dependent on K2. And we also know that the punctured key K2 star cannot be used to kind of undo this mask. And the other part of user 2 ciphertext, which is the encryption of K2 under the public key, is kind of remains secret if the committee doesn't release any information about K2. From this, we can deduce that kind of M2 remains private, and we get this nice or important security property of pending transaction privacy. And at the same time, observe that we didn't use any epoch setup, and also the committee member, the users didn't have to specify in the beginning which they didn't have to use some tag or they didn't have to know basically which block or like which other transactions they will be batched with. So we have kind of achieved all these properties that we wanted in the beginning. However, there's a small downside. So in order to do this punctured evaluations with this PRF, we wanted all these nice properties of puncturability and a key homomorphism from the PRF. But this means basically as a trade-off, we have that this punctured evaluation is rather expensive computationally because it requires us to compute a pairing. And yeah, pairings are rather computationally expensive group operations. So we kind of are a bit worried about aggregation time here. And this is even worse because if you scale this up to larger batches of size, for example, 100, then you will see that this aggregation step requires on the order of B² pairing. So it's rather computationally expensive. And we will later see some techniques how we kind of mitigate this problem. But first, let's look at another detail. And this detail has to do with collisions. I've kind of glossed over or kind of assumed, without explaining why I can assume this, that every user has a single unique index or like it needs to sample this index. And one problem with this construction is that whenever there's transactions that have the same index, for example, now there's 2 transactions with index 2 and 2 transactions with index 4, then we cannot assemble these transactions into the same batch whenever there's a collision. So how we kind of would deal with this in practice is we would just have encryptors sample this unique index from a huge domain. However, another trade-off that we have from having these nice properties from the PRF is that this is not a normal PRF where the domain is exponentially large, but this domain is actually polynomially bounded, and its size somewhat relates to the size of the one-time setup we need to do in the beginning. So we cannot make this arbitrarily large. And if let's say this domain is rather small, and we have encryptors choose an index at random from this domain, there's the risk of having random collisions appearing. So how we deal with this in our work is instead of trying to decrypt all the transactions in the same batch at the same time, we just kind of open multiple sub-batches. So in this case, let's look how it works for the example of 2 sub-batches. We now, instead of trying to fit all the transactions into one batch, we assign them into sub-batches such that kind of no collisions appear within a single sub-batch. So now the transactions with index 2 are in 2 different sub-batches, and the transactions with index 4 are also in 2 different sub-batches. And basically, this means, and all of the committee members now just release decryption keys for every single sub-batch at the same time. So we have some kind of minor communication overhead now, but we are now able to deal with these collisions. And in our work, we do some analysis, and we can show that for appropriate number of sub-batches, we get reasonable statistical correctness of basically having that the probability of having collisions more collisions than the number of sub-batches in a single given index is less than 2 to the minus 40. And also a nice property of this is that this really helps with our second issue of having to compute all these punctured evaluations. Suppose that we have alpha sub-batches, instead of having on the order of B² pairings during aggregation, we now only need to do B times B over alpha pairings for the aggregation. So the more sub-batches we have, the less is the smaller is the probability of collisions, and also the faster aggregation gets. But we pay a small overhead in partial decryption size. And to see all of these kind of different properties in the like how they work out together, let's look quickly at the evaluation. So for encryption, we are very efficient actually. We can encrypt ciphertext in less than 2 milliseconds, and also our ciphertexts are fairly small. We have less than like an optimized version of our construction has less than 200 bytes of overhead per ciphertext, which when calculating with call data amounts to about 5 cents. Partial decryption is also rather efficient. So this means that, for example, for large batches of size 512 transactions, the work that any individual committee member has to do can be carried out in less than 300 milliseconds. And also the partial decryption size is rather small. It's just one group element, which amounts to 48 bytes. So we have some room for adding more sub-batches here. And now let's look at kind of the difficult part, the aggregation. The blue curve shows the the time aggregation needs without sub-batches, and you can see that it doesn't look so nice. So even for 100 sized batches, we get aggregation times of more than 10 seconds, which I would say is a bit infeasible. But when you start to add appropriate number of sub-batches, you can even decrypt large batches of more than 500 transactions in less than 4 seconds, which I would say is reasonable. And a nice property of the aggregation procedure is that it's actually trivially parallelizable. So if you use the correct optimizations, then even on a desktop or like a normal desktop machine with just 16 threads, you can decrypt more than 500 transactions in less than half a second. So the approach would be to just like everything is efficient despite aggregation. So the approach would be to just have one fat node which carries out the aggregation and then just post the messages. So there, I want to mention there's also some concurrent work. There's basically 3 works which try to solve the same problems of removing this interactive per epoch setup from this original work, but they use a completely different approach, more or less related to witness encryption. They compare to us by being asymptotically more efficient in this aggregation step, but their ciphertexts are tied to a specific epoch. So they don't have this nice property that you don't need to know ahead of time which transaction which block your transaction will be inside of. And let's conclude with some follow-up or potential open problems. So in my opinion, the most important to make this more practical is to mitigate this aggregation overhead further. And I think most obvious approaches here are to use a more efficient PRF, which maybe doesn't need any pairings. And also you could, as I said already, there's this fat node, you could kind of try to outsource the aggregation to a very strong machine with lots and lots of cores. At the same time, all of these works require to set up the committee members with a DKG protocol. And this is not so nice because we really want a dynamic committee. So we want committee members to join and leave and kind of to reestablish the committee lots of times, maybe every epoch or every few epochs, and carrying out the DKG whenever that happens becomes prohibitive over time. So to this end, we have some follow-up work where we combine our work with the recent work of silent setup encryption, which allows us to completely adaptively start up a new committee without any interaction among the committee members required. And for this, we just pay with some like small efficiency losses. And with that, thanks for your attention, and here's a link to our paper.
Thanks for the great talk and great result. How does your work relate to like threshold batched IB? There was another talk at the main conference where they have this T-Bibe schema, and there is this like batch parameter that needs to be known at encryption time. So yeah, you encrypt an IB, and then the decryption keys are generated for digest, computed from the IBs in that batch. But there's also this batch parameter, which is a bit annoying because I need to know that at encryption time. So does your scheme realize T-Bibe without that batch parameter?
Exactly, yeah, that's what it does. So we don't have this batch. It's one of these concurrent works I mentioned. So interestingly, all of these concurrent works kind of have very similar approach, and their approach is completely different from ours. So all of these works have this property that you need to know upfront this batch parameter. And they model it in different ways, but in the end, you need it for all of them. And our work doesn't have this. And for this, we pay with like more with this aggregation overhead, I would say.
Any other questions?
You said that you need pairings. Which punctured PRF are you using?
It's due to Dujmovic et al., I think from last year's Eurocrypt. And they present 2 PRFs, which we can use both of them. It's just based on pairings and some one-time setup. And one of them has basically linear setup in this domain size, and one, I think, quadratic setup.
Have you tried using homomorphic PRGs with GGM trees?
No. We can look into that.
Right, we could take one last question. All right, let's thank our speaker. And then you got the clicker. All right, our next speaker will be Mark Simkin from Flashbots.
Okay, hello everyone. I'm going to tell you on some work in progress at Flashbots on building fast anonymous communication systems, which currently have the name FlashNets. Okay, so what is a, oh, I can guess, see it here. What is an anonymous broadcast system in the first place? So the one that we kind of consider here is you have, let's say, 3 parties. Each of the parties has a message. And these parties would kind of like would like to broadcast their messages to the network, but they would like to do so anonymously, so each message should not be linked to the sender of the message. And how this usually works is that the parties will in some way communicate with each other, and at the end the network learns the 3 messages, but cannot see that like M1 was sent by party P1. It could equally likely be sent by P2 or P3. Okay, so this is like a field that has lots and lots of research over many, many different years. So now let's draw some triangles. Kind of like we can look at like some very general approaches and we can put them in this triangle. So we have kind of like 3 properties that we might want to have, which is we would like to have our solution to have low bandwidth requirements. So the parties should not send around too many messages before the messages get revealed. We would like strong anonymity and we would like low latency. So the round complexity of the protocol should be small. And if we put something like onion routing as a blueprint, then it's great because it has very low bandwidth requirements, but it provides usually not very strong anonymity guarantees. And also the latency is not great. So you can trade off some of the parameters, but that's very roughly where it falls into. You can also look at mixed nets. Mixed nets provide very strong anonymity, but they are very bandwidth intense and they have many rounds, so they're also not very good in terms of latency requirements. And what we do kind of like in our current work is we trade off basically to have kind of okay bandwidth, but in exchange we get strong anonymity and very low latency. So this is kind of what we optimize for. So we optimize for 2 of the parameters and we pay some price in the 3rd parameter. Okay, so now let me explain you on a very high level how. We need to start.
I think it's okay.
Okay.
You can just keep running.
All right.
Yeah.
I need to put it in full screen or something. Great. Okay, so now that we kind of like outlined roughly what we want to do and also how it roughly kind of like compares in efficiency metrics to existing other approaches. Let's see what the high-level ideas are behind our system. So on a very high level, what we will do is we will have kind of like 3 groups of parties on the network. We will have the clients which have the messages that they would like to broadcast. We will have some aggregators, and we will have some servers. And in terms of trust assumptions, what we will have is that these aggregators are fully untrusted, they can all be malicious. This will not affect anonymity. And we will have some threshold honesty maliciousness assumption on the servers, meaning that some of the servers might be malicious, some of them might be honest, and depending on how the construction will be parameterized, we can tolerate different trade-offs between liveness and privacy. So kind of if you want to have as a maximum amount of privacy, then you can set the parameters so that even if all but 2 of the servers are corrupt, you still have privacy, but then liveness will suffer, and the other way around, you can kind of maximize for liveness, but then you need to reduce your privacy threshold. And the important thing that we will be doing, and for those who are familiar with ZipNet, is it will follow kind of like the line of what ZipNet does is we will be using TEs on the client side, and we will be using TEs on the server side. But importantly, we will be using them for liveness, not for anonymity. So what this means is that if TEs were to break, then the protocol will noticeably start failing because messages will not be delivered anymore. But TEs breaking will not affect anonymity of the messages. So the anonymity is a classical non-collusion assumption on the servers that says at least some servers are honest. Okay. So the starting point is a basic building block from secure computation called secure addition. And let's assume we have 3 clients, they have 3 messages. And let's assume that just one of these messages is not 0, okay? So in this case, we have these 3 messages. The first message is non-zero, and M2 and M3 are just 0. And what they can do is they can basically say, well, I take my message locally, M1, and I split it into 3 values such that the sum of those 3 values is my message M1, okay? This is what is called an additive secret sharing, but you could also make it a threshold secret sharing if you prefer this. And in this case, kind of like the important takeaway is that like now that I split M1 into these 3 pieces, unless you have all 3 pieces, you will not know what M1 is. And now what they will do is each party will send their first share to server 1, to their second share to server 2, and their third share to server 3. These servers can sum them up locally. And if I compute the sum of those revealed values, then I get kind of the sum of the 3 messages, but because only one of them is non-zero, I just get my first message. Okay, so like this is some kind of like splitting stuff into sums and then summing them in the right order. And what this guarantees you is that now the message that was non-zero was revealed, but the servers cannot see which client sent the message and which client sent the 0 message. And even if some of the clients are corrupt, they cannot see that either. Okay. So based on this very simple, very old building block, you can now build an anonymous broadcast system. So now what we do is, in the simple example, we said one party has a message and the other parties have zeros. So now we just assume we have a bunch of separate communication slots, and each party assigns their message to a random communication slot. So here they are kind of like viewed as an array. Now the first party says, I will broadcast my message on the second communication slot. And the other parties might pick some other slots. They do it independently, like completely at random. And now what we do is we basically do the same thing that we did for one slot. We now just do in parallel for all the slots at the same time. And because the message locations are completely random, we have anonymity because kind of like the location where the message appears is independent of who the original sender was. But this approach runs into one problem, and that is, well, each party independently randomly assigns their message to a slot. Maybe some parties will pick the same slot, in which case we kind of like, we have a collision. We don't really have one party having a message and everybody else having a 0. Okay, so now if we look at this and what we kind of like did with this addition, well, we really just added 3 vectors to get this vector at the bottom. And if we say we have a collision, then we effectively, in the bottom vector, somewhere we have kind of like added 2 messages together rather than just independently sending the messages. And what we now can do is we just do a trick. Well, we do it twice. So we kind of like run the protocol twice effectively. with different random choices. Now, in both of those, I might have collisions. But the nice thing is, well, if I look at these two arrays, then in this one, M2 did not result in a collision, so I can extract M2. And now if you assume that based on knowing what the message is, I can determine the location, maybe it's like a hash function of the message determines the location where the message is placed in these arrays, well, then I know that I can just remove it from the corresponding location in the second array. At this point, I had a collision in the bottom array, but now I resolved it by just deleting the message from the sum. And now it turns out that I can remove the other two messages from the bottom array. And in total, I extract all the messages that I want to send originally. And this is kind of like a simplified view of a more general data structure, which is called a stacked invertible Bloom filter. And in this example, I showed the two arrays being of the same size, but actually you can pick one to be somewhat proportional to the number of messages, and then each subsequent array to be like of half the size of the original one, so you get like a cascading smaller and smaller arrays, and you effectively kind of like get less than a factor 2 overhead in the number of slots that you need to send around, compared to just like assigning party I to slot I, which is like the minimum amount of communication you would need to do in this approach. Okay, so using this approach, now what happens is the parties basically share their messages, then the servers kind of like collect the messages that are intended for them, roughly speaking, and then they output kind of these like sum values which reveal the messages. Now, if we look on the left, that's a lot of messages. In particular, if we have a lot of servers, then kind of like the number of messages increases because each client sends one message per server. So one thing that we might want to do is we want to reduce the overhead, or like the bandwidth overhead, at least on the server side. And this is where the aggregators come into play. So now we have these aggregators, which are completely untrusted parties. And all they do is they take some of those messages and they just add them together on behalf of the servers. And after they have done this, they just forward that to the servers, and the servers then do some sort of decryption. I'm being fuzzy on how the decryption works and stuff, but like just trust me that it like works roughly like that. So the aggregators take a lot of messages, compress them into one small message for each server, and forward them to the servers, who now just need to do basically a decryption operation. Zooming in a little bit on this approach, and I forgot what comes next. Okay, so yeah, so this is authenticated by the clients. So they authenticate the messages that they send. But after the aggregators maul with the messages, they add them together. The resulting messages are not authenticated towards the service anymore. So this is a problem because now the aggregators can basically perform a denial of service attack on the servers because the server has no way of distinguishing good from bad messages. Zooming in a little bit more, if we look at just one aggregator, then effectively what we have is we have a bunch of authenticated messages under different keys. And what the aggregator would like to do is would like to compute the sum of the messages and get some kind of authentication tag for the sum of the messages. And what we kind of like show, that I won't have time to get into detail here, is that you can do this very efficiently by relying on some concepts of homomorphic hashing, which gives you exactly this kind of authentication tag with like good concrete performance. Yes, I don't know how fast I was, but I think fast. Oh, okay, yeah. So thank you. And if you have questions, then we have a lot of time for questions.
Thanks, Mark, for the great talk. Maybe I missed the part regarding T's, but what role do T's play in your protocol?
Right. So the role of the T is that I said, now I take every message and I put it into one random slot. If I wasn't running this in a TE, a malicious adversary could block the whole system by just like filling up all the slots with garbage. So the TE ensures that you really just put it into one slot, and the protocol remains live because at the end you can do the reconstruction of the messages. Yeah.
Any more questions?
What's the application or use case that Flashbots is thinking of for FlashNet?
So there are several different applications. One of them is for private block building. So you can do this twice. You can kind of once bid for building the block. And then in the second round, if you won the bid, then you can kind of like publish your block without revealing who you are.
Mark, you're from the academic cryptography community, and in doing this project, I know that you've been tailoring it to actually being useful in practice. I'm curious what that experience has been like. I think it might just be interesting to hear for the more academic crypto people in the audience.
So public key operations are already often a no-go in low latency situations. And as it turns out that AES and I calls are not an infinitely free resource. So there is a point in time where this is too inefficient, even if you just do AES calls. So you really need to optimize for both symmetric operations and public key operations. I think that's one. But I know it always depends on the settings. So here we really focus on the lowest latency type of application. So we want really the protocol to produce messages fast. And then these kind of things become an important issue.
Any more questions? All right, let's thank Mark. And we now have a coffee break until 3:50. So please come back for the final session then.
Do I need to turn it off?
Oh, we can actually
Feeding noise. I guess so.
Like the meta question, just in terms of what I should say.
Yes.
All right. Hey, everyone, if you could take your seats, we'll get started with the next session.
Zoom is gonna hate me if I stand here, right?
Yes. The visual field is extremely limited for the camera, so if you are behind the walls of this, you are good. All right, so kicking off our last session of the day, we'll have Joachim Neue, who is from A16Z.
Hey, everybody. Good to meet you. Thanks for having me. Thanks for organizing this. I'll be talking about consensus under adversary majority. This is joint work with my former colleagues Srivatsan and Nusret, and our postdoc Dionysus and our advisor David. If you want to check out the paper, you can see the QR code. So what does this talk about? Basically, an alternative title for this talk would be On the Role of Clients in Consensus. But before we can talk about this, I need to give you the disclaimer. This is not tax, investment, legal, business, or any other form of advice. I'm purely here for your entertainment. With that, let's get started. Let's talk about state machine replication consensus. That's a fancy way of saying blockchain. And one of the common questions we ask sort of on the distributed computing side of the problem is, what's the maximum fraction of adversary validators that we can tolerate so that the protocol remains secure? And I guess every user of the blockchain might have asked themselves that question. And if they go to Google and try to find out, then they find a bunch of different numbers. And that's a little odd. For example, maybe they find 33% for something called PBFT style protocols, things like Hot Stuff or Casper FFG. And then they continue Googling, and then they come across this other number, 49%. For Nakamoto consensus, like Bitcoin, Ouroboros, or even for synchronous PBFT protocols like synchronous hot stuff. And then maybe if they continue Googling, they find yet another number, which is 99%. For example, Vitalik had a blog post from a few years ago that sort of describes a protocol that is supposedly secure under adversary majority. So what's going on, right? Something's odd. Now you Google a little more, then you'll find, okay, the protocols from the first column are in a network model that we call partial synchrony. And the protocol from the second column are in a different network model called synchrony. Partial synchrony means, there could be periods of extended network delay, whereas synchrony means the network is sort of always well behaved. But then okay, so that rules out, one of the columns, right? But then you realize, hey, this 99% result somehow is also under synchrony. So now, we have Vitalik's blog post on the one hand, and on the other hand, for example, this theorem from some paper that I pulled up from Momosa and Ren from a few years ago that basically says, hey, 50% is like the maximum you can hope for, right? So then you're like, what the fuck? Like, what's going on here, right? So this is sort of the kind of misunderstanding, let's say, that we're trying to understand in this work. So let's dive in, right? So we're looking at a blockchain that receives transactions, and then there's a set of validators, right, that receive these transactions. And you may think, okay, the validators, their job is to run this consensus protocol, right? I've seen this guy talk before. There's always a log somewhere. There's always transactions that come in order. So, okay, these validators are outputting some log, right?
Okay. All right, we're back. Okay, the validators, right? Okay, and then somebody outputs these logs, right, of transactions. So what do we know about the validators? Validators, the characteristic of them is, we know them, right? Maybe except perhaps in like the proof of work setting, but at least in like all the proof of stake and permission kind of blockchains, we have a public key infrastructure for these nodes. We know who they are. Some of them may be malicious, but we have some sort of an assumption that, there's a threshold honesty assumption, right? Those are these numbers, 33%, 49%, 99%. Okay. Now, if you look at consensus flavors, right, this is so far what I've described so far, where the logs are output by the validators is a consensus flavor that we would call atomic or total order broadcast. And it's actually not what we do in blockchain. Okay. That's why the role of clients actually in blockchain is critical, and it changes the picture. Okay, so who are clients? Clients are parties that are not validators, but that follow the protocol's output, right? Think of, your wallet, merchants, block explorers, etc. Right? It's basically, another entity, right, that comes after the validators have sort of done their job, and it's actually the clients that output these logs. Okay, and the characteristics about clients is, for them, we don't know who they are. We don't have a public key infrastructure for clients. And some of them could also be malicious, but we also don't have any threshold honesty assumption on the clients. Okay, now this is the state machine replication kind of flavor of consensus, and this is the problem that we're after in consensus. And so this we need to understand, because that's gonna explain us some of the things of these like different numbers and seemingly contradictory things that we can find. Right? Now, once we have sort of this setup, right, here's a natural question, right? Like how do these clients behave? How should we model these clients? How are these clients connected, for example, to the validators, right? We mentioned briefly earlier that for the validators, we have some sort of a network model, right? Maybe synchronous, partially synchronous, asynchronous. How does that affect the clients, right? Do they also have some sort of a network model? What are clients able to do? So what we do in this work is precisely looking into client models. Okay, so for example, and that turns out to be what explains the difference between the 49% result and the 99% result. For example, the 49% result under Nakamoto consensus or synchronous BFT protocols is for what we can call sleepy silent clients. Whereas the 99% result is for what we can call always on communicating clients. What does that mean? Sleepy means that the clients in the system, they could go sort of asleep for extended periods of time, right? Or they could arrive to the system late, right? Maybe the blockchain was already running for 5 years, and then somebody decides to join the system, and now they sort of wake up, right? They see all the messages that happened in the last few years, but they weren't there when these things happened. Okay, so that's a sleepy client. In contrast to an always-on client, that's a client that's like, always, when your clients are always following the system, right? Similarly, what's a silent client? A silent clients are clients that are following what's going on in the system, but they're not able to send any messages. They're also not even able to sort of relay any messages, right? So they only have a kind of a receiving channel, right? They can read, but they cannot themselves sort of forward anything or send anything, in contrast to a communicating client, right? For example, our clients, if you run a full node, they're on the same kind of network that the validators are on, right? And so they take part in, for example, gossip protocols, right? If they get a message, they're also forwarding that message to other parties, right? So then, maybe it's a reasonable assumption that clients are actually communicating. But now that we have sort of these two dimensions, right, the client sleepiness and the communication model of the client, right, we can ask, okay, clearly consensus is easier if your clients are very alert, right, and if they can communicate. But now we can ask, okay, what happens in sort of the mixture models, right? What happens if we have always on and silent clients or sleepy communicating clients? So some results that we show in the paper is that for both of these cases, we get 49% resilience as well. So you only get the 99% resilience result if you have always on and communicating clients. Okay? Now I want to sort of burden you with one more conceptual kind of point, and then we can sort of understand the full results that you'll find in the paper, which is, so traditionally we would say consensus security means safety, which is that bad things don't happen, right? All clients confirm transactions in the same order. And liveness, which is good things do happen, which is that for every input transaction, if somebody wants to interact with the system, eventually that transaction gets confirmed by all the clients. Right? And then we looked at this resilience number earlier, right? We were asking ourselves, okay, what's the maximum resilience that we can hope for, right? It's the maximum fraction of adversary validators so that the protocol remains secure. Okay? So we have some sort of a consensus security is a set of properties that is parametric in this resilience parameter, right? And says, okay, whenever the fraction of adversary validators F is less than this resilience T, then we want these two properties. Now we can make the problem slightly more complicated, and we split this one resilience number into two, into a safety resilience and a liveness resilience. So instead of saying if the adversary is less than T, I want both of these properties, I now make the conditions sort of on a per property basis. Okay, I now have a consensus problem parametric in two parameters, right? And I want to have safety whenever F is less than TS, and I want to have liveness whenever F is less than TL. And then I can ask the question, okay, now a 2D kind of region opens up, right? What pairs of safety and liveness resiliences are achievable in each of these models that we looked at earlier, right? So this was sort of the results, the preliminary results based on the resilience, right? Looks like they're all the same except if you have always on and communicating clients. But actually, if you look at the region, the results look different. Okay, so something interesting seems to be happening in particular in the case of sleepy but communicating clients, right? So blue here means those are resilience pairs that are achievable, and red means those are resilience pairs that are not achievable. Okay? So what the numbers we've seen earlier, right, is the simple percentages, right? That's what you get when you take like a 45-degree diagonal into this diagram, right? And you try and find the point that has the last point that's in the blue region. Okay? So for Nakamoto and synchronous BFT protocols, like traditionally, right, that's like 49%. For the always-on communicating setting, that's the 99% result, right? And then we had these other results also at 49 and 49. Right? But what's interesting now is it seems that, and we show that with a new protocol, if we're in the sleepy communicating setting, then we can actually get 99% safety and 49% liveness. Or we could get 99% liveness and 49% safety. That is a bit surprising. In contrast, in the always on and silent setting, we get the same as in the sleepy silent setting. Okay. Maybe let me say one point of motivation, right? We're interested in this model in particular because sleepy clients is probably a reasonable assumption, right? It's probably on the margins, not reasonable to assume that all of your users are following the system at all points in time since the beginning of time, right? So sleepy is probably good, and communicating is probably also good. It's probably okay, right? Like that's how we're building the systems already. Maybe it doesn't work under all circumstances, but at least for a large set of systems right now, that is the case. So that's why we're particularly interested in those results. And I'm going to go give you sort of this protocol for sure, and then we're going to see where we are time-wise. Maybe we'll also do this one. Okay. So let's talk about the always safe protocol for sleepy communicating clients under Synchrony. Okay, Synchrony is our network model, nothing new there. I hope that this diagram isn't butchered. Okay, we want to build a consensus protocol. What's a consensus protocol? I think of it as a box, right? There's transactions sort of coming in. Then we describe some sort of box diagram, some sort of a flow chart, and then there's these logs of transactions coming out, right? And we want this box that we're going to build to have a liveness resilience of 49% and a safety resilience of 99%, 100%. Okay, so here's how we're going to do it. We start with any certifiable SMR protocol that works for 49%, 49%. Like pick, for example, synchronous hot stuff. Okay, you take the input transactions, you put that into that protocol. Okay, and then when there's an output of this protocol, right? Something's confirmed in this kind of protocol that's inside of this big box, right? The output is certifiable, so the output comes with some sort of a certificate saying yes, this was actually confirmed in this box. Okay, and then we're gonna gossip that. We're gonna let everybody know about this confirmation that we just saw, and then we're gonna wait a little bit, basically to see if anybody has any objections, or if we see anything that is sort of conflicting with the stuff that we just heard coming out of this protocol. And if not, then we're okay outputting. And if yes, then we don't output. Okay? Why does this work? Let's look at the liveness, right? So the liveness, for liveness, we need to show if the adversary is less than 49%, right? That's what we want from this box, right? Then transactions that come in here eventually make it, eventually make it out there, right? So why is that the case? Maybe can people see my mouse works, right? That is the case because, okay, if F is less than 49%, right, transactions that come into this protocol make it to the output log, simply because that protocol is now live, right? Then we're going to gossip it. That doesn't do anything to the transaction, right? We still have that transaction. And then we'll wait delta time, okay? And then after delta time, we output that transaction unless we see a conflict, okay? If we don't see a conflict, we're good, right? Because the transaction made it out. That's all that we wanted for liveness. If we do see a conflict, what does that mean? That means that this protocol is unsafe. But this protocol has a safety resilience of 49%. So this means that the adversary is stronger than 49%. This means that we don't have to guarantee liveness anymore, right? So then it's okay not to output. Okay, so that's the liveness proof. Here's a safety proof, right? We want to show that if two honest nodes output transaction logs, right, then these logs are consistent. So let's say there is a node that at time t outputs something, right? Then they do that because after waiting for delta time, right? That means, okay, that node has seen that log and gossiped that log delta time ago, right? And that means that shortly thereafter, everybody sees that log because of synchrony, and so nobody will output anything conflicting anymore. And that's the safety proof. And it's kind of interesting because once we realized this, we spoke. My co-author spoke a bit to folks in the Cosmos ecosystem, and what they heard is like, yeah, we don't have safety violations because our protocols basically stop before they output unsafe stuff, right? If they see unsafe things, the mechanism that they have is somewhat similar to this. They don't do this extra delta weight. You do need to do the extra delta weight. If you don't do this, then you don't get this safety property. But it's actually somewhat close to what's going on in this protocol. Okay, how are we doing on time? We're good? Okay. So then let's talk about the always live protocol. Same setting, right? Sleepy communicating clients under synchrony. We want to build this box that is always live. So it has a liveness resilience of, say, 100% or 99%, and a safety resilience of 49%. Here's how we're going to do it. Every transaction that comes in, we're first going to let everybody else know about it, right? We'll gossip it. And then we're going to put it into a regular 49% resilience hot stuff. Say, for example, synchronous hot stuff, okay? At the same time, we sort of take note of the fact that we have just received this transaction, right? And we'll write down at what point in time we have seen this transaction. We'll basically put it to the side, put it into a queue of pending transactions, okay? And let these transactions sit there for delta plus the confirmation time of this protocol. Okay, and then once something comes out of this protocol, we're gonna look at our queue here, right, and identify basically all the transactions for which we have seen them delta plus the confirmation time of this protocol time ago, but they're still not in this output log. Okay, these are like overdue pending transactions, basically. These are transactions that we saw a long time ago for the first time, and still they haven't been confirmed, right? And then what we're gonna do is we'll take the output log of this protocol, and we're just gonna insert these other transactions somewhere. We don't care. We'll just output them also into the output. Okay. Why is this live? Well, if you put any transaction into here, right? Now we need to show that this is live no matter how strong the adversary is, right? Why is this live? You put any transaction in here, right? No later than like delta plus tconf later, right? That transaction will sort of pass on sort of through this waiting box, right? And then either that transaction has been included in the output log of this protocol, right? In which case, fine, we're outputting this, right? The transaction is confirmed. Or it has not, in which case we're just gonna insert it into the output log and confirm it regardless. Okay, so every transaction definitely makes it into the output log. What about the safety property? Suppose f is less than 49%, right? Otherwise we don't have to care about safety, right? That means that this box pi int here is safe and live, and it has some worst case confirmation time, tconf. Okay, so there should not be, if f is less than 49%, there can never be a transaction that is overdue and pending, right? That sort of comes out of here, but is still not included in here, right? Because this protocol is live. So then this injection operation here, right, does do nothing, right? Because this set is basically empty, right? So then the output log is the log that comes out of this sub-protocol here, right? And that protocol is safe, so we're good. So that concludes the safety proof. Okay, those are the two sort of protocols that I wanted to show you. Now I'm gonna zoom one step out, right? So we have looked at client models, right? We've specifically looked at sleepy client and always on client. We've looked at silent clients and communicating clients. So far, we've operated in the synchronous network model, right? There's also the partially synchronous network model. And so far, we've assumed that the validators, the ones that are running the system, they're always online, okay? They're not sleepy. But there's another model where you can look at sleepy validators. Maybe the validators also come and go, right? And so in addition to these two client models, we now also have in addition to these two dimensions of the client models, we now also have two dimensions sort of for the validators, or for the network model and the validator model, right? So we get, woohoo, 16 different models, right? That are all in relation to each other. And we can plot sort of the safety and liveness region that is achievable for each of these settings, and that's what we do basically in the paper. So what we've talked about in the talk today is this row here, right? It's for the synchronous always-on validator setting, and we've looked at the different client models. Interestingly, if you go to the synchronous and sleepy validator setting, somehow this always safe protocol doesn't work anymore. And the reason why is, remember, we made the assumption that we use a component protocol that is certifiable, and certifiable protocols don't exist if we have sleepy validators. And so that is why that protocol breaks down. It turns out the other protocol continues to work. And then the last point I want to make is that under partial synchrony, interestingly, under partial synchrony with sleepy validators, everything's impossible. We knew that before. Under partial synchrony with always-on validators, interestingly, the results do not depend on the client model, and perhaps that's some explanation for why that is a model that people like to work with, and why people haven't focused on this aspect before. So partial synchrony is robust to client models. And that basically concludes the talk. Check out the paper if you want to know more, and I'm happy to chat.
Questions?
I can just make a short comment. It sort of reminded me, I wrote a note there for it. I don't know if you're familiar with like the really early Bitcoin papers, but back in the day in like 2011 or 2011, you could send a transaction on the network and within 10 seconds, you'd have high confidence that there's no double spends and it's guaranteed to get into the next block because each node had a relay rule where if I hear a transaction, I don't relay as double spend. And Christian Decker had a paper on that that analyzed the confidence interval of that system. So it reminded me of the always safe one, to be honest, because I was like, oh, you basically just wait around for like 10 seconds, no double spends, then everyone's synchronized, and we're all going to assume this is going to get confirmed.
Interesting. Yeah, I'm not aware of that paper, but yeah, interesting. 2012 or something. Cool.
Any other?
So what about the asynchronous model? So how do you think about that if, let's say, you're going for a specific protocol like trade-off here that looks good? Does it also open maybe some attack vector with someone DOSing certain network links or something like that? Or do these things kind of stay robust?
Good. We haven't really looked here at kind of the asynchronous model. My hunch is that it'll basically look like the partially synchronous model. So it'll probably, you will not see much dependence sort of on the client model, and you'll get this same trade-off curve probably as you get on the partial synchrony.
Okay, that makes sense. Thanks.
Could you explain what breaks about the always live protocol in the case that we replace the communicating client with a silent one? Like what specifically breaks about this protocol?
You're asking about this protocol in which network model you want to go here? Here? I don't know it off the top of my head. No, I don't know off the top of my head.
Yeah, I'm just making, I guess, your answer. I think that if the client is not communicating, then it cannot submit any kind of proof that something went wrong. So yeah, then the safety guarantees go away because basically, yeah.
Interested in the always live protocol, right? I think that what will happen, I think, is that the transaction, like your clients are sleepy now, so they may just not be around and may not hear that information. No, never mind. Forget about it.
I think they really cannot like forward to honest validators the fact that they've received, let's say, conflicting views of the chain, and that yeah.
That isn't the always safe protocol, right? Yeah, that is why this point doesn't work.
Yeah, yeah, exactly. Oh, so you were asking? Okay. Yeah, yeah, just that.
All right, let's thank our speaker.
Guard Media.
Okay, for our final speaker of the day, we have Pranav Garamidi, who's a researcher at A16Z.
Hey, thanks for sticking around to the last talk of the day. Super excited to present this work on multiple concurrent leaders. You might have also heard this referred to as multiple concurrent proposers or previously BRAID. And so happy to kind of have a formal kind of consensus model of how to approach this. And yeah, let's get into it. And so first, kind of all the important disclosures, non-investment advice, just a research talk, yada, yada. Okay, so let's start with the why of why are we interested in this problem. And so generally, we want to show is that protocols where there's a single leader kind of very naturally have this monopoly power that leads to poor on-chain kind of market structure. And this is just bad for various DeFi applications and so on. And so in particular, let's consider a first price auction to kind of really see where the single leader setting makes things not great. And so let's assume that there's some item that has this kind of expected value according to this mu t. So there's going to be some auction where we're selling this kind of blue item. At any point in time t, the expected value of the item is going to follow this distribution. And so let's say kind of the auction takes place over this interval of length kind of big T. And let's assume there's just two bidders. So there's Alice and Bob. In particular, we're going to assume Bob has some kind of enshrined latency advantage. And so it might be the case here that Bob is, for example, the proposer for a slot, and Alice is somebody else who's just trying to submit their bid. And so in that case, kind of both Alice and Bob submit some bids that are kind of close to this expectation, and the auction clears reasonable revenue. And we'll see kind of two examples of why this may not happen in kind of a normal blockchain setting. And so the first one is that if Bob has the power to censor Alice, then the auction is very easy for Bob to win, right? Bob is just going to not include Alice's bid. Bob will include his own bid of epsilon. And in particular, he'll win the auction for basically nothing, right? So this is obviously not great. Now this auction, instead of raising value close to this expectation, instead it's going to get this epsilon value, and Alice has no way to be competitive. And so we definitely need that our protocol satisfies some form of censorship resistance. Now, the second case that's also really bad is that even if Bob can't censor Alice's bid, if Bob can just see Alice's bid, we also have a problem. So let's say Alice bids, some bid BA, and Bob sees this. And now Bob has this very simple strategy, right? So Bob has this latency advantage. He gets to move a bit after. And so when it's Bob's turn to bid, if he looks at the current signal of this mu t, if it's bigger than Alice's bid, Bob will simply bid epsilon more than what Alice submitted. And otherwise, if the signal is below Alice's bid, then Bob's going to bid 0. And it turns out that this means that Alice always gets negative utility and expectation, right? And so why is this? Well, the only time Alice wins is when the signal, when Bob bids, is less than Alice's bid. So that means Alice only bids when the expected value of V is actually less than the bid Alice submitted, right? And so whenever the actual expectation goes above Alice's bid, she's always going to lose. And so in the setting, instead of bidding at all, Alice would rather just leave the auction, right? If she's only winning the item when she's losing money, she'd rather just not bid at all. And so then if Alice leaves, the auction is only left with Bob. And we're in a setting where, again, Bob can win with a negligible bid, and the auction kind of fully unravels. And so just to hammer this point home, if Bob can either censor Alice's bid or see Alice's bid, the auction just completely unravels and generates no revenue, making it basically unusable. And while we're talking about a simple example of a first price auction, like really you can reduce many DeFi protocols to what looks like a first price auction. And while the actual realized effects might not be as extreme as what I described, definitely if things like this can happen, of censoring some set of bidders or seeing some information, all of these applications become much harder to run on chain, right? So it's just running on-chain RFQs, liquidations, order books, any type of lever mitigation that relies on auctions. I think these are all applications that we'd really like to see happen on the L1. We'd really like to see happen kind of off-chain or on-chain. And today require kind of off-chain protocols to really run these things efficiently, just to deal with this informational problem, censorship problem. And so this talk's really going to be getting at like how can we redesign the underlying L1 infrastructure to be able to support applications like this. And so there's really two key properties that we're going to require. And so the first one is what we call selective short-term censorship resistance. And this basically says that for all transactions submitted to an honest node, they must be included immediately in the next slot, unless the next slot is completely skipped, right? And so this is it's a bit awkward compared to what you might normally think of central persistence here. And the caveat of having the slot be skipped is there might be the case of like just some leader just goes offline, right? And so it's somewhat hard to formalize this, but in some sense, this is kind of the best you can do. Kind of the way to remove allowing the slot to be skipped kind of just adds lots of latency by default and has some other kind of undesirable economic properties. And so really, we're kind of OK with this. If the slot is entirely skipped, that means nobody got a bid in, right? So even Bob doesn't get his bid in. And that means everybody has the opportunity to submit a new bid in the next slot. And so for the applications we're looking at, this feels like an acceptable level of censorship resistance. So that's the first point. And the second point is kind of a traditional kind of privacy type notion we call hiding, which basically says that an adversary can't learn anything about transaction contents before they're confirmed, right? And so this will be getting at preventing Bob from seeing Alice's bid. So you want the protocol to be that nobody's going to see other transactions that they didn't submit until kind of the protocol is basically over and the transactions are already confirmed. OK, so that was all the why. Now we're going to get into how we do this. So it's going to be this kind of 4-stage protocol. So we're going to go phase by phase here and talk a lot more in depth about how this works. But this is kind of the overall big picture. And so the first phase is going to be what we call the proposal phase. And so basically every slot, there's going to be a elected set of proposers. In particular, you can actually imagine literally every node in the protocol being a proposer for this talk. And so basically every proposer is going to gather a batch of transactions. And then basically once they have their batch, at this time kind of TS minus 2 delta, which is basically, we'll get into what that means in a bit. But it's basically just saying kind of 2 delta before the consensus properly starts. The proposer is going to secret share their batch contents amongst this relay committee, right? So kind of every slot will have a set of proposers, will have a set of relays that are both kind of sampled in some way. And yes, the proposer will secret share all the batch contents among the relays. We'll then have what we call the relay phase, where basically relays at a certain deadline stop accepting shares from proposers, and they make an attestation of kind of everyone they've heard about, and they send this attestation to the consensus leader. Very importantly, the relays do not send any of the shares. They only send an attestation saying of what identities they heard about. And then we have the consensus phase. And so you can think of our multi-concurrent leader protocol as kind of a gadget that just depends on any standard PBFT style protocol. And so we're going to take that as a black box, right? So you can plug in here hot stuff, alpenglow, simplex, whatever you want. This is just kind of a generic gadget that takes this underlying consensus as a black box. So kind of in this phase, the leader will collect all these attestations, and they'll propose a block that is just the attestations to the consensus protocol. And then finally, there's a reconstruction phase of basically once this consensus protocol has confirmed this block of attestations, this implicitly tells all the nodes what batches are available to be reconstructed. And so at this time, once consensus is over, all the relays will look at the outputs. And basically, once they see those outputs, then they'll broadcast all the shares they've been custodying. And then nodes can reconstruct the batch contents and reconstruct the log from there. So let's get into each of these phases in more detail. And before that, let's start kind of the higher level model we're in. And so it's going to be a partially synchronous network. We'll kind of parameterize by this network delay delta. So standard thing, after GST, all messages get confirmed or delivered in some time in delta. I will caveat that our economic properties will only hold during synchrony and not during partial synchrony. Or in particular, censorship resistance will only hold during synchrony and not during partial synchrony. The hiding property will kind of always hold. But to some extent, kind of before you hit the synchronous portion, you can't hope to have kind of all the transactions definitely be delivered. We're going to take an adversary that has static corruption and only has n over 5 nodes that are corrupted, right? So this is a bit different than standard kind of PBFT protocols, where it's n over 3. So our protocol can only tolerate n over 5 to get kind of the economic properties we want. We're going to assume the protocol operates in these kind of fixed slots. And then the main modeling thing is we will take this kind of atomic broadcast protocol, which is what this PyAB stands for, as some black box protocol. We're going to assume it comes with a leader sequence that might be whatever randomly sampled. And we're going to assume that we kind of have these fixed slot times TS, right? So we're going to assume that all the nodes have synchronized clocks and kind of know these times. And the two things we'll take use of is this input function, where the leader is allowed to make a proposal, and this output function, basically, which says that once transactions are confirmed by the consensus protocol, nodes see this output, and then they know that those transactions have been confirmed. So That's the model. And there's also another thing we use that we call hiding erasure correcting codes. And so these are very similar to like the standard erasure correcting codes you all are probably familiar with. But we need this additional property that too few shares don't reveal anything about the original message, right? And so this is what we're going to use to get this hiding property. And so in particular, with a normal kind of error correcting code, you might actually learn some information from a few of the shares, even if you can't fully reconstruct. And so we're going to have to make a slight modification to this construction to make sure that's not the case. And so it's going to be parameterized by 3 numbers, k, t, and n, where we're going to have some message n just being coded into n shares. And like this is the unique property to the heck, that any set of t shares reveals nothing about m in an information theoretic sense, but any set of k plus t shares can fully reconstruct m, right? So if you have any k plus t shares, you know what m is, but anything that's t or less, you learn nothing about what the message is. And you can actually construct this fairly easily, right? So you can actually take a standard Reed-Solomon code where you make the slight addition of we basically just append these random field elements to the original message before we apply the standard encoding function from Reed-Solomon code. So it's not too hard to actually make this. Cool. So let's start with the proposal phase. So I'll go through this a bit quick, and then I'll kind of go through it in pictures to make it a bit easier to understand. But basically, for every node, they're going to collect these transactions into a batch. They're going to erasure code those transactions. And so in particular, kind of along with our adversary having only n over 5 kind of corrupted nodes, we're going to assume both k and t are n over 5. So this means with n over 5 or less shares, you learn nothing. But with 2 n over 5 of the shares, you can reconstruct the original message. Okay, and then once p is kind of erasure coded this message, their batch, they're going to commit to this vector of shares, which we're going to denote as capital C. And then for every single relay, the node is going to create an opening proof for that specific share for that relay to the commitment they made. And for each relay, they're only going to send 1 share along with opening proof and the commitment. Okay, so what does this look like? So we have these set of transactions in these boxes. Here we have 4 proposers. The transactions will submit to whatever various proposers. And then basically every proposer will come up with some batch, and they're going to erasure code their batch into these C vectors. Okay, so now you have these proposers. They've erasure coded their batches. You have these kind of vectors of shares. And now each proposer is going to send 1 of their shares to each of the relays here, right? So the C11 only goes to relay 1, C12 only goes to relay 2, C13 only goes to relay 3, and so forth, right? So at the end of the day here, each of these relays should have 1 share from each honest proposer, basically. And yeah, so this happens at time t minus 2 delta. And so during synchrony, if all the proposers are honest and releasing at this time, all of the relays should get their shares by this time ts minus delta. And so that brings us into the relay phase. Okay, so now for the relay phase, for every received shred or share, basically the relay is going to first just check the opening proof and signature, right? They want to make sure that the share actually matches the commitment that the proposer sent them. And then if that looks good, they're going to create this attestation. And then they're going to store the shred for potentially dispersing it later. But they're basically just going to collect this vector of attestations for everything they heard about, and then send this to the leader, right? So basically at this time, ts minus delta, take every shred you've heard about. If each one of them looks valid, create a vector of them, of basically signing the commitments and nothing else, right? So importantly, the attestations here only have the vector commitment and the signatures, nothing about the actual shares themselves. Okay, yeah, and so basically we'll have a similar thing before. Each of these relays makes their attestation vector and they send it to the leader. Okay, cool. Now the consensus phase is very simple. So the leader has now collected all of these vectors of attestations from each of the relays. They're going to make a block that's just everything they've heard. And now, very importantly, to get our kind of desired censorship resistance, we're going to require the block to include at least 4/5 of these kind of big N relays, right? So a leader cannot cherry pick the handful of their favorite relays and just include those. They really need to include kind of almost all the relays. And so this will be like very important for getting the censorship resistance proof later. And then the leader, once they've done this, is going to just simply call the input function of the underlying consensus protocol and basically propose this as a block in that protocol semantics. Cool. And yeah, so it just looks like this. Leader makes a block with all these attestations they receive from the relays, and then simply have this as an input to the consensus protocol. OK, great. And now this is probably the most tricky part of the protocol. It's the reconstruction phase. And so if the protocol, the consensus protocol, the atomic broadcast protocol, just kind of outputs spot, which is basically an empty block, then all of them have a very easy job. They just output an empty slot, and they go on to the next one. Nothing really happens. And so this is the selective censorship part, where it's OK if the slot's skipped entirely and literally nothing is confirmed. And so that can happen here. And so otherwise, if the protocol does output a block that kind of passed through consensus that is a block of valid attestations, then all of the nodes, you're going to check all the signatures and double check this condition that at least the block is at least 4/5 of the relay attestations. And you can imagine this being in the consensus protocol itself. You can imagine the consensus protocol here doesn't know the semantics of what we're doing in our protocol. And so the nodes have to do this kind of double checking to make sure that the block really is valid according to the MCL gadget. OK, and so given that the block is valid, it has enough of these relay attestations, now basically all the nodes are going to look for what batches should be available, right? And by a batch being available, that means that it should be expected that enough relays heard about shares that everybody can reconstruct these batches. And so in particular, we're going to say if a batch is attested to by at least 3/5 of the relays, then we know, also with kind of the commitments being consistent across those relays, then we're going to consider that batch as available, right? And so for some looking forward to where this 3/5 is coming from, we know that 2/5 of the relays are enough to reconstruct. And so if f of these guys are Byzantine, which is only, you're assuming is at most 1/5, then we know that if at least 3/5 of the relays have kind of committed to this block, then we know that we're definitely going to be able to reconstruct the batch later on. And so let's just say that given the block is B, that the set of available batches is defined by this function P of B. OK, cool. So for part 2, relays have a very simple strategy. They're going to say, OK, I'm going to look at all the batches that are available. And for anything that's available, I'm going to broadcast my shares for those batches to all the other nodes in the network. And then all the nodes, basically, now we're going to just check the opening proofs, make sure all these shreds look correct, and then just kind of call the decode function from our erasure code, reconstruct the batches, and then to actually output or decide the log, they're going to simply take the union of all transactions in the batches, sort them by decreasing priority fee, and then add them to their log. Again, so in pictures, here's what it looks like. The consensus protocol is going to make some output of determining a block. It'll be sent to all the relays and all the nodes, which are the circles in blue. All the relays, when they see this, are going to basically decide what shreds to disseminate based on what things are available. And then the nodes will reconstruct those corresponding batches and then put that into their corresponding log. OK, so just as a high level now, like kind of going back to this big picture, just kind of reviewing the whole thing one more time. Proposers gather transactions. They make batches. They erasure code those batches into shreds. They submit those shreds to relays. Those relays make attestations. They send that to the leader. Then we run our favorite atomic broadcast consensus protocol. That protocol is going to output something that's going to basically decide what batches are available. The relays will listen to that and then gossip all of their shreds. And then clients reconstruct everything that they can. And we finally get this output log. So that's the entire protocol very quickly. And now let's see why it actually gets us the economic properties we wanted it to. And so there's really 2 ways in this protocol for an adversary to censor a transaction. So one, the adversary can control enough relays and have them each just claim to censor a proposer, basically, by just not attesting that they've seen kind of a batch. And then secondly, you might think that the Byzantine consensus leader maybe will purposely leave out enough relay attestations so that a batch is not considered available. And so we'll show that actually if the adversary controls less than 1/5 of the relays, neither of these attacks will work, and we'll kind of be safe and know that no adversary can censor a transaction without causing the entire slot to be skipped. So let's walk through this argument kind of closely. So let's consider a transaction sent to an honest node P, and so we're going to want to make sure this transaction is definitely included or the entire slot is skipped. So since P is honest, P will include the transaction in their batch. And so this is kind of fully from the consensus lens, not from the economics lens. So there's very natural concerns. So what if their block is full? And what are the fee mechanism? For the purposes of this work, we're assuming that the blocks have infinite size, and it's definitely useful follow-up work to kind of relax that assumption. But for now, assume the blocks have infinite size, and so that P is free to include the transaction if they wish to. And then so P will make this batch MP. They'll send all the shreds to the relays. Now, every honest relay is going to attest to receiving this shred. It'll be on time. So again, this property is only going to hold in the synchronous portion of the partially synchronous network. So everything, all these messages should be arriving on time when they're sent by the honest parties. So every honest relay will attest to receiving the shred. And now either the slot that the consensus leader makes from all these attestations, so either the slot's totally skipped or the leader made a valid block, right? So if the leader made a valid block, then by our construction, this block must include at least 4/5 of these relay attestations, right? So, okay, so either the slot was skipped, and we're happy satisfying our protocol, the slot can be skipped sometimes, or we have a block now with 4/5 of these attestations. And remember now we had f is less than 1/5. So in particular, that means of those 4/5 attestations, at least 3/5 of them must be from honest relays. And remember, our threshold for availability was 3/5. And so since our honest proposer got attestations from every honest relay, we know that this batch will be considered available. And now all the honest relays will broadcast their shreds. And remember, we only need 2/5 of the relay shreds to reconstruct the block. And so we will get that kind of every node will reconstruct this batch. And in particular, every transaction in the batch will be confirmed for this slot, right? So this kind of shows that an adversary either has to skip the entire slot or include everything submitted by an honest node in this setting. Cool, let's go into hiding now. And so the important fact here is that once the consensus phase is over, reconstruction is a deterministic function of what was proposed, right? So deciding what's available is just a function, like a deterministic function of the block. And so in particular, the adversary has no power to insert new transactions or in any way really affect the state after the consensus phase ends. At that point, it's too late for them to do anything. And so really all we need to show for our hiding property is that until the end of the consensus phase, the adversary learns nothing about batches that they did not propose themselves. Okay, and so before a batch is confirmed by the consensus protocol, what do people know? Well, if a node is a relay, it has one shred and this vector commitment. If there is not a relay, they only have the vector commitment, right? This is the only information that any honest node will see during the run of the protocol before the reconstruction phase. And in particular, by the construction of the heck, we know that an adversary with less than 1/5 of the relays an adversary of less than 1/5 of the relays now will only have at most 1/5 of the shreds, right? Because if they have they get one shred per relay they control, so they have 1/5 of the shreds and this vector commitment. And by construction of the heck, we basically know this is not enough information for a computationally bound adversary to learn anything about the batch contents, right? So this basically, by how we designed the erasure code, we know that the adversary just can't have enough information to really learn anything about a batch until consensus is over, at which point it's too late. The kind of the execution of the block is kind of baked in, and they can't, for example, see a bid and submit a bid as a function of that bid. Okay, great. So kind of wrapping up in conclusion, as the why of this, we know that many DeFi protocols are going to need the underlying infrastructure to be both censorship resistant and not lack or leak transaction details during block production. And we think MCL achieves these two properties. And so how do we do that in kind of one sentence? Basically, very importantly, we split up block production amongst multiple parties. So multiple people have the power to include a transaction in a slot. And then we kind of coordinated this using relays as a timing committee and also as a secret sharing committee at the same time to get kind of the two properties we wanted for censorship resistance and for this hiding property. Yeah, and that's it. So thanks.
Yeah, just a quick question. Is the relay depth homogeneous across the network, or is there an efficiency with which data flows through the relays?
I'm not sure I understood the question.
Does all of the data go through the same number of hops before it hits the block?
Yeah, right.
validators?
So the data flow will look like a transaction hits a proposer. The proposer erasure codes their batch, and then they send a share to each relay. Then the relay sends one thing to the consensus server.
I know you mentioned that this is more about the consensus rather than economic incentives, but I was wondering that since a pretty critical component of the block construction and reconstruction is now on the relays, do they have direct incentives to act in a good way? Is that part of the proposal going forward, or will we just assume that they won't act maliciously?
Yeah, so I'd say I would stop short of calling this a proposal right now. So I'd say right now it really is just working out the consensus details of at least now in theory we could do something. So that it's an excellent question. And so I don't have an answer right now. I think this is one of the things we're working on of really, so now that the consensus part feels kind of set, we're working on kind of the transaction mechanism, the incentives, like kind of how do you do rewards at the consensus layer for just voting and all this type of stuff. And so we have ideas around how we might do this that incentivize relays to kind of broadcast everything in a timely manner. And it helps that kind of any individual relay is not that pivotal, right? Unless you get sufficiently many relays, then like there's not too much benefit from one relay censoring or something like this. But it definitely is like a super valid concern. And I think making this into an actual proposal definitely requires fully working out those details. So I'd say stay tuned. Hope you have an answer soon.
Okay, last question.
Thanks, Pranav. Do you have any guess as to what might prevent the 20% threshold to being 33%?
No, I mean, so one thing here, right? So like, today Alpenglow also has a 20% Byzantine threshold for safety. This is one of those things. So you can tune this 20% to be higher at the cost of some other things in the protocol. So, and some of these things are like, maybe you don't want strict hiding, maybe you're fine with hiding with reasonable probability, and you can kind of tune these things different ways. And so if you're uncomfortable with 20%, there's some things that can still be done there. Yeah, there's not a super strong argument for why 20% is the level. To some extent, I think the problem is just, so I didn't talk about this at all in this work, but there are some lower bounds you can make of like the highest adversary resilience you might want that can still achieve these properties. And so, yeah, it's going to depend on the setting. The hope is you can design the incentives so that everybody is incentivized to just follow the protocol and that gathering 30% wouldn't be profitable. But it's always hard to say how things work out in practice.
All right, let's thank Pranav. That concludes the talks for today. So we're going to take 5 minutes to set up for the panel. So there's additional water now back by the coffee station. Grab water, grab coffee, and we're going to start in 5 minutes.
Test. Test. Yeah, yeah.
Yeah.
Figure it out.
And then
We will build the block just in time for this transaction.
Multiple concurrent proposers.
Oh my God, yeah. CL, yeah. But wasn't there just one leader? Did I miss that?
In the protocol just now?
Yeah.
But there were many relays, which I sort of.
Yeah, but there was literally, it was called multi-concurrent leader, and there was, in the diagram, there was one leader. Single leader.
Yes, but
But that seems not
I think
correct.
it's just a definitional naming issue.
Yeah, but I'm just saying, like, what do you want?
I mean, ask the backup.
That's my question. Why was there one leader in the protocol?
Yeah, so MCP got taken by the AI people, and so they.
Oh, okay, that's why. I see.
No, it's annoying. I was trying to fight against MCL.
Yeah.
The powers that be market.
hey everyone, we're going to get started for the panel. If you want to take a seat, please.
It's also annoying. Wasn't for the AI people.
Yeah, that's fair. Honestly, good answer. Everyone, let's centralize ourselves. Woo! Central.
Censored.
Yeah.
Okay, so we're going to get the panel started. So I will introduce the moderator and then he can introduce the panelists. So our moderator today is Phil Diane from Flashbots, and the topic of the panel is geographic decentralization.
Sounds good. Yes. Hi, everyone. I am Phil Diane. Hopefully you are all as tired as I am. So we have a bunch of very fun, spicy questions today about something I think is very important, geographic decentralization, and a few really impressive panelists. We have John, Pranav, and Quintus here with us today, and I'm going to let them introduce their own work because they probably know more about it than I do. So yeah, maybe we can go down the line, and if everyone takes a minute to just say who they are, what they're working on, and maybe if they want something about geo decentralization that's relevant to their work. You want to go first, John?
Sure. So, hi everyone. I'm John, one of the engineers at Celestia Labs. We're building Celestia, which is blockchain, I guess you could say. It is a blockchain that specializes in data availability. Therefore, it essentially optimizes and only does one particular task that blockchains do. So it moves execution up into higher layers, only does data availability, and therefore it can be maximally efficient and therefore maximally performant with the highest throughput, lowest latency, what have you, and verifiability because it focuses only on this one task of blockchains. So that's basically Celestia in a nutshell.
Hey, I'm Pranav. I'm a researcher at A16Z. Kind of broadly work on mechanism design, game theory type problems, lots of work on transaction fee mechanisms, MEV, all that type of stuff. So yeah, anything basically infrastructure related and game theory related, I try to think about.
I'm Quintus. I work at Flashbots Research, and I have been doing two things related to geographic decentralization. One is trying to get other people to do research on geographic decentralization, and so I'm aware of those conversations. And the other is working on sort of improving trusted hardware or secure hardware, getting better TEs, which I would argue is a technology that promotes geographic decentralization.
Oh, yo. Oh, that was so good. All right. Let me write that down to sidebar that. But first, I wanna do a context setting. So let's set the scene. Many people have many different definitions of decentralization, right? It's this kind of abstract kind of hopium we have in crypto that resists all science and definition. So I'm curious what you all think about when you think about geographic decentralization. What is your favorite definition? I'm going to try an anarchy session here where I'll just let whoever wants to speak grab the mic and then call on whoever hasn't spoken because I think I want to hear from everyone.
I can take a stab. Yeah, so I don't have a great formal definition, but like in some sense, you can think of like we have the world where information comes out of in different spots, and then we have nodes who are located in spots in the world. And so in some very loose sense, if the distance like, I don't know, like average pairwise distance or like, distance between 2/3 of the nodes or something like this is very small, you're not very geographically centralized. If that distance is like quite big in proportion to how big the world is, then you look better. But I don't have a great one-line answer.
Sure. So I want to preface this with that I would not try to define geographic decentralization or geo-decentralization, just like I wouldn't try to say that, or claim that I'm providing a definition of decentralization, because that's just contributing to the problem where everyone has a different definition. But I would say my opinion. So my opinion is that geographic decentralization is a metric that has a few parameters. One of them would be physical distance between the various nodes in the network, basically what Pranav said. And the other one would be some metric around distributedness of various jurisdictions. Because, the USA, for example, this country is quite large physically, substantially larger than, I don't know, let's say France. So just because you have, one node on the West Coast and one node on the East Coast, is that really more geographically decentralized than if you have a node in Paris and a node in Berlin, right? The node in Paris and Berlin are closer together, but they're in two different jurisdictions. So you kind of have, in my opinion, when dealing with this, you have to take both the physical distance and also the jurisdictional distance, if you want to call it that, into account.
Yeah, I would mostly agree with that. Only reframing I might add on to that is one that there are many dimensions of diversity which we look for, because we rely on diversity for the sort of neutrality properties that we're interested in, and geography is one dimension, and there are other ones like just entities participating and their views on what should be included, etc. But also, I think in these discussions we tend to look at like static definitions, where we say, oh, is this network geographically decentralized today? And that's an interesting question, but probably a more interesting one is like, is a protocol designed to promote decentralization? How does it tend over time? And we can ask this about markets in general. Like if we have some market that we use to select validators or whatever, does this tend to monopoly? Can we design this market so that it somehow involves more actors over time?
Super interesting. By the way, let me disclaim for the audience that I have, as many of you know, very strong opinions on many of these things that I'll be keeping to myself today. So we're going to be neutrally moderating. How fun. All right. So yeah, Tina's booing me. That's fine. She does that a lot. Yeah. So that's a perfect segue, I think, Quintus. One thing you just said, and that we've kind of covered broadly, is like there's many different angles to slice this. There's also this economic piece, this jurisdictional piece. There's also a distance piece. So one question, if we have all of these kind of elements of diversity that we want in our system, then why are we having this panel in San Francisco? That is the first question that I wrote down. But maybe on a more serious note, like, how do we think about also where these systems actually get built and like the power in crypto? And does that relate to these kind of technical definitions we're thinking about? And what can we as people sitting in SF actually do about this? It's a hard question.
So this thing on?
It looks on now.
Testing. Is this on?
Yeah.
Okay, now it's on. Yeah. So, well, first of all, to answer your first question is, I don't know, you're the organizer, so you tell us why it's in San Francisco. But jokes aside, I think this, to kind of be politically correct, but also talk about the politics, is that talking about this kind of stuff, let's say a year ago in San Francisco, maybe you could do it, but maybe there'll be fewer participants that could participate in this kind of thing. The regulatory climate has changed with the new, with the new president and the new regulations and stuff. For better or for worse, that's neither here nor there, but it has changed, and this is one of the reasons that you potentially want geographic decentralization across jurisdictions, is because how different jurisdictions deal with cryptocurrencies, decentralized assets, and things that aren't even cryptocurrencies, AI, for example, right? How they deal with these things changes over time, and while some jurisdiction may be favorable today, 4 years, 10 years, 20 years from now, it may not be favorable. It may be very unfavorable. So one of the reasons that is an SF today potentially is that there's a more favorable regulatory climate for cryptocurrencies today, which is why we've seen a lot more American presence and US-based presence from various crypto projects, but that may not be the case 10 years from now. I don't know if that answers your question.
No, that was a great answer. I'm curious. So Pranav, I'm going to kind of put this on you, even though I don't know if you have anything to do with it. I feel like I've been seeing on Twitter out of A16Z recently, like things vaguely of the form like we need to onshore crypto. Is that resonating with you
Can I
at
stop
all?
Nub's answer for you? This is not financial or legal
Yeah,
advice.
this is not financial, legal, regulatory, or life advice. Yes.
Yeah. So not representing A16Z's views here. Yeah, so personally, not involved in the whole mess of a legal world that people on our team are working on. Yeah, I mean, I think my personal opinion on this stuff is that I think some of that is more saying like we want less sketchy like Cayman entity stuff, less so like pure American business.
Flashbots Ltd is a kind of entity. Sorry, continue.
So part of that message is just like trying to create favorable environments for companies and whatnot. But yeah, I think there's interesting, like on the point of view after decentralization of like, there's kind of two axes I think that are probably being brought up. And one is the more like making sure the systems are robust, kind of like the long tail events of like very powerful state type entities kind of trying to mess with these systems. And then the other end being, like how can we create better, like an equal playing field for people around the world and like operating on chain, right? So, if like all the infra is located in the US, then a team from Asia either has to move to the US or set up servers in the US, and they just will have a worse experience with their infra locally, which I think seems bad. And so personally, I'm interested in kind of looking, I think the former question is extremely important, but is very hard to like theoretically analyze and model. But yeah, so I'm personally more interested, just for the sake of what feels tangible today, of looking at the second half of that question of saying like, how can we just get incentivize having robust infrastructure and like the same types of latency everywhere in the world, or like an equal playing field of latency, right? So that your confirmation time is, say, a second in Japan and it's a second in New York. It's not 0 in New York and a second in Japan. And so I think there's a hope to building those types of systems.
Nice. That was a great segue. So I know, Quintus, we've also talked about recently this kind of dichotomy or maybe categorization of, I guess, robustness and fairness, maybe one very loaded way to bucket these things. Curious if you have any thoughts to riff on there.
No, I think it's a good way of separating things. That those, I think, this, the one property that you can think of it as censorship resistance. People say, like, oh, I want a note in Costa Rica because, if some government is censoring me, probably the Costa Rican government isn't censoring me and I can get on chain. And there's another, desire to have some proportional economic activity happening in Costa Rica. I think maybe to ask a question, I think when you talk about involving different geographies, you often hear this idea that says, well, why don't we have a per geography piece of infrastructure, right? We have like a DA layer in this continent, a DA layer in that continent, DA layer in that continent, and then each continent can be served by its local DA layer or its local whatever crypto infrastructure, and then maybe we'll have a bridge that connects those. And I think that does make sense to some degree, and a lot of the systems we're talking about sort of look like that. But at the same time, having like infrastructure specific to geographies with no connection between them also doesn't really meet the goals we are setting for ourselves of like bridging these trust boundaries between geographies. And one thing I would love to figure out maybe in this panel, maybe over the next couple of years, is sort of what are the trade-offs between those different kinds of designs, in what settings does one approach or another make sense, or even is even feasible? English.
That makes sense. Would you say that's kind of the relationship between like locally gated systems and like maybe worldwide or geo-distributed systems?
Yeah, I think that's a reasonable way of summarizing it.
All right, cool. I wanna pop the stack pop the stack back to the beginning when we had a little bit of a disagreement between Quintus and John about TEEs. So curious, why were you skeptical, John? And then we can open it up to the panelists' comments.
Wait, trying to remember what I was disagreeing about. I think I was disagreeing that you said TEs help geographic decentralization. Was that
That's
it?
the claim. Yeah. Let's debate that claim now.
Wait, no, I feel like you're supposed to back up the claim.
I can go. So I think there's at least two arguments that I'll make, and if I'm creative, I'll think of more. But one argument is not specific to geographic decentralization, but just decentralization in general. So if you look at we had a talk about snitching and proving collusion in MPC. And one problem we have with MPC is like we probably don't want to have a static committee for too long. It's easier to collude in that setting. And I think most of the snitching stuff can be circumvented by colluding in a TE and these kind of things. And if we have this problem of selecting committees and we need to rotate them often, then we have this high overhead of selecting reputable actors. And if you're in one geography, it's more likely that you don't trust actors in other geographies. And using a security model that protects against, or like a security primitive that protects against these kind of collusive threats makes it much easier to distribute these kind of trusted roles. So that's a point more generally about decentralization. And then one more specifically about geographic decentralization. And this is really Phil's point, and so I'll sort of make the argument at a high level, and then if you challenge me, I'll make him defend it. But it's that certain forms of security schemes require a lot of communication between nodes, like interactive MPC is another the same example I'll give. And if you have many rounds of communication between nodes, with a bound on how fast you want to do something or an incentive to do something fast, you have a greater incentive to co-locate. But with TEEs, the security doesn't come from communication so much. And so, yes, maybe you give up some other security properties, but reducing the number of rounds of communication reduces the incentive to co-locate.
To clarify, you're saying because you use a different protocol that just happens to require less communication?
Do you want to give your signing example?
Right. So yeah. So if we want to collaborate on, let's say, each using like a key to compute some sum of like a secret input that we each have without revealing any of the component inputs, right? Sum is a bad example because you can kind of recover it trivially, but let's say it's like a three-party computation. Then if you want to do it with like, let's say like a garbled circuit MPC, like just fundamentally the way the protocol is constructed, you will require like a certain amount of kind of interactive communication. Like we will have to like decrypt like one gate and then like send the data and then kind of proceed in like rounds to decrypt the entire circuit, because that's like where the hiding property comes from. It comes from the fact that like we're kind of going back and forth and there's some secrets and some entropy within all that. So there are like a wide class of protocols, I would say, where TEE kind of lets you eliminate that and do things kind of magically, which shouldn't be secure, but are. And so in that case, if it's okay to use a TEE, maybe you want to.
I'm convinced.
Okay, great. I was going to ask Pranav to pick a winner, but that didn't end up working out the way I expected it to.
Well, no, I mean, like it's very reasonable, right? Like a lot of what we're talking about, geographic decentralization is, co-location on one side versus spreading out geographically on the other side. And, the speed of light is finite, so of course, if you're dealing with something with a lot of communication overhead, then you want to reduce the total latency, because otherwise you're just spending a bunch of time just moving light around, basically. So it's a completely reasonable explanation. I have no objection.
Nice. Pranav, any thoughts on TEEs, light speed, or
yeah,
anything?
I think in general, it seems like T's basically never hurt unless you use them incorrectly. And so I think as long as you like know the trust model you're working with, okay, maybe not, but at least for like a decent amount of applications, or at least for geographic centralization, I don't imagine that it hurts. So yeah, I generally buy the agreement or the argument that like for protocols or card communication, if you can reduce that, they're helpful. Yeah.
I'm just gonna add, this is a completely random question, mostly for Quintus, which is, why don't you just build an open source TE?
That we're doing. It's a challenging problem, a coordination issue, but we're working on it, and I think we will do that in the next couple of years. Hell
Well,
yeah.
I want to see it.
Yeah, yeah. Happy to share. Yeah.
So okay, so we've talked about like a few things here, like $1 trillion cabal. Wow, I missed that. Sorry, it took me a second to process it. Hopefully this is not recorded. All right. So yeah, we've talked about kind of many properties here. It's like the communication, but also the distance between nodes and like the distribution into jurisdictions. When we have a new protocol proposal, like let's say MCL, or on the Ethereum side, like maybe there's a lot of noise now around reducing slot times or including inclusion lists or some other protocol change. How do we evaluate these things and weigh them? And I guess from all your perspectives as like operators in this space, like what is the biggest thing we're missing? Is it like a science? Is it data? Or what do you think, I guess?
I can give a very quick answer. I think that one challenge we have is that we want to simulate some of these changes, like a shorter slot time. And one thing that simulations miss is they miss incentives, right? They miss real world incentives. So you can replicate a network where all the nodes behave in the way you want them to, but probably, you know, there are going to be different incentives. Maybe you want to release a block late, and there's going to be some like trade-off curve, and you might want to release it very late if there's high volatility. And factoring that into simulations, especially for like the engineers doing it, is challenging.
Yeah, I mean, I think one hard thing is like markets are always just so hard to predict and like know what'll happen. And especially, you know, blockchains are always an interesting science in that you have app layer incentives and protocol layer incentives. And it's very hard to control the magnitude of the two and how they relate to each other. And so, you know, things like shorter slot times or changing the consensus protocol. You know, I think there's actually some arguments of like shorter slot times can like change the market structure so that like new types of applications can be developed on these things, which maybe kind of elicits more value for more parts of the world. So then maybe then the incentives actually, even if the protocol layer incentives are pushing you that, okay, now I need more centralized, or maybe my operating requirements are higher, so I have to leave certain places. But actually maybe on the other side, on the app layer, maybe there is more demand for more places. And so people actually do spin up new nodes in new places. And so you know, we can do all the modeling we want. It's always really hard to see exactly things play out. I mean, you know, I think econ is really good at giving us the directional way things will move, of saying, hey, yeah, well, like obviously if app layer rewards go up from Asia because like some protocol change makes certain applications viable there, then that seems good. But it's a constantly evolving fight to figure out how everything interplays and finding the right design.
Sure. I can add 2 points. I can expand both on Quintus and Pranav's points. So one of them, Quintus talked about simulations. So the third rule of engineering that I learned while I was in university is to find the answer, you must know the answer, which unfortunately applies to simulations, which is that it's pretty hard to simulate things unless you know what you're simulating. But of course, if you know all the incentives that you have to simulate, then, well, you just know all the incentives in the first place. And do you need to simulate it? Maybe, but also you know all the incentives. On the other hand, if you don't know all the incentives, then is your simulation worth much? So it's a very tricky problem indeed. So to expand on Pranav's point, I think it's actually a very good point that there are certain classes of applications that can't be built with certain latencies, for example. Right? Let's say you have, you know, a 12-second slot time like Ethereum. Maybe you find it hard to build perps DEX. That's a club, like Hyperliquid, right? So the Hyperliquid maybe chooses a different point in the trade-off space, but it enables an application that isn't quite a centralized exchange, arguably isn't quite a decentralized exchange, but, you know, certainly is different than something like Binance, that you simply couldn't build on Ethereum. And if, you know, is the world better because that app exists versus if it didn't exist at all? Potentially, yes. So this might be an argument not for maximizing decentralization or geographic decentralization, but rather allowing different applications and different consensus protocols and different blockchains to flourish that take
take different points in the trade-off space because that allows applications that otherwise users straight up wouldn't have access to. And then finding a way to aggregate and secure over these different protocols instead of trying to make one thing that is the best at everything, because arguably you can't.
Yeah, no, I think we've gotten to kind of an interesting place here, which is like what I'm hearing is that it's very context dependent and kind of nuanced, and you need to almost take it on a case by case basis. Would the panel agree with that so far? And very hard to measure probably is another aspect.
Well, yeah, I mean, the first things first is we need a metric, but good luck agreeing on a metric.
Maybe we need many metrics, and then we can argue about them, and one school of researchers can optimize for one, another for another, and some of it will be completely academic, but there might be something useful that comes from it.
Cool. One more question I have is how do you fit privacy tech into this? So I think MCL was like one example of this, where you have this kind of blinding property used, and maybe there are other possibilities with TEs. So how do you all think about kind of all these new privacy technologies? And like, is there anything that's super promising from a geo-decentralized point of view, at least in today's context of the kind of systems and regulation we have?
I mean, I think there's a distinction between privacy, like during block building, and like long-term privacy, right? So for things like peer-to-peer payments, that you might want to be private, like actually like forever, and not just when you're making the block. I think the types of systems you can make there look pretty different than types of systems that are just privacy during block production. Right. So like, for things like peer-to-peer payments, you probably don't care about like actually like 50 millisecond latency, like probably like, I don't know, 500 milliseconds or seconds, fine. And so like the incentives driving you to certain equilibrium in one case and apply in the other. And so I think there's definitely things to explore there. I mean, yeah, I think in the lens of like, can we get privacy during block creation time, which I think of as more of a market structure choice that enables certain apps that otherwise like couldn't exist. I think that's super feasible. Yeah, like, the TE stuff definitely makes a lot of sense there. I think the heading erasure code stuff I was talking about makes sense there. There's encrypted mempool type stuff that has a different sort of the trade-off space. And so yeah, I think the privacy, at least during block creation, is super compatible with still being geographically centralized. And then, yeah.
I can't remember who, but a very smart person remarked to me recently that potentially we've passed the peak of maximal decentralization. I think it was in Bitcoin. I have a bad memory, so maybe I'm remembering the protocols and things wrong. But like 2021, we have lots of hash rate in China. And then it gets banned, and all the miners leave China's. If you view the world as having like two poles of power, that's a very important loss of diversity in the network. And if we had better privacy at the network layer, at the level of the participants, then you'd probably see deeper penetration into a wider set of geographies. Yeah.
I'm gonna make a hot take related to what you said at the end there, which is that my hot take is that I'm unconvinced that on-chain privacy is viable long term, and protocols that rely on it, such as MCL. Sorry, Pranav. There was a presentation at SBC actually on this topic about de-anonymizing the Ethereum validators. And basically, they just had the TLDR, to just summarize it, and someone correct me if I'm butchering this, but they just put some validators around, watched the attestations that other physical nodes sent, used some heuristics and stuff, and basically figured out with fairly high degree of confidence which validator corresponded to which physical IP address. This is not like an inherently new idea. I was talking about these kind of attacks with Dankrat like half a decade ago. He was unconvinced at the time that this was possible. It turns out it is. Also, this is not my idea. I heard it from someone else at the time. Just so you don't think I'm trying to take credit here. But you can do things like this to de-anonymize people at the peer-to-peer layer. So even if you fully encrypt or fully ZK or whatever, what happens on-chain, there's nothing stopping adversaries from watching what happens off-chain. And it's very hard to hide your IP address because you need to connect to the internet from somewhere. And my hot take is that I'm unconvinced that, especially if we move towards an ever-increasing surveillance state where privacy is actually needed. In other words, when we need privacy versus when we don't need it. When we need privacy, if we're in a surveillance state, it's very likely and very possible that everyone's IP address is going to be watched, and everyone's going to know, or at least the actors that may want to censor will know who is transacting. Even if you do all the ZK and all the math in the world and there's no backdoor, they'll still know who is sending transactions because they can just watch the physical bits move around on the internet pipes. So that's my hot take. Hopefully it's not true, but my hot take is that we'll see stuff moving in this direction. And crossing my fingers we don't, but it might.
Isn't the action implied, the required action from that fear that we should increase anonymity sets as much as possible to normalize? Okay, so for example, you want to hide that you're an Ethereum validator, right? If we have some specific encryption, whatever hiding scheme that is only used for Ethereum, then you can tell if someone is using that by monitoring their traffic. But if you have a general scheme that people just use to browse the internet and use Ethereum and whatever, and that is the status quo, then it's much harder to identify people who are doing the bad things. Right?
Yeah, that's a possible solution, but it means that if we want to resolve this, we need to look for solutions elsewhere and not just ZK encrypt on-chain traffic, for example. We need to think of more creative solutions that, like you said, maybe that's one solution.
Decentralize outside of Ethereum. Yeah.
Any thoughts on privacy, Pranav? You got two mics. Yes, opposite of privacy. Yeah.
Yeah, I mean, on this type of privacy, I haven't thought about it too much. I definitely see, yeah, there's basically whatever cryptographic model you have always, there's side channel attacks is basically what you're getting at, which definitely makes sense. I mean, I think this is less of a concern for the block production time privacy. I don't think of this type of privacy as being stuff that I think of that as being much more economic in the sense of, oh, I don't want people to see my bids. I don't want people to know exactly how much I'm bidding at the second. But in a second, I'm fine with that being revealed because the auction's over. And so at least privacy at block production time that only lasts a second or half a second or even less than that, I think that's still fully compatible with everything else.
Cool. That makes sense. I would love to take some questions from the audience if we have a minute for one or two. And if not, I have a closing question. I think we're almost out of time, right? Yeah, cool. Anyone have any spicy questions?
We have a de-anonymizer over there, by the way. We were talking about your work earlier, Leo.
Advice or plans on how to still capture that traffic?
Maybe you should repeat the question just for the recording.
So the question was that basically users and chains are moving towards kind of this lower latency paradigm driven by things like demand for high frequency trading and other use cases that just require this lower latency to exist. And to the extent that this is in tension with geographic decentralization, running things over a world scale network is slower, how do we think about that? Or is there any advice for managing that tension?
Yeah, I can start maybe. So I think there's one interesting thing. Then this is kind of the Solana viewpoint of if one of the end games is let's actually build a chain that hosts the world's finance. So it's one interesting point is that execution can still be extremely fast, even with a very like globally centralized network, right? So the only thing geo-decentralization forces you is it says, okay, there's like a minimum, at least like couple delta latency to confirmation of transactions, right? And so what that means is when you submit a transaction, it will only be executed kind of at earliest like 200 to 400 milliseconds later, and then a consensus protocol you run that runs around the world. And now it's not obvious this is like inherently unworkable for TradFi, right? So you can still have that like the tick rate of the blockchain is going at say every 10 milliseconds, 20 milliseconds. It's just extremely pipelined, where kind of the transactions that are currently being executed were queued up 200 milliseconds ago somewhere around the world. And so I think one interesting thing is this is actually just like net new like market structure that doesn't exist in TradFi. Like there is no sense in which like a Asian exchange is on the same server as a like American exchange. And so I mean one of my hopes is that like actually this new market structure can actually like enable new types of applications and activity where maybe like this slightly different model of like a like I don't know if it's inherent that like you need finance to move at a rate of like sub 200 milliseconds to like actually be extremely productive. And so if there's apps that benefit from being on the shared state that still get the like instantaneous execution, but just delayed by this fixed amount, I think we could still live in the world that's decentralized with those properties.
Correct me if I'm wrong, but it's interesting that you mention a tick rate with pipelining, because that sounds isomorphic to a live blockchain with a finality gadget, which is essentially what Dev, the lead dev, no pun intended, of Osmosis has proposed with dev sharding. So dev sharding is essentially a hierarchical sharding scheme where you can have small committees that can be geographically co-located, and then they produce a bunch of blocks potentially extremely quickly, and then you have a larger globally distributed finality gadget, if you want to call it that, that attests over attestations from the committee or blocks produced by the committee, which sounds like an isomorphism of basically what you're saying, which is you have a very fast tick rate and then you pipeline things, therefore you have a finality gadget that operates over the very fast blocks. So it sounds like, and from what I've seen, there's a lot of similarities in things like dev sharding, multiple concurrent leaders, what you're describing here, roll-ups and all this other stuff. There's a lot of like convergent evolution where they're all kind of converging on something, a solution that has a huge amount of overlap, potentially though with different terminologies because we're approaching it from different angles.
Yeah, so I think it's so that's close. It's a bit different from what I was describing in the sense of, so yeah, I think that design makes a lot of sense of you have just different geographic areas that are producing at their own rate, and then there's some shared settlement across them. In the MCL version of this, it would be that like like the Tokyo and New York proposer make their blocks at the same time, and then they make another block 20 milliseconds or 40 milliseconds later before the previous block has like gone through that whole pipeline. And so at execution time, you're executing the batch of transactions from everywhere in the world at the same time, which is, I think not quite the same, but definitely I think it's a different point in the same trade-off space. But yeah, there's definitely, I think, tons of designs here that will be interesting to see how they all play out.
I kind of buy the convergence because I hear what you're saying, but in some ways, you don't have to consider the execution as happening at like finality time from like the global gadget. You could say like, oh, hey, my regional chain like confirmed it. Maybe it's like good enough for this use case. So yeah.
Yeah, and there's a trade-off curve then where if uncertainty is expensive for you and if uncertainty is unpleasant, then you want to use a local system and you don't tolerate the like overhead or the latency of being interoperable. And if you benefit a lot from the shared state interoperability, then you take on the uncertainty of having to wait for the global thing to come to consensus. And that's like, I agree what all of these systems are tending towards in some janky way or another.
But it also means it was very exciting because we're going to see, I think, these systems evolve and be deployed over time, and not just be theory, which is nice because all the blockchains to date have just been single shared states and single global consensus, and that's it.
So now we're going to see, systems that pop up like this is going to be, Cambrian explosion, and it's going to be very exciting.
Maybe just one thing to add here is I think we're very critical of, so like, you can imagine some system deploying 4 validators in the same country, and we all say, oh, why don't you just run a single server? And from this global decentralization perspective, that makes sense. But if we're thinking about it in this more hierarchical setting, from the perspective of the people in that country who maybe have a different relationship with the government, that still is a meaningful kind of decentralization. And maybe our critiques of systems should be more nuanced as well if we want to encourage this kind of hierarchical system.
Yeah, like, for example, just as a concrete example, so that's not just purely theoretical, is that, let's take Hyperliquid. Again, nothing against Hyperliquid, just as an example. They're based in Japan. They run their 5 validators that have 99.9% of the voting power, and all ran by the Hyperliquid Foundation, all out of Japan. It's great.
Closed source.
Closed source, yeah, all that stuff. But if you're in America, you can't use it, and there's no possible way you can get around to use Hyperliquid. So from an American's perspective, do you care that they're all in Japan? Not really, right? Now, if you're in Japan, well, it's nice if they're in Japan because you get low latency, right? So you're correct that just because something is co-located doesn't mean it's bad for everyone. It could be neutral for some people and good for other people.
I think if I was in Japan, I'd prefer that the validators are run by different entities, and that the code is open source.
Yeah, but that's orthogonal to the geographic, then the co-location part.
Yeah.
All right. Thank you all. Let's thank our panelists here. That was really fun. And thank you to the entire audience for staying through such a marathon day. Hopefully you learned a lot about MEV. And yeah, that's all we have, I think. Anything?
At SBC. Thank you all for participating. See you all next year, I hope.
Yeah, see you all next year. See you all next year. Hopefully not in SF or New York, but I already know it's going to be in SF, so we failed. Palo Alto. So yeah, see you there.